PhD student here with Sawbury, and it is my pleasure this morning to introduce Vivian Zaff. Vivian is the director of the QSC, and Vivian serves as the secondary contact for the DOE and helps oversee the QSC research efforts. As scientist at the National High Magnetic Field Laboratory Pulse Field Facility located at Los Alamos, her research focuses on using high magnetic fields as tools to induce, probe, and understand potential quantum spin liquid states. Zaff is a fellow of the American Physical Society and currently serves as the chair of APS's Division in Material Sciences, as well as leads the magnetoelectric couplings and quantum materials thrust for the Center of Molecular Magnetic Quantum Materials, a DOE Energy Frontier Research Center. She received her PhD in physics from the University of California, San Diego, and was a postdoc at Caltech, and joined the Los Alamos National Labs in 2020.
2004.
2004.
Yes.
I think there's a typo.
I wish it were 2020.
Please join me in welcoming Vivian.
Hey. Good morning. Thank you for, I figure the important dedicated people are here on the weekend. And thank you for sticking around. Okay, so I'm going to talk about magnetic approaches to quantum information, except I'm not going to talk about all of them. I'm going to only talk about the ones where I know a little bit about them, which are spins and molecules and spin liquids. So, of course, spin is a great quantum property, and so we have a number of different approaches to quantum information that are based on it. Spins and molecules is probably one of the ones that's coming up from behind. We don't have practical gates yet, but there's some ideas that this is going to be helpful. Spins and quantum dots is, of course, almost there. There's commercial interest. There's prototypes. Magnetic defects in semiconductors we've heard about. All of the ones on the left involve individual spins. The one on the right is sort of fundamentally different from the ones on the left because you're talking about collective behaviors of spins. So on the right, we're creating frustrated interactions between spins in order to generate these collective quasi-particles known as anyons, with the hope that those could one day be used for quantum information. Everything that I work in is in the, it's not there yet, there's not yet a lot of commercial interest. We're still in the basic science stage of trying to understand it. As soon as it goes into the commercial space, then it leaves labs like mine and goes to other labs. Okay, so I'm going to start with spins and molecules. And here are the ideas that you use the power of molecular chemistry to shape, firstly, the behavior of your spin and its environment, and secondly, the architecture of your eventual quantum information system. And so actually this is out of date, a 15-year effort that ended 5 years ago, so let's call it a 20-year effort of very dedicated work by chemists to improve the coherence times of spins and molecules has brought the coherence time up to, and here the important thing is not how long the coherence time it is, but how long it is compared to your gate operation. So we're at 10 to the 6 gate operations per coherence time in theory in spins and molecules. Of course, no one's built a gate yet, but if they do, that's your figure of merit. And so this effort involves, of course, thinking about nuclear spins, thinking about the kinds of phonons that you get in large squishy molecules to minimize that effect on the decoherence. Okay. And then if you make a gate, well, a gate with spins is simple. You just turn on a magnetic interaction. Of course, how to turn that on and off in a molecule is tricky. So here's an example where you have an intermediate spin between your two qubits. And now, because you have anisotropy axes that vary across this molecule, by varying your magnetic field direction, you can select whether you're going to talk to the one qubit, the other qubit, or the one in between that turns your gate on and off. Now, this is still mostly theoretical, but in principle, this is a C0 gate. in a molecular system. Now, the problem is how to make just one of these. You can easily grow a crystal with 10 to the 23 of such gates. Getting this down to individual control is where this field needs to go next. Okay. Where my efforts are is in trying to control the spins with electric fields. Right? So of course, the technology of applying electric fields and currents at the nanoscale has developed over decades by the chip industry. So can we exploit that for molecules? Can we expand molecules to where they match nanoelectronic systems? And then can we think of the physics of how an electric field is going to control a spin? So we've been working on several ideas along this direction. And I'm just going to give you 2 quick vignettes in this direction. So the first vignette is something called a spin crossover. Aha, there we go. So in the top, so this is a molecule. The red thing is the spin. The spin is manganese, and the spin is 1. And so it looks like this. And it's in a relatively symmetric molecule where there's no electric dipoles, because the negative charges balance the positive charge. However, if you take the spin 1 and you turn it into a spin 2 by promoting an electron, at that point, the Jahn-Teller, the quasi-Jahn-Teller effect in this material pushes the magnetic ion, this is the manganese, out of the center. It becomes energetically favorable to have an asymmetric electric field on this arrangement of orbitals here. And now you have an electric dipole. So now you have a very simple way of coupling the size of your spin to an electric dipole. So now in principle you can control your spin state with electric fields, or vice versa, read out your spin state by the presence of this electric dipole. And this is completely distorted. Actually, it's more like 4 to 5% change in bond length, not a factor of 2 change in bond length, but it's big enough. So then you have this coupling of magnetization, which you can control with field and temperature and so forth, to electric polarization, and you have this hysteretic switching. So that is one direction we're pursuing. Here's another idea that we're pursuing. So this is taking advantage of frustration. So this is your classic triangle of 3 spins. And it turns out you can make your classic triangle of 3 spins in a molecule. And this one's not entirely frustrated because, well, they can just adopt this 120-degree arrangement. But it turns out that when you apply a magnetic field and you start lining up the spins, well, these antiferromagnetic interactions are less happy because their spins are lining up. This one's a little bit more happy. So you start shifting the atoms in between, and you start changing the exchange interactions in order to minimize your magnetic energy. The happy bonds want to have bigger exchange interactions. The unhappy bonds want smaller ones. The net effect is that you get an electric dipole. Another way to think of it is that if you just look at the symmetry of the spins, here the spins obey mirror symmetry. Here they do not. The minute the spins don't obey mirror symmetry, then the lattice doesn't obey mirror symmetry either because of the way they're coupled. And the minute you break mirror symmetry, you get an electric polarization because electric dipoles also don't obey mirror symmetry. So now you have a linear coupling of an electric dipole to a magnetic field. And once again, we have a way of controlling this. So here's the data on this molecule. So this particular compound is a triangle of iron spins. And what I'm showing you here is the magnetic susceptibility as a function of time. And the reason it has a sawtooth pattern is that the electric field that was applied with a sawtooth pattern. So you can see how the electric field modulates the magnetization of this compound. So with this, we're sort of developing the basic physics tools by which we can then use electric fields to control the spins in some future system. Okay. And then the next stage beyond that is, how do you architecture this into some larger system? So there's a research effort at Los Alamos on molecular frameworks. So these are, well, the chemists say these are plug-and-play Lego systems. It's not quite that simple because it's chemistry and the atoms do what they want to do, not what you want them to do. But you do have a lot of room to play with, altering the ligands, altering the pore sizes, and so forth. And so the hope is to create an architecture that could be used as a quantum simulator. And also we can think about expanding the size to match that of being able to put copper wires on things, which is something like 10 nanometers or a little bit less. So in principle, you can then scale this up to billions of identical qubits using the power of chemical self-assembly, plus or minus a few defects. You can control the spacing. You can do things with the pore framework to put things inside, different functional elements. And then you can, if this is two-dimensional, you can then come in with electric fields, or you can come in with photons, would be another way to control the system. So this is the beginnings of a research in progress. Okay, so that was my few vignettes about spins and molecules. And then the second half of my talk is about collective patterns of spins, such as spin liquids. Are there questions on my spins and molecules? Yes?
So what's the substrate for this spin liquids? The living solution? Yeah, or the idea is for them to live in a...
Well, yeah, I can hear him.
Okay, so repeat the question. The question is, what's the substrate for this? So the living solution or somewhere else?
Yes to all. So, well, we usually start with single crystals just because they're big and we can measure them easily. Of course, an eventual quantum information system probably will not be a single crystal. I mean, you can maybe make a sensor be a single crystal, but if you want individual control, you need to go out to thin films. Yeah, and then you put them on a substrate which varies all over the place depending on your molecule. I mean, these are not oxides. You don't need strontium titanate. You can put them on a lot of different things. Yeah.
You showed the graph with the magnetic field on the time. Yeah, why is it so slow here? Does it anyhow correspond to Rabi frequency, or?
That was just the speed at which we chose to apply the electric field. So we'd have enough time to measure it. Yeah.
I'm just curious, are you considering any form of spin-orbit coupling in these systems?
Yes, depending on the spin-orbit coupling can be important. These are the two examples are 3D spins where it's weak, but still plays a role, for example, in the Jan-Teller distortion. You can also do this with heavy ions where spin-orbit coupling dominates, like iridium or what have you. But the fundamentals remain the same. I think young Chen had a question.
There are lots of these molecules with very long names, but I wonder, what is the best molecule which behave most like a ferromagnet, even in the individual molecule, if that's even possible, meaning, let's say I can maintain a stable vertical moment, has even some kind of memory or hysteresis effect. Which one is the best?
Okay, well, if you want to create something like a ferromagnet, that's actually a different challenge than making something like a qubit. They kind of go in opposite directions. So there's actually, the ones on top are the ones where people are looking for qubits, and the ones on the bottom are the ones where people are looking for something like a ferromagnet. And so I think that these terbium phthalocyanines, PCs, phthalocyanine, are still the state of the art. So,
Final question.
yeah.
So when people talk about spin teleportation in this molecular system, what exactly do they mean?
Excellent question. I've asked them that question too. Well, they're doing sort of an exchange interaction where they have a molecule and then they have a spin on one end, a spin on the other end, and an interaction between them, and then they manage to entangle the two spins, flip one, teleport it over there. I don't see how that's not just an exchange interaction, but apparently it's teleportation. So,
What is the information they are passing? It's just like
the spin state.
spin state?
Yeah. I may be missing something. But certainly it's cool that you can do it in a controlled way over a long molecule. That's kind of different from normal magnetic interactions that we think about. So. Okay. Okay, so moving on to the other far from yet practical applications, but still in the fascinating physics stage of thinking about quantum information, is spin liquids. Okay. So collective patterns of spins. So we're not thinking about a spin as containing quantum information, but some emergent pattern, usually an excitation of a collective system. Of course, the standard picture everyone shows is skyrmions. I'm not going to talk about skyrmions, but it kind of gets the point across that you have complicated spin patterns. Okay, so at the heart of this is magnetic frustration. I assume you're all familiar with the standard triangle that's frustrated. And then right now, a lot of people are working on frustration on honeycomb lattices. But if you think about a honeycomb lattice, it's bipartite. So if I make the red, I make the blue spins up and I make the red spins down, there's actually no frustration. This is an unfrustrated lattice. So the way you make it frustrated is you go to Kitaev interactions, as proposed by Alexei Kitaev. So if you take a Kitaev interaction and you put it on a honeycomb lattice, then you get frustration. So what is a Kitaev interaction? Let's go. So we have Ising interactions that couple one axis of the spins. We have Heisenberg interactions that couple all of the components of the spins. A Kitaev is somewhere between those two, where it's an Ising interaction, but the quantization axis of your Ising spin, the quantization axis of your Ising interaction depends on the direction of the bond between the spins. So here is a honeycomb lattice with Kitaev interactions. And so, for example, along the blue bonds, the X components of the spins are coupled. Along the green bonds, the Z components, and along the red bonds, the Y components. Now notice that X, Y, and Z are orthogonal, but these three bonds are not. So it's not that the quantization axis is along the bond axis. It's just that you have these three different choices. So this turns out to be frustrated. And it's frustrated in an extremely quantum way because a single spin is participating in three Ising interactions, each with different directions. So maximal frustration. So the resulting spins, this is where the pictures stop because I don't know how to draw the ground state of a Kitaev spin liquid. But I mean, basically it tries to solve the frustration problem for, let's say, 1 out of 3 of the bonds, making that bond happy. And then it goes into a superposition of making all of the 3 different possible bonds happy. And then that's your ground state. So it's a superposition of solving the frustration in different ways. Okay. So it turns out what's exciting about these potential Kitaev quantum spin liquids is not even just their ground state, but their excitations. So the excitations out of the ground state, which are nominally gapless for a simple Kitaev quantum spin liquid, these excitations can be modeled as, or are, non-abelian anyons. And the reason we care about excitations that are non-abelian anyons is they can be braided, as demonstrated by Daenerys, if you allow this classical picture. Okay, so a quasi-particle is an excitation that it's not an excitation, it's a pattern of spins, or it's a pattern of some aspect of the spins. So it's non-localized, it's delocalized across your sample. And when it's non-abelian, so non-abelian means it doesn't commute. Anyon means you braid them and you get a different state than you started with. So now, as you move non-abelian anyons around each other with some arbitrary phase, these operations can then be mapped onto gate operations. And the hope is that they're fault tolerant because this is a topological system. Okay. Topological because we're not dealing with individual spins, we're dealing with delocalized patterns that have now become braided. And so your quantum information and your gate operation involve the state of a large delocalized system with many particles where a single local noise event isn't going to mess with your quantum information. You have to undo the entire braiding system of a delocalized system. So that is what's driving this research into topological spin liquids. Okay. However, depending on who you ask, we do or don't yet actually have a Kitaev quantum spin liquid. So we definitely have magnets with honeycomb lattices. We definitely have, we're pretty darn sure that we have Kitaev interactions. Actually, a lot of that work was done by Arnab, sitting here in the audience, and these slides I will also show. But whether we definitely have a Kitaev quantum spin liquid is still a matter of debate. And the issue is that, that these Kitaev interactions are just one set of interactions, and then we have all the other pesky interactions that appear in magnets. Of course, these are not always pesky. There's perfectly respectable magnets that are based on such interactions. But if you're trying to create a Kitaev spin liquid, then these become, these take you away from the pure Kitaev system. However, luckily, at least in theory, you can still have a Kitaev spin liquid with some small amount of these other interactions. And so then what happens is your Kitaev spin liquid can, in some cases, become gapped, and it's also moved to high magnetic fields. So the leading candidates all involve this spin liquid state appearing in high magnetic fields, which, since I work at the high field lab, it's nice for me. Oops, let me just go show. No, okay, I'm missing a slide. That's okay. Okay, so there's a number of different candidates, which I was just going to show you, but we'll get to that in a moment. This is ruthenium chloride, which is probably the leading candidate, in part because it contains ruthenium that you can actually probe with inelastic neutrons, in part because we haven't yet disproven that it's a Kitaev quantum spin liquid. And so the point is that in the red region here of this phase diagram, so this is temperature versus magnetic field, so it forms ordering, because of all these other interactions that break the frustration. But then in applied magnetic fields, depends on angle, but somewhere between 7-ish and 9-ish or 10-ish, sometimes Tesla, you have a region where it apparently does not order. And then this is where people are debating whether that is a Kitaev or modified Kitaev quantum spin liquid. And then I'm just showing on the right some other phase diagrams. This was, this paper grabbed the attention, but it's actually not the end all of the phase diagram. The phase diagram has additional phase transitions. It depends on angle and so forth. So these slides then come from Arnab. So this is sort of the latest in trying to understand this compound with inelastic neutron diffraction. So the question here is whether it's a gapped or an ungapped spin liquid. And so there's been attempts to look at this with heat capacity. So I'm just going to go a little bit quickly. So this is Arnab's and his students and postdocs inelastic neutron diffraction data, where this is a gap. These are the excitations. And then this looks like it's probably ungapped, and this might be diffuse fractionalized excitations. And so it turns out that this gap depends on angle, and it also depends on magnetic field. So this is the gap versus magnetic field. So you can ask Arnab more. I'm going to move on. So that's kind of at the center of the current controversy. This is another possible Kitaev spin liquid. This is probably less exciting because there's some questionable neutron scattering data, but here the idea is that you're using cobalt instead of ruthenium as the spin. Cobalt, it's a 3D, so it has less spin-orbit coupling, but the hope is that the Heisenberg interactions in the system are weak. And so another way one can look at these compounds in high magnetic fields is that as you get to very high magnetic fields, you need measurement techniques that can tell you about phase transitions. And so a lot of the measurement techniques that we use here are listed, and magnetization kind of has a limited use because many of these complex spin systems don't have a net magnetization. But there's other things you can look at, like entropy. So you can look at specific heat, you can look at magnetocaloric effects. And then going back to this electrical control of spins, the minute your spins or their excitations break mirror symmetry, well, then you can see it in their dielectric properties. So this is a symmetry probe of magnetic spin systems. And then you can look at the lattice, because spins couple to lattice. So this is probably one of the most sensitive ways of detecting a phase transition at high magnetic fields, is to see if the length changes of the sample. So by all of these different techniques, we've mapped the phase diagram in high fields of sodium cobalt telluride, which is very complicated, depends on angle, is hysteretic. But the point is that the orange, hello, there you go. The orange region here is the subject of debate, whether that is or isn't a Kitaev quantum spin liquid, so between about 8 and 10 Tesla. Okay. So this is my summary slide. So within the Quantum Science Center, these are the main compounds that we're looking at to try and look for a Kitaev quantum spin liquid. With the arrow is sort of my attempt to summarize how hopeful we are and how far the research has gotten for that compound. And this ranges from 3D all the way to 5F, varying degrees of exchange interactions and spin-orbit couplings. This is a very active area of research. In the Quantum Science Center, the Quantum Science Center has many different institutions. Each one gets a different color on this slide. So this is to show that we're working together to tackle this big problem, from sample growth to characterization to neutron scattering to some of more advanced measurements like spin noise spectroscopy. These are some theoretical proposals for how you can then actually detect and braid the non-abelian anion excitations using different device structures. And then here are the first attempts, and I believe this is from Young's lab, of attempting to grow these. So, okay, so questions on the second part of my talk, and how much time do I have? I think that clock. Okay. Yes.
Any potential candidates who are in the play which would not require that huge magnetic field?
Well, depends how hopeful you are. So these compounds supposedly have this hydrogen lithium iridate could be a spin liquid at zero field, but there's a lot of questions about disorder in that compound. Right? So disorder is always the leading alternative explanation for why you don't have ordering. So I think that kind of summarizes the state of that compound.
So what is the lifetime of this excitation?
What is the what?
Lifetime.
Well, first we need to show whether there are excitations, and then we can measure their lifetimes.
I mean, typically, what do you expect? I mean,
I don't know. I mean, in principle, they should be long-lived, and in principle, we should find ways to stabilize them. And they can be pinned by defects in some cases. But since we haven't yet verified that they exist, that's still a very theoretical question. So, So I mean, there are various proposals for how to generate them, how to pump them, how to pin them, how to braid them, and so forth. And then once they're braided, well, now you have the topological stability. Right? Oh, yeah.
Thanks. Are all these materials at least candidates for the non-abelian type of
Yes.
spin liquid? Okay.
Yeah, these are all Kitaev quantum spin liquid candidates. We call them PKQSL, putative Kitaev quantum spin liquids.
Are there quantum spin liquids which are abelian?
There are such, but not in this category. If you have an abelian spin liquid, you could maybe make a non-abelian excitation with geometry, with holes, and so forth. So that's certainly also a direction. Okay. Okay, so yeah, in my final few minutes, this is actually stolen from here and then modified and expanded different approaches to quantum computation involving atoms, superconductors, spins, topology, photons. In the Quantum Science Center, we mostly focus on the gray areas, with particular emphasis. We have one entire thrust on the topological materials. I have a few slides about the Quantum Science Center, just to summarize. So the Quantum Science Center is a DOE-funded National Quantum Information Center. As you know, they're hosting the summer school, which has 3 thrusts, 1, 2, 3. The one on the left, it focuses on the science of and the discovery of these topological materials. The center thrust, led by Andrew, who is also possibly here or talking, is on algorithms. And the one on the right is on dark matter, which actually has strong ties into quantum information. Firstly, because they need sensors based on, let's say, transmons and other such things for sensing dark matter. And secondly, their attempts to move to very large arrays is pushing the technology of large arrays of qubits in a way that the other industries aren't yet. And so what they're learning is going to feed back as the quantum computing companies try to scale to the next size. Okay, so here's most of the institutions that are involved: 4 national labs, 3 industries, 9 universities, plus additional industry partners. And then on the right is the attempt to tell you that we're all collaborating together using pretty colors. So, and these are the list of different quantum computing platforms that are in use in the Quantum Science Center. These lists have a way of being out of date the minute you write them, but at some point this was the list, with the ones at the top being the commercial systems and then the non-commercial systems being explored at each institution. So that is most of my talk. Thank you very much.
All right, any more questions for our speaker? All right, one more.
Outside of quantum spin liquids and these superconducting wires which people played with, any other systems which people seriously considered as candidates for nanobillion anyons?
Well, there's the
Like maybe-
fractional quantum Hall.
Of course,
Which
right. I
we
forgot to
heard
mention
about,
that. And
yeah.
in addition to that,
There's,
like other material platforms which people could look at.
in theory, there's spin chains, which you could imagine in molecules. How you turn that into practice isn't yet clear to me. But yeah, you could have an interacting high-spin spin chain, and then at the ends you have a leftover spin a half that can act as a non-abelian anion. So
That looks promising. Anybody pursues this particular direction?
theoretically, sure. Experimentally, how you would detect it or make a single spin chain by itself and detect its ends is just as challenging as the superconducting version of that. So,
Thank you.
yeah. And there's probably more, but.
All right, let's thank our speaker one more time. All right. Thank you very much for being. Our next speaker is Chen. Professor Chen is the Carl Lark Horvitz Professor of Physics and Astronomy and also Professor of Computer and Electrical Engineering. His lab exploits quantum physics to manipulate electrons, atoms, spins, and photons in various materials and artificial systems with the aim to uncover novel quantum phenomena and new states of matter.
Oh, sure.
And to explore applications in quantum devices, such as quantum information and quantum computing devices,
According to
nanotechnology, such as nanoelectrons and nanosensors, and energy. Professor Chen is also the director of the Purdue Quantum Science and Engineering Institute. Please join me in welcoming Professor Chen.
Okay, thank you very much. Can you hear me? Yes. All right.
That's yours.
Yes. Okay. Just start. Which one is control? Okay.
Okay, now try it.
Yeah. Works. Oh, okay.
Oh, whoops, 1 second. Okay, now try it one more time.
Okay. Yeah.
Okay.
So here's pointer. Okay, thank you very much. Good morning, and thank you for coming out on Saturday morning. So first of all, I want to thank the organizer of summer school, Sasha, David, and the team for really doing a great service to our community to put together a wonderful summer school. This is the third time, and it's a great program. And also wearing the hat of as a director, PQC, Purdue Quantum Science Engineering Institute. Again, I want to extend one welcome to our guest from outside Purdue. And PQC, just like QSC, is very much about collaboration. We want to encourage cross-disciplinary collaboration between both within the university, also beyond university partnership with institutions like Oak Ridge, Los Alamos, and other institutions in Quantum Science Center to attack problems that cannot be solved by individual laboratory or individual departments. And in addition to research, of course, the workforce development, education is a big part of that. So again, thank you for the opportunity to present something that's dear to my heart at this summer school. I chose a topic that's maybe a little bit different from, so my group has some activity on the electronic side of quantum matter. Vivian alluded to one example, but we also have experiment effort going on the atomic side of quantum matter. And I chose this system. I'll tell you a few stories. Also the key word spin, which Vivian already mentioned, in my opinion, spin, one of the best currencies of quantum science technology. It's the platform, it turns out to be a spinner, atomic BEC, is a wonderful platform for doing quantum transport, simulation, and even chemistry, which I'll give some examples. But also, I think part of the topic today, the third day, we'll talk about some education. I think it's also one platform to illustrate, demonstrate some really simple, but I think powerful phenomena in quantum physics. It's not only, I think, a good teaching tool, but it's also kind of, at least to me, inspiring when you think about something very simple, fundamental, but in a different way, in a different context, it generates new ideas and new approaches. At least that's the hope. Okay? But I will kind of make connection to a bigger context. So some of these, the platform, even in atomic system, is very much related to, in one way or another, to the effort on what I call spin helical particles. I make some connection, give some examples, including electrons, which is a very nice platform to engineer, realize quantum matter and quantum technology based on, say, topological states matter. All right, so, okay, again, it's a Saturday morning. How to start with a coffee, or a cartoon, to that matter. Okay, so here's a cartoon of mine, pulled from internet. I have some citation in the comment, but to me, what Quantum Science Center is about is bring all these different beasts together, different disciplines together. We keep talking about the power of quantum science, quantum computing, how it can solve a tremendously complex problem. But another very powerful thing about quantum science, it really has brought together disciplines that traditionally are not necessarily interacting on a daily basis. I think I'm not speaking alone to say, since we launched Quantum Science Center, me as a condensed matter / bit AMO physicist, talking a lot, certainly a lot with high energy physicists, or even people doing dark matter. And previously, we don't interact that much. And now we talk, if not weekly, but very often. And that is very powerful, I think, from a scientific sociology some kind of point of view, because if we keep doing this for some years, something good, I think, will happen. We may not know what it is. And the cartoon, of course, this is a bit physics-centric cartoon. It brings all these different beasts of physics together, drinking the same water. That water is quantum, of course, quantum physics. It kind of feeds all of us. Did I hear somebody say the water is the DOE money? But of course, we also need DOE funding as well. But of course, this is a physics-centric cartoon. Of course, we also bring engineers, chemists, even business and political scientists, because there's really complicated business and political issues also in this kind of emerging technology. We can talk about that later. So I think it's really important to keep in mind the value of the Quantum Science Center to really kind of bring many different disciplines idea together. I hope I can illustrate some examples. So what I primarily want to discuss is a platform of atoms or particles in general with a spin degree freedom. Here by spin, it may be more than just 2 spin states, could be more than 2, but we all know the simplest, oops, I'm sorry, I probably did the same thing.
The secret
All right, okay. All right. If it's two-level system, we can represent by block sphere, right? Up and down spin, you can create superposition, but idea, in general, you can have multiple of these kind of a spin-like discrete quantum number you can deal with. And if you can do this, so this summarizes some main idea I'll talk about in case I don't finish, which is quite often the case. So already you can do very interesting things. If you have a particle like atom, which you can create superposition between different spin states. Imagine you can have a chemical reaction or two particle form molecule, which I'll give you examples. If you put them in superposition states, which now we have the ability to do so, they can react simultaneously in different these spin combinations. Up can react, up down can react, for example. And if you can do this in a coherent way, there can be interference between these different chemistry. So this is a little bit like Young's double slit in some kind of Hilbert chemical space. Okay. The amazing thing is, this is a simple idea actually worked out. Provide a possible way to control chemistry using just the spin degree freedom. Okay. You can do a lot more. Turns out if you couple to the momentum, okay, spin moment coupling, that's what I call spin helical particles in the later part of talk. And here, by coupling different states with optical beams, and that can include RF, microwave, but with the lasers, you can introduce a momentum kick. You can actually create, you keep doing discrete momentum kick, you can generate some kind of a discrete lattice in momentum space, which look like a reciprocal lattice. And that actually, in turn, can allow you to create a periodic, something like a crystal. So you can synthesize a crystal like a phase, even without imposing a periodic potential in the first place. That you can actually study by transport measurement. I'll explain how you do transport for neutral atoms that you cannot flow a current, but you can just apply force. And with that, we can actually probe topological band structure in many cases with a very interesting analog or some new aspect from things like topological insulator, topological semimetal, which is also studied a lot in this center. So that has been very interesting platform to explore some of the physics related to how topology manifest in the states and the transport and dynamics. Okay, so I will, in between, I promise, I will make a, short intermission, whatever, a digression into some of the, at least intellectually related aspect of spin helical electrons that demonstrate the power of these spin helical particles. I think that's one of the unifying thing of the spin-dependent quantum technology that is happening in multiple fronts in the center. And that I'm also fortunate enough to be involved in some of these. All right, so I should thank a lot of people for contributing to the work I'm going to show. But for the neutral atom part of the effort, the data mostly come from these individuals. Most of these have moved on to other places. I won't be able to name all of them, but also on the theoretical front, on the BC experiment, we benefit very much from the ideas of Qizhu, I guess it's out of town, it's QSCPI, but also Sabri, who is sitting here, and other people, colleagues here and elsewhere in a lot of ideas, exchange, and discussions. All right. Now, let me start with something very general. I think is the power of this kind of platform. Particularly is well demonstrated in the case of an atom with 2 levels, 3 levels, or n levels, let's say d levels. So when you have a particle with a small number of states, can be as few as 2, but in the particular case of atom we work with, which is the rubidium-87 atom, there's actually 8 states in the ground state that we can conveniently access. You can encode each of these levels as some kind of an index on the vector. So you can create, you'll see superposition states with coefficient in front, the wave function would be superposition of each of these, what I call generalized spin states. But more importantly, you can introduce coupling between these levels just by light. Here, at this moment, light, I mean very general, could be actually optical light, but could be RF or microwave. For this particular particle, the energy, frequency of it's typically RF between some states or microwave between some others. And when you turn on these coupling fields, you basically are turning on some kind of off-diagonal elements. Linking, for example, you couple from state 1 to state 2, you're putting some entry here in this matrix. Okay, from 2 to 5, maybe a different microwave field, you connect here. So you can filling up this matrix with these coupling constant, which is a complex number, by the way, fundamentally, depending on amplitude and phase of that electromagnetic field you're turning on. But you can build up matrix. You can simulate a up to 8 by 8 matrix. I can realize it. If you have enough these RF optic fields, you can basically design any type of Hermitian, that has to be Hermitian, at least right now, matrix. It's pretty powerful. So if you talk to a subray, this is already a QDID. In this case, you have kind of 8-dimensional Hilbert space. But you can also think of this, can simulate the 3 qubits, 2 times 2 times 2 10 to the power 3. 2 to the 3 is 8. It's not scalable, for sure. Already, you have about, something like 8 times 7 or, 50 or 20-ish RF microwave you have to worry about if you want to completely, but it's possible to create this kind of matrix or arbitrary control. That may still can be done with, for example, the Gustavo's wonderful quick type of chip development Fermilab. But as this number goes up, it will be a very large number of fields. However, you can still use this kind of very interesting model system to test or learn, to illustrate some of the very interesting aspect of the control of these quantum systems. And even as simple as it is, it gives rise to fascinating phenomena that you can ask similar questions in other systems. Later, I will also mention, you can also turn on something called optical field or Raman coupling between two states. When you induce optical field, one thing, so for RF and momentum, for RF or microwave, the momentum aspect, wavelength so long is negligible. But for the optical field, at least for length scale we deal with for these atoms on the micron-ish length scale, there's a momentum kick you can introduce, right? Photons give you a momentum kick. You can actually couple spin with the momentum, so that's also very, very powerful. So later I'll illustrate that aspect. Okay. You don't have to deal with necessarily with the Raman coupling. If you have atoms, some atom like alkaline Earth, like June studies, have long-lived excited state. You can even with one laser beam you can introduce momentum transfer as well. But in our atom, we usually have a Raman coupling to introduce a momentum kick. Okay, but let's first say what we can do, even just with a pure microwave and RF coupling to engineer some small n by n matrix, okay? So before that, let me briefly show you, this is actual reality. Okay, so this is a summer school, so we're primarily aiming for graduate students, so tell me a bit more about my experience. So when I was about finishing my grad school, so I did my PhD in solid-state physics, 2D electron gas, quantum Hall effect, Wigner crystal, stuff. And I went to a March meeting. I heard this wonderful, wonderful, fascinating talk about how people use Feshbach resonance in atoms can control the interaction between repulsive attractive. That I really got hooked. And I say, why? Oh, I want to do a postdoc, learning about lasers more than just laser pointer, which was only laser I used in my PhD. So I did a postdoc in the cold atom physics, learning how to make a Bose-Einstein condensate. And since I came here to Purdue, thanks to a team of wonderful student postdoc, we built a apparatus, which was actually first BC apparatus on campus, but now there are several of these apparatus. So we're one of the coldest place in Indiana with a 100 nanokelvin, 50 Kelvin, whatever, cloud suspended in the room temperature vacuum chamber. It's been a wonderful kind of playground to learn about quantum physics, in addition to a lot of things we study, material side stuff. For example, one of the iconic experiments that kind of helped give birth to quantum physics is a Stern-Gerlach experiment. So this is a modern way, we take this kind of movie every day, literally, whenever this apparatus is on, you create these atoms or cloud atoms. So you basically do photography. You shine a laser beam, which will leave a shadow, and from that shadow, you can infer the density of the, typically we take these kind of images, these red part are dense part of the cloud. Under magnetic field gradient, you see them separate into different spin components, and they are, in this case, they're falling down under gravity. You can also see wonderful stuff. For example, I mentioned there are discrete levels. For rubidium, you can, for example, confine to the 3 lowest levels. You can use RF, simple RF to couple these, if I might. Then you can see so-called Rabi oscillation, coherent Rabi oscillation between these discrete spin states, okay? These are fairly standard. Of course, people see this many, many years ago for atoms. Seeing coherent Rabi oscillation is usually a milestone that you are dealing with some good coherent quantum system. In the solid-state system, that is usually one of the first major milestones. If you want to say, claim you develop solid-state qubit platform, whether it's a quantum dot or superconductor Josephson junction, you want to demonstrate some Rabi oscillation, right? Of course, they're very difficult in the more complicated solids. But here, of course, atom is clean, and these are well demonstrated and fairly easy to do. Here's another example. You can pulse on or shine some kind of a, if you have two laser beams with the same frequency interfere, they form standing waves, right? So it's some kind of optical grating. Then your both condensate can, or this also known as an atom-based matter wave, right, can diffract from these laser-based standing wave, almost like light diffract from a matter crystal from diffraction pattern. So this is a similar kind of diffraction pattern. So this means this coherent matter wave light crystal interaction is real. So this shows you can do this kind of stuff. Our apparatus, so we also has a feature which is, by the way, if I don't tell what it is, it also looks just like a lattice in some space. So you can treat these different momentum lattice points or even spin states as some kind of lattice in a fictitious space, so-called synthetic dimension. This is actually a powerful idea these days people utilize to engineer interesting or even high-dimensional topological state that may be difficult to realize in electronic materials. Finally, our apparatus has another component. So this apparatus can do many, many type of experiments. Another component is I already mentioned, it can do some chemistry. So we do a very simple kind of chemistry, the physicist kind of chemistry. Even simpler molecule than what Vivian showed, just two atoms. You shine a laser beam, slightly lower energy than the atomic resonance. It can actually glue two atoms to form a molecule. Rubidium-2 in this case, it's an electronic excited molecule. So you may, when I first heard this, I thought, well, laser usually burn or break things up. Why is glue atom into molecule? Because it's promoting into an excited kind of upper floor of the house, but bound there is a little bit of energy before it totally ionizes. So it's an excited molecule. It won't live for very long, so it will be lost from the trap. So all these are in some kind of trap. But from this loss at a certain well-defined detuning from many this example of these molecular resonance, you know you're making a molecule. So this is called photo association. Laser, it's kind of laser chemistry. Okay. So there's a lot of detailed atomic physics that my students probably have to worry about more frequently to build and maintain this kind of apparatus. But we kind of push those behind the carpet. Let's just say we have this machine that can control atoms in different spin state. By the way, having BEC is wonderful because you have this very dense coherent wave function. Basically, it's a wave packet you can image easily with the camera and just visualize the quantum mechanics dynamics. So this CODAPS is a machine you can slow down and blow up the quantum physics in the length scale and time scale that you can take this kind of image and movies to just look at them. So it took some effort to build this kind of apparatus. It's a little bit like building a dilution fridge. Dilution you can buy commercially, but usually these you have to put together in these individual mirrors and components. It's a standard thing these days, but still it's reasonable time consuming. Although companies like Code Quanta is a great effort to try to make this more available, accessible, kind of provide at least a good starting point components of this kind of apparatus these days. All right, so first example, I promised to give you an example of what can be done if you just can control those spin states. So one of the dream in chemistry, I know very little chemistry, but I think I heard this is to use a laser to control chemical reaction. So traditional approaches, actually it's wonderful to hear Travis, I was doing a lot of these kind of physical, chemistry, but there are two class approaches using laser to control chemistry. Selective breaking bonds, either you design some complicated pulse to steer the reaction or some interference between different colors to steer reaction. It's been going on for decades, a lot of impressive progress, although I think they're still very, very challenging. But it's a big field called coherent, some kind of a coherent control photochemistry. The approach that we demonstrate is different from this. We have a very simple photochemistry, one photon kind of a photo association, make a molecule. We work on the underlying reactants, atoms, by being able to control them in the spin quantum superposition state. We can control this chemistry. So long story short, Again, this is this is conceptual, okay? If you can put atom in the superposition state, something interesting happens. Fundamentally, this reaction is a two-body process, right? So you have to kind of product two of these wave functions, each is superposition. So you have a lot of these combination coefficients you need to worry about. But luckily, there are these reactions, we pick a certain reaction, which are spin sensitive, only react to possibility. So it only reacts two atoms with some kind of magnetic quantum number 0 and 0, or 1 and -1. Okay, so that simplifies things a lot. So there are two channels that you can react. And it turns out also this photo solution that we pick is acting on the total angular momentum. So there's a Clashford-Gordon coefficient you need to worry about. But in the end, what happens is there's for the experiment I'm going to show you, there is a destruct interference between these two different channels, different spin combination. And if you design the coefficient right, you can actually completely suppress that chemical reaction, even though it is allowed in either of these two possible spin combinations. In fact, one demonstration of the superposition is that if you make the statistical mixture of different spins, so it's not superposition, the reaction is kind of independent between different components. But you make a superposition, they all react together, have the same kind of a loss rate. More importantly, if you turn on this coupling parameter I mentioned, that off-diagonal matrix element in the right way to prepare the right coefficient, you can actually suppress this reaction completely, which is due to this destruct interference term, which you cannot account if you don't have this interference. So again, 2 is from the bosonic, so we're dealing with bosons here, two-body process, spin plus minus 1. The minus sign is from that destruct interference. So if you have the right coefficient, we can control with that off-diagonal matrix element, then your eigenstate, right, is a vector with the right coefficient. You can suppress the chemical reaction. People have also designed, for example, Sabri's team, other schemes. You can take advantage of other possible reaction. You can also get construct interference, and this is something we are actively working on in a slightly different project. And also, their approaches developed. This is a work by a former postdoc, still in QSC, but now at UCSB. Just by pulsing on some RF microwave, you can also introduce a time-dependent phase evolution, in this case due to slightly different energy shift of these three so-called Zeeman levels or three spin states. You can have a time-dependent destruction or construction interference of this chemical reaction rate that is being observed, still being studied to clarify some of these. So I think that's hopefully is a very simple example, demonstrate you can do interesting control, even you just control these few spin states. I actually lost track of time. Did we start on time or?
Yes, just about. You got about 10 minutes.
Okay, 10 minutes, that's good. All right. So there are other, another very powerful aspect. So this is actually a project led by Qi Zhu, our theoretical colleague, who has a lot of very interesting idea to say, if you can just microwave connect different spin states. So I said you can couple up to 8, so you can select small them. In this case, just need 4. Connected with a microwave and R fields. Remember, each of these coupling parameter has an amplitude phase, so it's actually a complex number. So you can realize a matrix in the high dimensional space, so it's kind of parameter space. And you can ask a question, are there eigenstate structures? So you realize a matrix I mentioned, right? Up to 8 by 8. This is just maybe smaller, but with these, depending on these parameters. You can solve for its eigenvalues. You can ask where are those in the place in those parameter space where you may have certain degenerate structure of the eigenvalues. For example, you want the two middle eigenvalues to be degenerate. You solve for that eigenvalue equation. You find this is in the more restricted part of the subspace or parameter space. It happens along a ring, for example. If you want another type of degenerate structure, upper 2 and lower 2, so this is 4x4 matrix, right? So 4 eigenvalues, pairwise degenerate, then it happens along a line through the origin. So this is actually very interesting. So the kind of the manifold you want, that where the eigenvalue degenerate actually have certain topological, some kind of topological defects. It could be as simple as a point also. And one of this project, Qi and my postdoc Chuan is doing now, also running actually experiments on this apparatus I showed you, is to explore. We know very, very little, actually. This is fascinating. There's connection between how to design Hamiltonian that has a right kind of topological, these defects, and then how would that topological defect affect these quantum dynamics, which you can suddenly change? That's another thing I mentioned is important, is these parameter quantum fields can all be time dependent. So you can suddenly turn on, turn off these coupling and perform so-called quantum quench experiments. By watching these more generalized Rabi oscillation, you can actually infer these eigenvalue and their structure and connect to these topological effects. So this is, we're just starting to kind of test some of these ideas, and it's very, very interesting to see this connection. Okay, so now I give you maybe a quick example, things you can start to do with when you connect to the momentum. And here, in our case, we use a pair of Raman laser to couple the atoms that would introduce a momentum kick. So of course, for people doing Raman on materials, this may be a bit strange, but the material Raman spectroscopy is an incoherent process. Yeah, you like laser come, lose some energy time, collect excitation, and get you measure shifted another outgoing photon with shift energy. But the kind of Raman coupling, of course, in here we deal with is a coherent Raman coupling. You already shine this pair of the light, so you turn on these coupling on these off diagonal. In this case, I'm just using a 2x2 to focus on two states, right? So if they are counter-propagating, the atoms can swap one photon, get a momentum kick, and stimulate emit also in the opposite direction, get another momentum kick. So this coupling is actually connecting atoms whose momentum are differ by 2 units of so-called recoil. So you can rewrite the previous matrix into this form. You notice I have absorbed that phase factor in the light, rewrite this is mathematical equivalent into actually the momentum in the recoil momentum atom. So basically, you're coupling these two free particle parabola. Once you turn on this Raman coupling field, you are turning on basically avoid crossing, open the gap. So this is very much like a fictitious magnetic field in the transverse direction. You see this kind of a Hamiltonian matrix in the basically same way in Rashba, quantum wire in the transverse field, which is a platform for topological states in electrons. So same mathematical structure. The eigenstates now are superposition of the bare spin up, spin down, if I label these by up, down, with states with some momentum shift by the recoil momentum. And this coefficient can be controlled by this coupling light field you turn on, and also where you are in this so-called quasi-momentum space. So as simple as this, it can allow you to do a number of very interesting things. This can also be generalized to more complicated 3x3, 4x4, as I said, up to n by n. So now you also see this, you open something this in this so-called ground band, or actually any of these bands, which is basically the momentum-dependent energy eigenstates, has this interesting spin momentum locking. If you go to the opposite momentum, the dominant spin component is opposite. Okay, so this is what I mean, start to look like spin helical particle that I mentioned at the beginning. I won't have time to go through this a digression of spin helical particle. Of course, this has a beautiful origin in the higher physics, but I don't know much, but neutrino is one of the prime example. People talk about helicity locked to the momentum. But in the more relevant example, in solid state physics, in electrons connect to the project in the Quantum Science Center, are the electrons whose spin are locked tangentially to the momentum. For example, you have a Fermi surface electron with the fermions, where if you know the momentum, you know the spin, and you don't have the other spin state. So these are spin helical electrons. You can create this kind of spin helical electrons either by the trick I just said, turning on some kind of transverse field, or in the topological insulator surface, you kind of get this for free. So these are two common approaches to get these kind of spin helical electrons. Both of these are, if you put superconductor into these spin helical electrons, you can engineer what's called a topological superconductor, which people also hypothesize to be very important for the reasons. So these spin helical electrons not only are interesting for those, they are interesting for spintronics. You flow current, you get a spin polarization, which you can detect by magnets. You can generate even possibly nuclear spin polarization, which long-lived, reflect this spin protection because you flip spin requires fluid momentum, which is more expensive, stuff like this. So it actually can already have some benefit in spintronics and possibly even related to nuclear spins. One of the reason people are so interested in these spin helical electrons is what I just alluded to. If you couple two superconductors, remember the superconductivity is some kind of singly pairing between opposite spin, but also with the opposite momentum. If you have a spin helical electrons, you're missing the other possible pair, it's difficult. But nature says you can mix in what's known as a triplet channel, and theorists told us the vortex or defect in this kind of a triplet, P-wave type of channel is contains some kind of a zero mode we call Majorana bond state, or, which is hypothesized to be a non-abelian anion. And still need to be demonstrated, of course, but this is one reason this is such an interesting field. A lot of efforts, people trying to pursue this, including in Quantum Science Center. Travis showed this image of the coupling superconductors, control these localized vortices, try to manipulate these states. But all of this based on the foundation of you have a spin helical electrons to start with. Okay, so there's a lot of interesting things you can do with these spin helical electrons. All right. Okay, so let me skip this. So if you have these spin helical atoms, one of the interesting thing I showed you have the band structure you can deal with, and how do you do transport, right? So I said you can do transport. So here there's no electric field or current you can run, but you can utilize a force. One of the natural force you can realize is just the gravity. So if you let the atoms can release the trapping potential a little bit, that move under gravity, it can kind of travel through this band structure. And when you stop at a given time, release them from this trap, you can actually perform these spin momentum resolve imaging to get this, project each of these eigenstate at different these momentum into this spin component. So this is a little bit like doing, so skip some of these details, but you can engineer these band structure doing this kind of spin momentum imaging. It's a little bit analog of the spin resolve RPES, which is of course happening also in Quantum Science Center for the electron materials. Here you have a wave packet, this BEC, traveling around the band. You can just image what is the spin texture of this band, have some kind of similar analog with this kind of spin, using transport to do this quote band mapping, okay, which is interesting when you deal with the BEC. You can just follow these wave packets as they move. So the final, very brief, maybe 1 or 2 minutes, when you have these multiple spin states, you can connect with a light field. In a round trip, I mentioned that you can generate a bunch of these discrete momentum spots, which actually generate a real space periodicity. A truly periodic band structure actually emerges with a very interesting topological feature, which you can study by, again, doing this kind of transport. And one of the reasons these topological, there's protect crossing these bands is because in this, now we're talking about the 4x4 matrix in this example. These coupling fields has a underlying symmetry, so-called non-symmorphic symmetry. In a very simple case, you shift this by half the period, it gets a minus sign, but you can remove that by some discrete manipulation. And this non-symmorphic symmetry often can protect certain topological feature. In this case, it protects this band crossing. This kind of non-symmorphic symmetry protect the band crossing or topological semi-metal is also important in the actual materials. But this is, again, a boson moving in this band structure. And you can follow these topological crossing in the band structure, again, by doing this kind of transport experiment imaging. By follow through each band, you see so-called block oscillation. So the image of the atom, this kind of spin mapping, repeats itself certain period, which is already kind of very interesting. So you didn't apply any crystal at it to start with, but now atoms behaving like a coherent motion in the periodic system have this block oscillation with some right half period offset from these two bands, and this structure, this dynamics, shows you have these topological crossing. And what's interesting, won't go into detail, is you can manipulate so it's a bit like a walking momentum is kind of Mobius strip. You need twice the period to go back to the same point. You can manipulate these coupling to actually engineer this topology. You can add the coupling like RF to open the band gap, which kills this crossing and recover more conventional block oscillation, untwisted Mobius strip. You can remove a coupling to completely kind of cut open this kind of what we call a synthetic Hall cylinder into a more flat thing. Then you don't have any periodic structure. You have no block oscillation at all. What's interesting, by multiple of those phases, you can control what's called almost like a fictitious magnetic field, which controls the magnetic band gap, which you can measure by following these spin-dependent transport. So this is a bit like magnetoresistance. Here, this fictitious magnetic field is controlled by the phase you apply. So all of these is a very wide range of degree of control, because almost every term in this, even just very simple 4x4 Hamiltonian, but once you couple the momentum, it generates a very interesting band structure with the features in topology you can control by just changing these coupling terms. So, and that has interesting also connection with some of these cylinder of electrons in topological insulator. That's study center, but I won't go into these. This is open interesting question of the quantum dynamics even in some of these curved space. So I'll just close to say these spin helical particles, once you can control coherently around these different spin momentum states, along with just spin state itself, give you a very interesting platform. You can test ideas or develop asking interesting questions ranging from quantum chemistry to quantum simulation of the, say, topological states of systems. And there's, I think, there's many new questions you can ask in different contexts. Many of them may not make sense, but it's interesting asking questions. Occasionally, it may generate new techniques to do things in a different scenario. So thank you.
All right, do we have any questions for our speaker? I have a couple questions. So going back a few slides, there was you were graphing the quench time dynamics, and the experiment and the theory didn't really look like they matched up very well. Why was that?
There are many reasons. So that's actually healthy. If they match perfectly, you will be worried. The real experiment, you're dealing with many non-ideal factors. That's usually not taken in this theory. So they are inhomogeneities of fields, right? They are noise in the laser. They are finite extent of the atoms. There are many of these issues that are not usually taken account in the simple theory. That's usually what we do.
Thank you. All right, let's thank our speaker one more time.
Thank you.
Next, I believe we have a Quera training. If you haven't looked at your email yet in the past few hours, go check. I believe there's an email from Morris instructing you to install some packages for this training before we get started. Raise your hand if you need a handout.
Yes, and I need an adapter just because you see. Sorry, you can see those.
So if you want to put this up on the screen, what we need you to do is, in fact, you don't need the
Just go
adapter.
to
Go to
Zoom?
Zoom, yeah. And what we'll do is, here, I'll get you the information for this. Yes. And so it's right here.
Raise your hand again if you need
Yeah, and I'll go ahead and
the
let you
materials.
6051. Thank you very much. Nine 770 26.
Already?
I'm doing well. How are you?
Good, how are you?
Not too bad. I'm gonna admit myself because I haven't used a mouse in forever.
You about ready?
Sorry, you ready? I guess I just need my. See if I got this right.
All right. This morning, we've got Pedro Lopez joining us from Quera. Pedro is a business developer at Quera Computing Incorporated. With a PhD in theoretical physics, his research career through Brazil, the USA, and Canada explored topics in quantum matter and topological physics. He's passionate about communicating quantum computing at all levels and helping customers and developers understand ideal entry points into this technology. Please join me in welcoming Pedro.
Oh, I guess I can hear myself, so probably this is all right. Thanks very much, everybody, for coming. I think that looking at the program so far today, we got a very, very good segue. Talk a lot of rubidium, talk a lot of simulation, and about also Quera joining QSC. So either by design or by luck, we got a very, very coherent approach today. I want to just make a quick announcement here. We will be emitting certificates for everybody that participates on the 2 days of training today. So today and tomorrow. So I'm going to pass this list around. If you're interested on a certificate for, pretty much it's intro to Quera systems, just put your name, put your email, check your first day. Tomorrow, check your second day. If you check both, you got it, okay? We'll send it later by email. So I will just pass this around, and yeah. So, very well. As I was saying, this is a very exciting moment for us because we are joining efforts with QSC. We do already have some very interesting collaborations, for example, with Arnab over there, and things are heating up, I would say. There is plenty of opportunities for future work. And I think that the whole idea for these 2 events is to really onboard you with our systems and onboard you with the concepts that are necessary for you to develop your own applications or your own quantum simulations in the Quera system. So this, despite being a tutorial session, it's really going to go through, it's not like a talk, so we are going to have activities together, and but it does go through a lot of concepts because when talking about quantum computing, we are not operating our machines just like you would be expecting, like a gate-based machine, et cetera, et cetera. So there's a few layers of, both understanding and familiarity that we need to get you into. So for the sake of me and coordinating logistics, how many of you succeeded at installing the things that the notebooks, etc.? So we have 1 here, we have 2 there, we have 3, 4, we have few, 5, we have few. Can I get at least 1 person that has everything installed per row? So lift your hand again. So 1 here. So 1 there. Can you go to the middle of the row? Here you're more or less in the middle. Any more? Someone in the back. I saw a lifted hand in the back there. Okay, we are good over there. Because I wanted everybody to join as close as possible because you will be working together. And I really want to see you play with this, or I'm hoping that you will play with this. It's going to make it more fun for all of us. So please sit closer if you may, as much as 1 dimension allows. So very well, while you organize, I'm going to simply get started because time is short and content is plenty. So why you want to do Quera? I think that's the main question that we should start with. Like, why is this interesting? What are we talking about? So our quantum computers, they're based on neutral atom technologies. You may have listened to Misha, one of our co-founders, talk about this 2 days ago. And this is the newest entrant on this race of technologies for quantum computing. So this is new, novel, shiny. It still smells like a recently bought car. It's like it's really like it's cool, right? So we got a lot of atoms that we can put in a single processor. Okay, so these processors, they really come. Our first machine here that's available on Amazon, it can operate up to 256 qubits, coherence through the system, everything that you want. Because these atoms, they are neutral, they are not ions, I can pack them together. They don't complain, right? There's no repulsion. So that's why we can get such larger systems together. We can operate in 2 dimensions and more, amusingly. So this is very cool. The control is very efficient. We have very few control lines per qubit channels, and this means that scaling is also very much at reach. And what's going to be the most fun part of this is the freedom that you have for problem encoding. Okay, so we are not doing gates today, but we are doing things that no other company is allowing, no other technology is allowing out there, which is for you to define your processor according to your needs. Okay, so if today you want to use your processor, your qubits, place them in a square lattice, you place them in a square lattice. If you go to sleep, you wake up, got amnesia, and today you want to do a triangular lattice, no problem. You choose. You can choose every second what's your processor is supposed to look like. And that really gives you some great freedom for problem encoding. So we are very excited because this really gives you new ways to think about quantum computing. Okay, so but the downside, or maybe it's an upside, there's a barrier over there that we have to overcome together so that we are all ready with the tools necessary to do quantum computing. So I'm gonna take a full approach, like full classroom approach. We are gonna talk about our learning objectives of today. And by the end of this workshop today, you'll be able to explain how neutral atoms can be used as a platform for quantum computing. Maybe not many of you know how to operate on, or why, or how this thing happens. By now, most of you might have heard of, Josephson junctions and ions, but maybe you have not heard how we do this with neutral atoms. So I do think that it is important for you to understand the platform before you play with the platform. So it makes things more concrete. We're going to distinguish what we call analog and digital quantum computing. Digital is what you know as gate-based quantum computing. Analog is what our machines are operating today. So having a clear distinction of what are those 2 methods is very important. We are going to define this concept of field programmable qubit arrays. Do many of you know of field programmable gate arrays, FPGAs? Right, so it's like these circuits where you can reprogram the connectivity of your transistors, of your calculation elements to make application-specific circuits that are very efficient for very specific applications, even if they're not going to do everything. So FPGAs, what we have is a quantum analog of an FPGA, it's an FPQA, and it has some advantages, and we will talk about them. And we are going to really go through the programming range of our first machine. The name is Aquila. We are going to talk about what are the Hamiltonian parameters and what are the limitations, how to control them. Tomorrow we are going to go through applications. Okay, so today I just want to make sure we cover the basics. Okay, so very well. Questions so far? Anything we're missing that you would like to see? Okay, not surprising. It's still abstract. So how do we do qubits? First of all, it's the basic element, we need to talk about that. And for us, we go back to the talk that we just saw. We are using rubidium atoms, rubidium-87 just as well, with the distinction that we are not doing clouds here. It's these atoms, they come individually. Okay, so 1 atom of rubidium. If you don't remember the periodic table, I will give you a fresh reminder. Rubidium is down there to the left. It's really the first column. And if it's the first column, all that you need to know is that it's like hydrogen. Okay, it's a heavy hydrogen, that's all. It has 1 valence electron, okay, that you can play with. And we are going to encode today these qubits between 2 states. The ground state, which is a 5s, and another state that is highly excited, highly excited. Those highly excited states we call Rydberg states. The principal quantum number of this Rydberg state that we use today is 70, okay, 70. It's not ionized, but it's huge. Okay, so when you do that, what happens is that your atom, the characteristic distances for the physics of your atom go from angstrom size to micrometer size. Okay, so I think that the fluctuations go with n to the power 3, so or n squared. Really, you're puffing up your atom. Well, when you puff up your atom, the effective volume that it has is much larger. Polarizability goes with the volume of your particle, of your neutral particle, so it gets highly polarizable, and when it gets highly polarizable, it can interact with other particles. So when it's tiny in the ground state, it sees no one. When it's large, puffed, it sees entities, other bodies around it, including other atoms. So that's how we are going to create qubits today. If you're curious about why I keep saying today, I'll tell you later what we're going to do tomorrow. Not tomorrow, but the abstract tomorrow, the future, the vision. But this is how our qubits are operated in the machines today. Very well. What's the routine for operating this machine? I think that this is not something that you can see in our documentation everywhere, etc. But it really gives you a feeling for what's happening every time you submit a job to our machine. So we have a parallel operation of a QPU and a CPU, right? So the quantum computer has to be controlled by a CPU. And it goes as follows, okay? So you decide what you want, you send a job to the machine. The first thing that's going to happen is that we're going to have this glass cell. It's going to capture a little gas of rubidium into something smaller. It's going to pre-cool it. And this operates a magneto-optical trap. Okay, so there's some magnets, some coils, and then some lasers. This traps this cloud and stops it a little bit so that we can actually play with it. That takes a few tens of milliseconds. Then what's going to happen is we are going to load something that we call tweezers. So these atoms, how do we get from a cloud to a processor of individual atoms is using something that we call laser tweezers. So we get these lasers, we compress them in space to the micrometer size of our atoms. And it's very amazing. So sometimes nature is against us for doing quantum computing. This time, nature is in our favor. So if you make these lasers tight enough, either you have 0 atoms or you have 1 atom. You cannot have 2, you cannot have 3. It's 0 or 1. And this is super helpful, because otherwise, how would I guarantee that I'm holding 1 qubit at a time? Okay? But maybe the atoms are not going to load in the place that you want them to load. Okay, so this loading is stochastic. Okay. And then we need to actually create a processor, right? So if you look at some machines, you'll see that they are in brick wall geometries or octagons. We can do all of those, but with a stochastic loading, you will not necessarily get that. So what we do is we image to see where the atoms are, and then we send the command back to the classical computer. There's going to create a pattern that's going to make these atoms move now and position them into the position that you actually want them to be. Okay, so in this case, what happened? I loaded just a complicated rectangular lattice over there, but what I wanted was my atoms to be forming these 3x3 small shapes. On the left, you don't see them, but then I take an image, see where my atoms are, go back to my classical computer, the computer says, oh, I need to move atom 1 to position blah, and until it positions everybody, sends the command back to the QPU, and boom, I move my atoms and position them. I create my pristine 99.9 fidelity of loading these lattices or not lattices or these structures in the way that you want.
So how do you know you have only 1 atom?
Again, so it's just a fluorescence. I take a picture. If I see nothing, there's no atom. If I see something, the atom's there.
If you see something, why only 1 atom?
It's only 1 atom because if I had 2, they collide and both of them fly away. So each laser spot is capable of holding 1 atom only, not more than 1, which is, again, very, very convenient. So then what do we do? At some point, we have to do quantum calculation. This is where we do it. Okay, so this is some Rabi oscillation. You can see that these things, they oscillate a lot. We actually can have about 18 Rabi oscillations in our coherence time today, 16-ish. And this means that if you try to convert this into bit flips for like something analog to a T2, this means that we would be operating 32 to 35 gates in depth for these guys inside of the coherence length. Sorry, question?
When you load the traps, are they already in the Rydberg state, or does the fluorescent
Ground. No, they shine in the ground. Okay. Yeah, this is a little bit complicated. The natural 0 is the ground, the natural 1 is the Rydberg, but it shines on the ground and it doesn't shine on the Rydberg, which means that our machine actually flips what is a 0 and a 1. So that's a little, yeah, but yeah, that's it. So you do the calculation, and tada, you find some pattern that, whatever it was, the pattern that you were trying to create. We will look at some examples of what that can be. Okay, the bottom line of this story is what? It's that over this whole period, quantum computing is just a tiny part. Okay, so the time scales for this is that you can run one cycle like this pretty much 3 per second. Okay, so that's the speed of this today. Of course, that we have 256 atoms or less. You can choose how many atoms you want in your processor. Which means that our output of information is actually very, very large, even if the machine is low on the clock. Any more questions on this? This is important. Above everything, pay attention to the sorting thing, because sorting means starting from a general pattern and arriving at the pattern that you want. It's a very important concept, and we are going to get back to this with some questions soon. So what does it look like? Unfortunately, I don't have a picture that looks like a shiny chandelier or anything. If you are very good at art and want to figure out how to illustrate this in a beautiful way, I'll be very happy to hear your ideas. This is the best I could get so far. Our processors, they're going to look like a 2D system of qubits. Okay? Here they're positioned as a honeycomb lattice. They don't need to. There's going to be lasers that come from above, right? So transversal to the plane, which hold the atoms in place. And this green light that you're seeing here is to represent a laser that shines in the plane. Okay, this is the laser that excites my atoms from ground to Rydberg. You can see that this guy shines over everyone at the same time, which means that all qubits are under a single control channel here for excitation. Okay, so this is more or less what it looks like. We're going to go in detail. So 2 things that you need to know to program our machines. Thing number 1, you need to know the geometry that you want, and you need to know what are the geometries that are allowed. Of course, not everything is possible. That would be beautiful, but this is a real physical system. So there is errors, there is limitations, and we will go through them. Second thing that you need to know how to program our machines is what is allowed for the dynamics. That pretty much means what is the algorithm. Okay, what are the algorithms that you can encode. So let's go through that. We're going to start with geometry. So let's start with this idea here. I'm going to have, let's say, 9 atoms. I'm going to distribute them in space in some way. And behind the click to join audio comment tag over there, you would see that yeah, you can do that. the error in positioning for these atoms is of order 0.1 microns. Okay, so if you're curious about, if my atoms are misplaced a little bit, what's going on? So the error here is 0.1 microns. Actually, that error is very low, and I'll be happy to talk about why and how the type of interactions that we have, they pretty much wash this error away for most applications. This is going to require some concepts from tomorrow. What else? Minimal distance between these 2 atoms in a real system, 4 microns. These atoms, they live in a play field. Okay, so you have some space to position them. On the x direction, this play field has 75 microns. On the y direction, it has 76 microns. It's not, yeah, there's some aspect ratio over there. And the next important thing is that these atoms in the y direction, they have to be positioned in rows. Okay, so the user can only access rows. And the minimal distance between those rows is also 4 microns. So I have here maybe 4 different geometric constraints. So constraint number 1, let's see. You can take note. Constraint number 1 is minimal distance is 4 microns. Constraint number 2, let's put those two together, is that there is a play field that is 75 by 76 microns. And constraint number 3 and 4, let's say, the atoms come in rows, and the minimal distance between these rows is 4 microns as well. And I will have a challenge for you now, or an activity, which I'm gonna time. I wanna do some kind of think, pair, share type of thing. We don't need to literally pair, but I would like to give you 1 minute, counted 1 minute, because we have not so many minutes, to think about the origin of these constraints. What you can imagine are the origin of these constraints. And then a couple more minutes for you to talk to your neighbors about exactly what you thought. And maybe we will share back with the class, and maybe I will give you my hints or my understanding for where this comes from. So I will be silent for a minute, and feel free to ask questions as well.
Are all these atoms excited to the Rydberg state, or?
Everybody's in the ground here.
Oh,
yeah,
everybody's
it's just
in
the
ground.
position, really, yeah. Can we start coming back here? Slowly, slowly, slowly. We are back. So, can I get some feelings of ideas where these constraints might be coming from? The Rydberg blockade distance. The Rydberg blockade distance matters, but I would say that at least as far as I can tell, these are more hardware constraints, really. They're not necessarily the physics. But for sure, there's one thing that the Rydberg blockade matters here, which is the scale. Okay, so it's very important to know the scale, right? These are micrometer scales. And it is related to the characteristic blockade distance, etc.
Does it have to do with your SLM, like, settings?
Okay, we got pros here. So yes, it is related to the SLMs. So what is an SLM? An SLM is a spatial light modulator. What does it do? It modulates light in space. So it is a special mirror that is an active optical element where you shine the light with, let's say, like a Gaussian profile, and it diffracts back into some pattern, right? And that pattern, this mirror it's a liquid crystal, so you can program it via just electrostatics and change the different patterns of diffraction that you get back. So roughly, it's the secret sauce. It's not secret and it's not sauce, but it's what allows us to create processors that look like whatever the user wants. And surely there is some limitations there. Absolutely, yes. A couple more comments, if I can ask a couple more.
So are like the van der Waals interactions between the electron clouds like not significant at that scale? Like do they kick in at smaller scales?
So I think that this is related to the other questions that points that were raised. This is really, even for the atoms that at the ground state, in the ground state they do not interact. Really, because they don't polarize, right? Remember that polarization is function of the volume or the apparent volume of the atom. In the ground state, too tiny.
Is there like a limitation on how big you can make the 2D arrays in general?
Well, I guess that here we have this space that is 75 by 76. So there is a limitation, but I think that
like can maybe like arbitrarily big, like is there ever like a limit you hit with like, I don't know, I'm not a huge, like I don't know really anything about the system, but like at a certain point, like you get some sort of thing with your light field where it just can't scale up farther and you need a separate array that you need to like then connect them?
So there definitely are limitations to the size of the arrays that we can make. And here, actually, even though we are providing the user with 256 atoms, actually what we are trapping is more like 500 of them, okay? Because exactly of that 50%, 60% loading probability in the beginning, there's always some extra atoms. And this starts to give you hints as to, for example, why these atoms can have to be positioned in rows in the y direction. I guess we have one more comment here, let's see.
What's the imaging resolution of
the imaging resolution? What do you mean by imaging resolution?
the numerical aperture of the optical?
The numerical aperture. Yeah, it's actually much bigger than this. I think that we can fit up to, that's what I hear, we can fit up to 10,000 atoms in the numerical aperture. Okay, so this is much below that. I'll give a few comments, a few extra comments of this, just for the sake of getting you more familiarized. But many of these are highly non-trivial. Okay, so don't feel bad. I was not expecting them to miraculously appear, but I wanted you to just give some thought. So the distance between the atoms is really, to some extent, again, it is related to the excitation. If we put these atoms too close together and I excite them, energy levels are going to mix too much, and the approximations for the system that we want to simulate are not going to apply so very well. But above everything, if we put lasers too close together, we start having problem of resolution between the two laser beams, right? And so if we bring the atoms together and try to split them apart, there's a risk they will collide, etc. So of course, there's going to be a limitation in the distance, in the minimal distance, okay, that these lasers can come. Another interesting point is why they come in rows. And this thing of rows it really comes from the sorting of the lattices that we have. So technically, the user has the 75 by 76 space. We have a reservoir of extra atoms on the side. We load this thing up to 50–60%, right? And now we have to bring these atoms from these extra reservoirs into the space of the user that the user wants to use. Now, if I bring one atom at a time, odds are that I'm not going to get to 256 before something flies away, right? So, so if you see other groups doing smaller system sizes, frequently it's their sorting algorithm that is going to do this one at a time. For us, we actually bring these atoms together. Okay, so we align them by rows and boom, and we align them in parallel, several line by line. And that's why these things, they come in lines. It's to keep our system efficient in sorting and allowing you to make larger chips, right, larger processors. This 75 by 76, this anisotropy, anyone has a guess why there is an anisotropy there? And this is, it's a guess, really. Sorry? Lattice area. Not quite. If you see something that is 75 in one direction and 76 by the other direction, which direction would you favor when creating your lattice? 76, right? Yeah, and that's it. Okay, so if you're ever putting together linear chains, favor the y direction. That's what we are trying to tell you. And the reason for that is that to shine that green light that we were seeing in the previous slide, okay, so these laser beams, again, the focus of each laser beam there is on the micron scale. Here you're having something that shines over everybody in a 70, right, micron scale. So this type of laser profile that it's not going to be, if I want the lasers, the atoms on the bottom to see the same intensity of laser as the ones on the top, I cannot have a Gaussian profile for this. It's not going to work. So we have to create something that we call a top hat. A top hat is like the British top hat, right? And it's flat, and then it falls down again. And when we engineer those top hats, of course, there's some fluctuations. And depending if the laser comes from below or from the side, the atoms are going to see inside the fluctuations or deep in the direction of the fluctuations. So it's going to be more uniform for you. So whenever you're doing 1D systems, favor the y direction. Okay, that's what we are trying to say. But subtleties apart, just remember, don't put your atoms less than 4 microns apart. The system is going to scream. And whenever you're planning for your geometries, remember that you want to align things in rows. Okay, these are the two most important points. And we have a system of programming, an SDK, it's called Blockade, that works both as an SDK for Aquila, so whatever you program in Blockade, you can submit jobs to Amazon, but it also works as a very efficient simulator of these devices. And I want you to learn a little bit of how it operates so that we can go through it and so that you can play with it later. So I'm going to interweave a next activity still on the topic of geometry. Let me just keep an eye on time so that we can learn how to operate this. Now, so Blockade is written in Julia, don't be scared. But Blockade is very packaged for you so that things are easy, okay? To program one of our devices, this notebook, you have it, and it's self-contained. We're not going to go through it, but there's 5 steps to program our machines. And step number 1 is to define the geometry of your processor. When thinking about coding a quantum computer, this is the only step that you don't already know. If you use Qiskit, if you use Penny Lane, if you use Circ or whatever else, everything else is the same. You're going to have to define your algorithm. For us, it's going to be through a Hamiltonian, but it's the same as for everyone. Okay, so you define the algorithm, you measure, you initialize the qubits, you compute the circuit, and you measure the results. Everything there is the same. But the first step is geometry. So I want to give you a little hint of what are the functions that we have here that help you doing that. So I'm literally going to go through this with you. And again, we don't have many people with Blockade installed right now. If you're very curious about it, I do recommend you that you sit closer together. I guess you got one here. I guess you guys got one there. I guess you got one over there. And over there, I think that there was one more. So get closer, and but in any case, I will do this here live for you. So to define your circuit or your processor geometry, you start with this object called an atom list. Atom list. I'm not good with that word. Atom list, where all that you have to do is to provide tuples, right? So this is one atom at 0, 0. This is an atom at x equals 0, y equals 5 micrometers. Okay, so to use Blockade, you have to know physics, okay? Things come with scale because this is a real system. Okay, but other than that, all that you have to do is to create your array of tuples, and you feed it into atom list, define a variable for that. In this case, I'm calling it atom coordinates, and you run it, and you're gonna have something that Blockade eats and can operate, feed Hamiltonian, etc., etc. Not too complicated. If by any reason, like if by any chance, a piano falls on your head, you forget what you did, what you put inside your variable, call your variable .atoms is going to tell you what it is that you put inside it. Okay? But more interesting than that, if you simply call the variable that you defined here, atom coordinates, Blockade is nice enough to give you a geometric, a visual representation of what is it that you did, and it's going to let you look at it and say, oh, no, this is not what I wanted. Okay? So Blockade is here to help. I do have... I think we passed around a little handout that maybe, given the few teams with Blockade installed, maybe it's not going to be so relevant. But we have a handout with MIS activity. Can I just hold this for a moment? This thing. So I would recommend you to try and actually try to encode this on Blockade. So I put a little lattice behind. Your choice of what is the scale. This can be 1 micron, this can be 4 microns, this can be 10 microns, your pick. Blockade does not suffer from the same restrictions that Aquila does. So Blockade can do more, of course, but then if you ever want to submit from Blockade to Aquila, Aquila is going to scream if you did something wrong. Okay, so, yeah, I would hope that, you guys try to just define an atom list with these atoms in place. And I think that it may not be relevant to spend a minute for the whole classroom going through this, just because not everybody has it installed. But if you have it in front of you, please play and call me, and we will stop and we will look at it in a moment again. I can, at worst case, simply show my solution. So, continuing, what do we have? What we have is a serious situation, yes?
So between 2 and 3, you have only 3 micron gap. Between 2 and 3 in your atom list, you have only 3 micron gap. Is that?
Between 2 and 3, where are you seeing that? This one here?
Yeah.
Yeah.
You said minimum gap, minimum distance should be 4 micron.
And it is true, but I'm not submitting this to Aquila. If I were, Aquila would scream. Absolutely. Okay, and Blockade comes with functions to rescale, actually. So if you define a lattice in a way that is not what you wanted, but it's just convenient for you, just because like you go in units of 1, not in units of 4, and that's easier to compute, then Blockade has a function for scale. You just multiply that lattice by the scale, and poof, it's going to go in the distance that you want. So again, it's Julia, but we are packaging everything to make it easy for you. And it has to be Julia, okay? Because this is really for efficient calculations. This is to operate in HPC centers. Like this is the tool if you want to compare and have like large solutions or large simulations to compare with your experiments. Yes, next question.
My outline is
Yeah, it's a Julia version thing. I need to update that. I think that it's a Julia 1.7 or 1.8. I'm probably running 1.7, so maybe you're one version ahead. This was called. I heard that one. Yeah, the upside down is the newest Julia version. I have no clue why that flipped. So the next point that I want to raise here is that many of you are physicists in this room, if not most of you. And physicists tend to want to study periodic structures. It is the nature of life, or it's the life of nature. And you really don't want to be creating our own functions to generate periodic structures. So we put together an extra set of helping functions here that's called generate sites, from which you can actually generate lattices, okay, with periodicity. And we have a series of pre-programmed 2D lattices. So Chen means 1D. We have square lattices, we have honeycomb lattices, triangular lattices, lib lattices, kagome. So pretty much everything that you can imagine that could be interesting to create a lattice in 2D, we got this, we got you covered. Okay, so you just call a square lattice, and you say how many unit cells you want in each direction. In this case, it's 4x4. You tell what's the scale for the lattice constant, and voila. Okay, you get your square lattice, and we can get here, just to show that I'm not lying. If you never saw a lib lattice, you will see one now. This is a lib lattice. Okay, so it's just it's a square lattice with 2 atoms in the 2 extra sites on the bases, and then it repeats. Okay. In some sense, it's the square version of our square heir to the kagome lattice that is doing the same, but for the triangular lattice, right? So you have the hexagons and the triangles, not triangles, the stars, the David stars. Very well. Bottom line is, defining geometries is not complicated, and we got this for you. Good. Comments? So let's continue moving them then, because again, time is of the essence. So step number 1 of all of this is to define geometries. And we got this, we went through it, not too bad, just 1 or 2 lines of code, you can define what your processor is gonna look like. The next part is the hard part. It goes into the dynamics. And to go into the dynamics, I have to talk to you a little bit about our paradigm of information processing. So probably most of you are familiar with pictures that look like the picture here in the middle. Digital operation of a quantum computer. So you have gates, you have the set of universal gates, they're Hadamards, they have X gates, Y gates, rotations, and then you have your entangling gates, your CZs, etc., etc. And if you are very, very ambitious, you get your Toffoli gates, etc., etc. And that's what we call a digital mode of operation. But it's very important to remember that quantum mechanics, right? Time evolution in quantum mechanics is just a unitary evolution. So I would be very keen to substitute all those gates by a single unitary gate, okay, which covers all my atoms, cover all my qubits, and evolves this in time continuously until it gets to my answer. Okay? So when you learn quantum mechanics, that's what you're doing, not the middle one. Right? The middle one is just like we do what we can. Right, we do what we can. We want to operate in the Hilbert space universally. So we find out what are the set of universal gates. So we break these things down. But breaking things down leads to errors, gate errors. If you want to control each qubit individually, you're going to be in trouble, because if your engineering of your hardware doesn't go so nice, you end up with too many control lines per qubit, which means that when you add 10 qubits, you have way too many control lines. When you have 100 qubits, you cannot manage your control lines. So engineering something universal like this is actually very hard. So what we decided to do is to start from the other side, start from this analog operation mode, have one single unitary that operates through all my qubits, with the caveat that having one unitary that is universal, that is general, is going to be nearly impossible to create. Meaning, if you try to operate things from the left point of view, it's going to be very hard to get universal applicability. But that's fine, as long as your machine justifies itself, as long as your machine cannot be simulated easily, and as long as the set of unitaries that you can create is useful for someone, for some reason, you're good to go. So here we go. Our machine is operating in the analog processing mode. Okay, so what this means in the end of the day is that you're going to have to program Hamiltonians. You're not going to program qubits, you're not going to program gates, you're going to program Hamiltonians. So you need to know what's a Hamiltonian. Not too bad if you're a physicist, if you're a computer scientist, sometimes that takes a few extra lessons. But of course, we don't want to leave you, without any help. It is true that we don't have universal applicability, but we can do this idea of having a field programmable qubit array. So we leverage the fact that we can reposition our atoms to create processors that you, as a user, can define the connectivity. Okay, so even though we don't have all the universality, we have some extra tuning knobs that people so far have found quite invaluable. And that's where we go. So let's talk about algorithms then. Everything boils down to Schrödinger equation. Schrödinger equation is not too bad. It boils down to knowing a Hamiltonian. Okay, Hamiltonian controls time evolution. That's it. What is our Hamiltonian? It looks like this, and it's not too bad either. Okay, so starting from the left, omega. Omega is what we call the Rabi term. We're going to introduce some terminology. That's what we use in our everyday life. It's the Rabi term because that's what it does. It makes atoms oscillate between ground, Rydberg, Rydberg, ground. This is analog of X gates if we're just flipping once. Okay, it's the term in the Hamiltonian that would cause an X gate. Now, notice that omega does not depend on the site index I. Don't confuse it with the complex I. I will not apologize for that. I'm not going to call any of this J, except for when I need. And the reason why omega does not depend on the site index is exactly because it corresponds to this green light here. It shines over everybody. It's one light for everyone. Okay? This omega also this green light also controls the phase, phi, and these next terms here, the deltas. The deltas, we have a name as well. We call them detuning. They're detuning because of the way that we apply this. It's just a stark shift in the energy levels that detune them from resonance and end up giving you some cost energy. So whenever your atom is in the ground state, delta costs you nothing. Whenever you are in the Rydberg state, n equals 1, and you pay delta in energy. Okay? So omegas flips qubits, deltas, they give you a individual cost in energy, and you're left with the most important part, which is the interactions, Vij, Ni and J. So Ni and J is 0 if Ni or Nj are 0, so 0, 0, 0, 0, 1 is 0, 1, 0, 0, 1, 1 costs Vij. Okay, and Vij is a van der Waals interaction. Somebody called van der Waals there. We call van der Waals. It is a van der Waals interaction. It falls with 1 over R6. Okay? More on that tomorrow. For now, I just want to go through hardware constraints. If you want to program, what can you do? So, as a user, you will have access to omega, phi, and delta, the time dependence of all of them. Vij, you control by position. So you actually control all terms in the Hamiltonian. Okay? 3 of them time dependence, the last one is geometric. How do you define time dependencies? So for us, we're going to be doing piecewise linear functions. I'm doing some very lame ones here. Okay? The resolution that Aquila takes is actually much better than this. You can do fairly arbitrary functions. You can do things that look like sines. They're going to be, right? But they're going to look like sines, cosines, etc. But generally speaking, remember that the functions will be most well defined as piecewise linear. Same for the phase, except that we do piecewise constant. Details don't fully matter. The maximum value for omega is 2.5 megahertz, 2 pi megahertz. AMO physics problems, but 2.5 megahertz. And delta goes from minus 20 to plus 20 megahertz. Most important for you as well, for how long can you do a calculation? 4 microseconds. Okay, 4 microseconds is the largest amount of time that we're going to be allowing you to evolve your time system. And I'm going to go through this on Blockade with you as well, because I want to convince you to use Blockade, and doing it in Julia is already hard enough, but I will convince you because we really made this easy. So if you want to create a piecewise linear function on Blockade, all that you have to do is to call this object called piecewise linear. Okay. Defining piecewise linear functions is actually quite simple because it only requires you to tell where a piecewise segment starts and where it ends. So the clocks are going to tell you the positions where things are starting, and the values is the y direct, the y-axis. It's as simple as that. Okay, so you can see here we're starting at 0, 0, at 0, then at 0.2 we go to 1.5, so on and so forth. Okay. If you want to do something that is piecewise constant, same story. Instead of calling piecewise linear, you call piecewise constant. Simple as that. I have here a little exercise that we will not have time to go through because I see it's 11:09. But guess what? We come back tomorrow, so this is homework, right? And if you're thinking, do you think Pedro really expects you to do? Yeah, Pedro expects you to go through this. Like you want a certificate, you gotta earn it, okay? So earn it. And this is actually a very easy in the sense of it's not gonna require you to code very much. So get with your friends. The idea here is I'm putting you a few examples, and they're all from Blockade's page. So if you wanna cheat, you can go to Blockade's page and figure out where they come from. But the idea is just for you to think of, okay, I have this omega that is becoming flat, coming down, delta is ramping up. What is this an algorithm for? Right? What kind of algorithm is this? What could I be doing, could a person be doing with this algorithm? And all that I would like you to do is to think a little bit about that. What kind of algorithm is this? I have a few different ones. These ones, they have some kinky features here, and they jump. It's kind of interesting. And some of them are actually messy. So do talk about it, and do talk about it with me as well. I'm here to exactly so that we can interact. So make sure that, many of other times I did this tutorial, we were doing it online. People did not have access to me from one day to the next. So you do. So I'm here for you. So to make sure that we are keeping going, I do want to stop a little, do a little extra pit stop on the motivation side of things, because motivation is important. I want you to use Aquila. QSC seems like they also want you to use Aquila because we are partnering together. And I want you to get a reason as to why you would be doing this. So FPQAs, they really give you access to very efficient problem encoding. This is a nice example that we put together. Let's say you want to put coffee shops in Boston, right? Dunkin' Donuts, it's what we do there. And you don't know where, right? So let's say we remove all Dunkin' Donuts, and Dunkin' Donuts say, like, we want a new plan to put all the Dunkin' Donuts in the city in the best possible way. I'll tell you, well, we put one everywhere. They'll say, well, if I put one everywhere, A, it's going to cost me a lot. B, these guys, they're going to start competing with each other, and maybe I don't want to put them close together. So I say, okay, no problem. I create a graph of all the plausible positions of Dunkin' Donuts, and I make edges between any two stores that would be competing with each other. Guess what? Aquila can make Boston in atoms. Each individual spot there is one of those spots. And if you doubt it, I just encourage you to look at this bottom right corner here. You can see that triangle structure. It's really the same graph. Okay, we are making Boston in atoms. We made Boston in atoms. We made Manhattan in atoms. We made a lot of things in atoms. It doesn't need to look like a city, by the way, but it's just to give you an idea. And guess what? You can compute, and all the atoms that disappeared are here, optimal positions where I could put my stores in a way that they don't compete with each other. So if you look at the graph on the side, the logical version of this, you see that the red dots, they would be the place where I would put a store, and there's no two neighboring red dots, right? Two neighboring red dots would be connected by an edge, so this means that they would compete with each other. Okay? So this is something that our machines can do directly. So if you like optimization and you don't like physics, or if you like both, we can do that. Okay, but tomorrow we are going to be focused more on physics problems, and there's plenty more, right? So we have a lot of atoms. You can parallelize your processor. You can define sub parts and increase your throughput. There's a lot of interesting things. So the bottom line is we did go through our architecture and analog versus digital operation. We went through a little bit of this FPQA paradigms and the discussion of what are the hardware constraints that you have when you try to encode our problems in our machines. But I hope that you are convinced that we covered all our learning objectives. So I will be taking quizzes in the afternoon. So if you cross me in the corridor, I will ask you questions. No, I won't. No, there's no pressure. But I hope that indeed you feel comfortable at explaining a little bit better how neutral atom machines work today and what means this analog digital and why you actually care about analog quantum computing. And yeah, that's it, right? So field programmable qubit arrays and our programming range. I hope that this is not too late.
Any questions for our speakers? I know that we had a lot of questions during the talk, but are there any questions following up?
Thank you for the talk. Could you share, please, what currently limits the 4 microseconds of the simulation time?
Of the simulation time, it is of course that we can actually run things for longer, right? This is a good time within which we can guarantee to you that you appreciate, you see all the coherency effects, etc. We want the quantum properties of this machine to be very robust for the user. Okay, and at the end of the day, that's it. So nothing more than that.
All right, let's thank our speaker one more time.
For tomorrow, if you can, please try to install the installation guidelines are here in the beginning, and it's really these 3 lines. Okay, so tomorrow we can play better if you got this on your laptops. So here we go. Thanks again.
All right, looks like we're headed right into break 5 minutes late, so we'll take a 15-minute break as scheduled and kind of shift everything back 5 minutes. So we'll see you at 11:30.
This optimization problem you showed, that's a typical problem that you would do on Z-Wave. So how is it different?
How is it different?
Yeah.
I tell you how it's different. Oh, great. So the difference here is twofold. Number one is coherence. Okay, so
Let's wait just a minute longer for people to
Okay,
settle in.
sounds good.
So I get what they're thinking around. All right, let's get started. Our next talk is by Raksha Katiwara. Professor Raksha Katiwara is an assistant professor at Illinois Institute of Technology and associate scientist at Fermilab. Katiwara earned her bachelor's degree in both physics and mathematics from Linfield University, followed by a PhD in physics from Purdue University. Boiler up. She completed a postdoc at University of Washington in Seattle before joining Fermilab for her second postdoc. Today, Katiwara is engaged in quantum information science research, an area Illinois Tech is expanding into with her help. Quantum information sciences combines both computing and sensing with quantum mechanics, focusing on physical properties of atoms and subatomic particles. Please join me in welcoming Professor Katiwara.
Hello, everybody. So, as Ethan said today, I'll be talking about quantum science for fundamental science, and in particular, I'll talk about how we can utilize quantum science for dark matter searches. And so, I'm a scientist at Fermilab, and we have a group with a couple of different projects that specifically look for dark matter and that specifically investigate quantum information science to look for dark matter. So I'll kind of talk a little bit about what we are up to right now. And since this is a very short talk, somehow I will have I will have to skip a little bit of the details, and I'll just kind of touch some of the information just very, very lightly. So I apologize for that. Here is a picture of this new facility at Fermilab that we just started. This is a new dilution refrigerator inside a clean room, and this is dedicated in investigating these qubit-based quantum technology for dark matter searches. So let's get started. So my talk, here is an outline of this talk. So I'll touch very, very quickly on dark matter search overview, and then I'll mention why we can use qubit-based quantum sensors, what is the advantage, and I'll just briefly also mention how can we detect these dark matters utilizing these qubits, followed by a very brief summary. So just briefly talking about dark matter, we know dark matter constitutes more than 5 times matter content of the universe than the ordinary matter that we know of. And some of the properties are, it's a non-standard model particle, it's weakly interacting, it cannot be detected with traditional observational astronomy, tools and techniques, and it makes up a large, it makes up large structures of the universe. It clumps together, and the type of dark matter we are interested in that forms the structure is called cold dark matter. So that's kind of what we're looking for. And so by now we actually already know that dark matter must exist through all these astrophysical probes like gravitational lensing, galaxy rotation curves, and cosmic microwave background radiation, etc. So we have a whole lot of motivation to look for this dark matter. And at Fermilab and IIT, we have a group of people who are looking for dark matter. So let's just kind of look at some of the candidates for dark matter. I don't know if you can see my pointer here, but you can see the parameter space. This shows the mass, possible mass a dark matter particle can have. And as you can see, EV is somewhere in the middle, so we're talking about extremely tiny particles that are sub-EV, right? And then on the higher mass scale, we have also medium-sized black holes also with, tens of solar masses. So we're talking about extremely wide parameter space. And as you can imagine, the tools and techniques needed to look for these kind of dark matter particles is going to be extremely different because the parameter space is so big. So for today's talk, I'm going to loosely lump these dark matter candidates that you can see into this like red section that we call wave-like dark matter. And then the ones in yellow dashed line you can see that are called particle-like dark matter. We kind of do this because they kind of in some ways behave like particles, like separate individual particles scattering off like billiard balls, like you can see on the right here, whereas the lighter particles, they kind of behave like wave-like. So you instead of individual particles scattering, you want to think of this wave of dark matter coming to your lab apparatus. And so you can imagine the detection technology is going to be very different for these two. I'll kind of spend our effort describing our efforts at Fermilab basically in this middle range here that now you can see is an overlap between those wave-like particles and then particle-like dark matter. So let's just first maybe just quickly touch on like how traditionally we have been looking for these wave-like dark matter and then particle-like dark matter, and I will transition into how we can utilize quantum science. So here is a very good example of wave-like dark matter called axion dark matter. And so we are super creative in naming our particles because this theorist you guys know about, Frank Wilczek, he named this particle axion because he thought it cleaned the strong CP problem in QCD very nicely, like a dish detergent would clean a dirty dish. So that's kind of how creative we are. So this is an example of a wave-like dark matter. So how do we detect this traditionally? So I'm all talking about like traditional detection mechanism, okay? So it was produced after Big Bang. It's everywhere. It's in the local Milky Way galactic halo. It gets kicked around in this gravitational potential. And of course, the velocity is a distribution, right? So it's a Maxwell-Boltzmann distribution. And its mean is similar to the local virial velocity, which is 10 to the power minus 3c. And there are tons of these in a volume, in a small volume. So number density of these is like in the order of 10 to the power 14 per cubic centimeter. And so you can think of this as these football stadium-sized clumps of axions drifting through the detector of wavelength of 100 meters or so. So traditionally, what we have been doing is we have these so-called resonant cavity-based axions detection mechanism, and so this is the most sensitive detector we have up to date that probes this kind of dark matter called axion dark matter experiment. So this experiment uses this kind of cavity here. So this is a resonant cavity. When its frequency matches to that of this axion wave's frequency, resonance enhancement takes place, and there is this extremely high magnetic field that provides a very uniform magnetic field here that provides the condition for this dark matter axion to convert into visible photons. So what you have is a very small, minuscule power from this photon that comes from dark matter, and this is in the order of 10 to the power minus 24 watts or so. So that's extremely tiny, right? We pick up these through antennas and then amplify this using amplifiers. And turns out the best of best amplifiers that have lowest noise are quantum amplifiers. And I'll talk a little bit about like what they are based on. So those are the amplifiers we use because we don't want to add extra photon noise. So turns out, if you have an amplifier, it's going to not only amplify the signal, but it's going to add extra noise. So you want to minimize that as we are picking up this like super tiny 10 to the power minus 24 watts of power deposited from dark matter, right? So that's that, and then the signal gets amplified and digitized, and what you hopefully see is this sort of power spectrum where there's a blip that is the signal that's centered around the dark matter mass. However, this is, like very, very airbrushed version of what happens, right? Because this signal is going to be buried so deep in the noise that you'll have to do this measurement many, many, many times, and even then it's not going to look like this, right? So the whole parameter in any experiment is this, the most important parameter is this signal-to-noise ratio that is listed here. And you notice this T system, which is the system noise temperature on the bottom here, and you want to minimize that in order to maximize the signal-to-noise ratio. And so in order to do that, so what is this T system noise temperature? So this is going to depend on the physical temperature of where you do your dark matter search, and also the noise temperature of this first stage amplifier that I just mentioned, which is quantum amplifiers. And so that's kind of like the whole reason people in dark matter community, at least in wave-like dark matter community, entered in quantum science. So these quantum amplifiers are based on these squid loops. So you guys are probably familiar with this already. Squid loop is basically the basic building block of quantum circuits, right? So it has these two Josephson junctions. You can't probably see my pointer here. So the two Josephson junctions and the superconductor there. And so this is a very quantum phenomena because you have this Cooper pair of electrons tunneling through that insulator. And this has very unique and interesting and very important property that is, you can think of this, this loop, you know, when even for a very, very small amount of magnetic flux pinning through this, you can have a very good signal voltage across it that you can check out, you can see. So on the bottom here, you have this voltage change, very big one for a very small flux change in the loop. And so that's actually the fundamental basis for these amplifiers, you know, fabrication, and also they are very broadly used in particle physics and cosmology for like pickup signal because it can amplify, you know, like any small signal. And we have been using this in particle physics for some time. And so we kind of, so this was like a, you know, precursor to quantum science using qubits and other things for particle like dark matter. So this is kind of how we started. So let's see. So it's good that we're using these quantum amplifiers and other things, but now these quantum amplifiers are limited by so-called quantum noise. And so what is that? So we're measuring, as I said, power, and photons are electromagnetic field, as you can, you know, as you already know. And so it turns out when you are measuring the phase and amplitude of electromagnetic wave, kind of like from uncertainty principle, you're making measurements in two non-commuting quantities at the same time. And so you're fundamentally limited by how well you can measure both of them at the same time. And so you have this fundamental noise limit, which is called quantum noise limit, which I have listed there. And so that's going to be high. Remember, like I mentioned, that the dark matter signal is super small, and even a quantum noise like this that comes from uncertainty principle is going to be high enough that our signal is going to be buried. And so that's the fundamental challenge in this kind of dark matter detection scheme. So I told you about the current status of the wave-like dark matter scheme. The particle-like dark matter scheme in nutshell uses slightly different techniques. And so I'm going to get at, the point I'm going to get at is what is the current status of that, and how do we jump to like quantum science being useful for that. So the current technologies in this particle-like dark matter search implement these scattering off of nuclei and scattering off of electrons processes. So they are typically done underground because we have these cosmic muon and unwanted radiation coming in and acting as background to these kind of detectors. And also terrestrial gamma rays, these can also be backgrounds that kind of mimic the dark matter interaction with your target material. So the dark matter can not only scatter off of these nuclei and electrons, but it can also be absorbed completely. So the whole energy of this dark matter can be absorbed, and you can have some sort of excitation in the material, target material, that will tell you there was some dark matter that, you know, caused this excitation, right? So that's kind of like the general gist of how these current experiments look for dark matter. And so here are two examples of the current particle-like dark matter detectors. You guys have probably heard of Super CDMS Snow Lab experiment and LZ. They look for WIMPs, weakly interacting massive particles. Those are very commonly known particle-like dark matter experiments. So how do we go from here to quantum science, right? So one of the very fundamental challenge in particle physics is, so here if you look at the summary, the blue region is the region that does not have current existing technologies that we can look for dark matter. So the current technologies I told you, they are just limited in this green and yellow region. The blue regions are not, and the reason for that is, so if you look at the top two, the scattering processes, where you see this mega electron volt, so a dark matter with mega electron volt mass, it's going to transfer several orders of magnitude less momentum and energy to the target material. So it's not going to transfer the whole, like its energy, but it's going to be a fraction of that. And that's going to be less than an EV. So that's going to be less than an EV. I want you guys to make a note of that. And similarly, in these absorption processes, you can have the whole dark matter mass be absorbed into the target materials, but then we don't have a technology where we can see some sort of signal from these sub-EV type of dark matter absorption in target materials. So the whole point of wanting quantum science is we want some system that will detect this sub-EV type of energy deposition. So that's the gist of it. And turns out quantum science is great for that because we have these qubits that sense extremely small quanta of energies. So that's kind of the bridge here. So when we are talking about this kind of very small energy coupling coming from dark matter to our system, target materials, the best way of harnessing all the energy, or most of it, is through lattice vibrations of these target materials. So imagine phonons, right? Phonons are lattice vibrations. Along with that, we can also use for single photons that come from dark matter, and qubits can easily detect photons because, as you all know, state preparations in qubit is all based on photons, right? So photons, qubits can detect single photons. So that's kind of the two things we kind of want to utilize in qubits to look for dark matter. Let's see. So the other advantage of using these qubits is, of course, they are all housed in this millikelvin cryostat. And as I showed you earlier that you want to minimize backgrounds. And since our signal from a wave like dark matter was photon, we want to minimize background photon. And so this is a very good ideal environment to operate those experiments. And then superconducting technology is intrinsically low noise, right? There's not a whole lot of resistive elements, not a whole lot of dissipation, heat dissipation. So that's actually really good. And so this all has advantage. You guys are already familiar with qubits looks like, because this is kind of like at the end of this program. But we are not so much interested in the computational subspace aspect of a qubit, but more like the hardware aspect of the qubit. As I mentioned to you, we want to couple phonons and photons, these very small quanta of energies, to the qubit, right? So the superconducting circuit is of relevance to us. Let's see. So let's see what has been demonstrated using qubit-based dark matter detectors. Can we do it, or is this just like wishful thinking, right? And so we have actually demonstrated some really significant results already using superconducting qubits. So there was this is work by Fermilab, our Fermilab colleagues and University of Chicago colleagues. And so they looked at this. So they were not doing dark matter research. So these are just quantum group, and they were just trying out new thing, and they were like, hey, can we do this dark matter detection? Particularly, they were looking at this wave-like dark matter, not the axion, but hidden photons. That's another type of wave-like dark matter. And so they had this qubit and a 3D cavity. So you guys are already familiar with the quantum computing infrastructure that has a 2D resonator coupled to a qubit, but here it's a 3D cavity. And so you can actually couple it to this blue here. This is a cavity, another cavity. So this is a dark matter converting cavity. So here, dark matter will convert into some photon signal. And so if you couple something like this, what you have is like, you can actually sense, of course, like you guys already know, if you want to sense something with a qubit, you don't want to make the measurement directly at the qubit, right? You're just destroying its state. So that's why we have these cavity coupled systems with the qubit, because we're kind of reading out the qubit state with the cavity, right? So we implement very similar stuff. And so what you end up seeing is for the number of the photons in this cavity, you can see corresponding shift in the cavity frequency. So that's kind of the gist of it. And so depending on however many photons from the dark matter come here, you'll be able to see corresponding shift. So that's kind of a very, very neat idea using this qubit apparatus. So they published this results in physical review letters. And so this surpassed the sensitivity. So this was the integration time. The data taking was done over just a few seconds, like 8 seconds or so. And it's a very, very narrow thing because this was not a designated dark matter, like a run, but they demonstrated that it has very, very good sensitivity, and compared to these things, these limits, it has taken these experiments years to get this limit. So you can actually get really, really good sensitivity with qubits. So this has been demonstrated already. So at Fermilab, we are looking for different ways of looking for dark matter. The one I showed you is one type, but you can utilize, of course, there are, like assortment of qubits too, right? Like there is not just one type of qubit. And so all of them have slightly different advantages. And so we're trying to look at how can we utilize these different types of qubits to do different types of dark matter detection. And one of these efforts happening in our group is using this quantum capacitance detector, which is based on charged qubit. So the general idea is, so this is fabricated by Jet Propulsion Lab. We have collaborators there. So for NASA mission, like in these far infrared spectroscopy missions in space telescopes, they use these kind of detectors to detect photons from the space. And so here is a picture of 25 array detector that we have at Fermilab. So the main idea behind this is you have this ground plane near this blue arrow. So this ground plane is a aluminum mesh. So this is a superconducting aluminum. Imagine dark matter photon signal that I mentioned to you guys about hitting this aluminum mesh. And so if it has more than twice the band gap energy of this aluminum, it's going to break the Cooper pairs in the superconductor. And in traditional quantum computing, you do not want broken Cooper pairs, right? That's the cause of decoherence. That's going to kill your apparatus. But here, we want to use that as a signal. And so this is slightly different than quantum computing. We are using similar infrastructure, but we are kind of using it as a signal to our advantage. And so this broken Cooper pair of electrons can be easily read out using charge parity measurements, which is one of the basic measurements that you can do with qubits. And so here is demonstrated 1.5 terahertz photon, single photon detection through these detectors by JPL. So these gaps here are caused by single photon events. And so at Fermilab, we're trying to use, okay, can we use this to look for dark matter? Because imagine that photon 1.5 terahertz comes from a dark matter. Can we do that? So JPL doesn't do dark matter research, so we're trying to do that. Okay, so the other idea that we're entertaining is, and so this is extremely new, so you'll probably not see this anywhere yet. Can we use this substrate on the qubit to have this dark matter come and scatter off of them? And so the broadly used, two broadly used substrates in qubits are sapphire and silicon, right? And so sapphire turns out has many different phonon modes that can couple to this dark matter, as I showed you earlier. And these energies that you need to excite these phonon modes are below EV, and that's the key, right? I mentioned earlier, that's the area that we need detection technology in. And so, can we couple these phonons, and then that energy is going to be like 2 orders of magnitude bigger than the energy you need to break the Cooper pairs in the superconductor. And can we use that as a signal to look for dark matter? So that's kind of another area that we are entertaining and working on in our QSC group at Fermilab. Here is a big cross-section of the dark matter group that we have there. We have a couple of projects working together. And so this is a new program, QSC program started in 2020. And we have this brand new dilution refrigerator that I showed you earlier. We have several new qubit-based experiments that we have housed. And we collaborate with Illinois Institute of Technology, Northwestern, and Fermilab, and we have students and postdocs at the forefront of this program, moving our very state-of-the-art facility and program here. So, apart from that qubit-based detector development, we are doing these other technological development that we need to bridge the gap between being able to use this qubit detector with what we want in dark matter. And so some of these have very broad applications too, like this one. This is called Quantum Instrumentation Control Kit, in short, QIC. Probably some of you have already heard about this. Chances are you have, if you are using a lot of big arrays of qubits. So these are these toolkits, and also there is this like electronics board that Fermilab senior engineer and his groups have developed recently. And they have demonstrated really good performance in qubit control and readout using this toolkit. So this is very specifically tailored for qubit control and readout. And some of the issues that we covered in earlier talk here about the need to use tons of lines, RF lines and components, and it being really expensive, and the real estate inside the refrigerators being really limited, those can be mitigated and reduced by using this kind of toolkit. So this is based on this commercial FPGA platform, and so yeah, this is one really neat thing that a lot of universities and institutions throughout the US have been implementing now, including SLAC, National Lab, Chicago, Princeton, Berkeley, so yeah, you name it. So this comes from our group. Let's see. Oh, so the other thing that we're doing is, so we talked about building detectors to look for dark matter. And so this work, simulation, is extremely relevant for quantum computing also. So this is about understanding phonon and charge transport in these substrates and qubits in general. So you probably have heard about a lot of these new results, and I'll show you in a bit the result that came out a couple of years ago from Google. You want to understand these background events in a quantum computer. right? Like because these background events deposit large amount of energy and they cause qubit decoherence, not just local, but kind of spreading throughout the qubit chip. And so that's not good for error correction, right? You don't want correlated error. So we need something like this. If you want to do anything with qubits, whether detector development or quantum computing, you want to understand how does the initial energy that gets deposited in your qubit dissipate? Like where does it go? Like what are the things you can do to mitigate that? Those kind of things. And so that's happening at Fermilab. So we in particle physics community have an advantage for this because we had to worry about the same background radiation events like cosmic muon and the terrestrial gamma, like backgrounds in our dark matter detectors. And so we have these tools, particle physics tools like that simulate these particle interactions in your target material. And so we are leveraging on that. So at Fermilab, we have students and postdoc working on simulating these kind of phonon kinematics and charge transport in a qubit using these toolkits based on Gent4 and G4CMP. And we collaborate with Northwestern and SLAC. And the super CDMS group that looks for dark matter is particularly useful because they have had those expertise. So we are trying to leverage on that. But of course, it's not sufficient, right? So the materials targets they have looked at is very limited. So we're trying to expand that. And so that's kind of another area of research. And we have these cryogenic photon source development going on. So to characterize these qubit detectors, as I mentioned, we are literally counting photons, and so we kind of want very, very weak photon source that works in the millikelvin temperature stage, doesn't provide, doesn't have like super, like a super broadband like noise, like a black body source that produces photons in all different frequencies and needs filtering. We want something elegant, and so we are kind of trying to look for a solution, and we have this something called this MEMS-based steering mirror and this cryogenic photon source development work going on at Fermilab too. And we also have this underground facility at Fermilab. And so this is very relevant for dark matter research and quantum computing right now to understand the impact of these radiations that I mentioned to you about. Being underground, you block, the layer of Earth will block these cosmic muon and those extra radiation that you have to worry about. And we also use these lid-shielded environment in the dilution refrigerator, so that will block some of the terrestrial radiation also. And so we have designated facility, and Fermilab is great for this because we have neutrino tunnels like shown in the left here. And we had this middle facility for some time, but we have recently built under QSC this brand new facility on the right that's called Quiet. And so Dan, who is a PI on that project underground, so we work closely above ground and underground, and we want to make comparative studies and very quantitative studies on impact of these kind of radiations by doing this comparative study underground and above ground. So we have that happening. And so this is relevant because, as I mentioned, there have been many papers out there where they have indicated that these kind of radiations do impact quantum computers. And this is from, I believe, 2020 or 2021, Google Sycamore processor, right? Like where they showed that, cosmic muon, like energetic event can cause havoc in the chip that was like 60 qubit chip, and it was not just localized, decoherence, but it was everywhere, like for some time, right? So studies of these kind of events underground and above ground will help us understand this better and come up with mitigation technology. So in summary, what I want you to take out from this talk is we are interested in particle physics community to use qubits because it senses extremely small quanta of energy, single photons, phonons. So those are the things we are interested in. And this is very, very focused on the superconductor in the qubit being able to produce signal through broken Cooper pairs. That's kind of what we are interested in, using it as a signal. And so that threshold for producing that signal is very small, and that's why we're interested on it. And let's see, qubits can sense different types of dark matter, like the ones I told you about, particle-like dark matter and wave-like dark matter. So we have several of these efforts going on at Fermilab and IIT. As I mentioned, these two efforts. And yeah, that's kind of the summary of this talk. Thank you.
Thank you very much. Do we have any questions for our speaker?
Yes, I saw that.
Please wait for the mic so we can be on.
I had a quick question about the phonon dispersion. So is your understanding, is your characterization of the phonon dispersion to the point where you could actually start doing experiments to try to detect them in addition to the photon interactions?
So yes, good question. So we are still in the not so mature phase yet. So to answer your question, the phonon propagation in these kind of dark matter experiments has been done only in silicon and germanium kind of crystals. So if we use a qubit that's a silicon, there is some infrastructure already that kind of like explains a little bit, but it's not complete. So they don't look at, for instance, they kind of like lump these phonon kinematics into charge kinematics. And so, like you would have like electron hole pair production, and then, like the estimates come from that. However, if you are talking about extremely low radiation, you don't have energy to break, like electron, excite an electron, right? So you kind of need to go beyond that and look at just the phonon kinematics. And so those kind of things we need to really, like tailor and like understand for this. So to answer your long story short, the infrastructure we can use, we have something to build it on, but we don't have it well developed enough that we have a good understanding of it to be able to right now just fit it with an experiment. And a lot of these efforts will have to be done with the, in parallel with the experiment, because you want to have measurements from the experiment kind of as an input to the simulation, because this simulation depends on your properties of the material, impurities and stuff like that. You cannot really it's very dependent on the particular stuff you use, right? So in that case, you can imagine how you need to do cross-check and cross-input and then come up with a realistic model. Yeah. Yes.
Oh yeah. Without understanding the exact differences between how you use, I guess, dark matter research versus qubit experiments, it looks like from one of your slides you use the single mode cavities for 3D architecture.
Yeah.
Is there any sort of looking into implementing multimode cavities for dark matter research, or?
Yes. So yeah. So there is a lot of R&D on multimode cavities for cavity-based dark matter search. So in our particular program, we are not so much doing that kind of work. But if somebody is interested in that and says, okay, we can use these multimode cavities, and then we can produce these signal from dark matter, and then we need some qubit detector to detect that, then we are open to working with them. But right now, we're actually not looking at multimode cavities.
Oh, hi, my question is, when you search for axion,
Yeah.
the cavity needs to be put in the high electric field?
Magnetic field.
Magnetic
Yeah.
field, yeah. Will that change the behavior of the transmon and the cavity?
Yeah, excellent question. Excellent, yes. So this is one of the challenges that we have to worry about, because superconducting technology is innately, does not like magnetic fields, right? So that is an excellent thing we have to worry about, yes. However, I want to say that, so imagine a scenario where you convert this dark matter into photons or some signal in the magnetic part, and then you put your detector, photon detector, outside the magnetic field. And you have some sort of coupling. And this is an active area of research that's happening right now. How do we minimize the loss between the coupling? Because we're, again, talking about super small signals. So you do want to minimize the loss by, like using that coupling from magnetic field zone to, like something that doesn't have magnetic field, right, farther away. So yes, that's an active area of research, and we do have to worry about that. Any more questions? Yes.
Hi, yeah, thank you for the great talk. So my question is about the potential impact for a successful implementation of some of these qubit-based detectors.
Yeah.
I'm thinking specifically about the axions.
Right.
So, suppose you were able to successfully kind of get in this sub-1 EV regime.
Yeah.
Of course, there'd be tremendous impact if there was a detection. I'm curious, I guess, also, what would be the impacts of a non-detection? What would that mean for the axion search?
Right, right. Excellent question. So, not detecting and being able to confidently say, we looked for axion and it doesn't exist here is very important, right? Because it tells you it doesn't exist there. And so that means it eliminates a very small chunk of parameter space and opens up the possibility to look into what's remaining. And so that's very important information too. At least we dark matter people like to feel good about that and tell ourselves that this is still important. So, but yes, so it's an important information. Yeah.
Yeah, thank you. This is not my field. For me, it's still a dark field of research. But if I see like a particle-like and wave-like, and we know the duality in quantum mechanics, can you look at interference?
Okay. So that's a zone that, I think, yes. My thought is yes, probably, but we have to think a little bit about like what exactly do you want from that kind of experiment? Like, so what's your goal?
Your field, I don't know. I see quantum mechanics, you have interference between particle-like and wave-like.
Right. So I guess, like perhaps, but we'll have to think a little bit more about like how to do that. Yeah, that's a good question. Yeah.
Sounds very interesting. Do you know if are there proposals for creating detectors also based on non-composite qubits, like atomic qubits? They don't, like the cross section should be minimal. They don't care really about these effects. So, as far as I can tell. So, do you know if there is any?
Yes. So there is. There are several efforts. So one thing that comes to my mind is like. There is like Rydberg atom, for example, type of, like qubit states that can be used to look for this dark matter in tens of GeV or something in that range. So yes, in principle, there are technologies that will be sensitive to some fraction of this parameter space that I told you with those atomic transitions. However, yeah, that's not something we're doing in our effort at Fermilab and IIT.
Do you know if these ones, they are WIMPs or are they strongly dark matter candidates?
Oh, so they are actually still wave-like dark matter. So they are light dark matter. I mean, ultra-light
but
dark
they're
matter.
weakly interacting or strongly interacting, the expectation? That's the question.
Oh, all dark matter interacts weakly.
Okay, we can talk about that later.
Yeah.
Okay, thanks.
Yes.
All right. I think in the interest of time, we have to move on, but you can follow up with the speaker afterwards. So let's thank our speaker one more time.
Oh.
All right. Next speaker is Zheng Yi, Professor Jun Yi is a fellow at JULA and a fellow at NIST. Yi is also a member of the National Academy of Sciences, a fellow of the American Physical Society, and a fellow of OSA. His research focuses on the frontiers of light-matter interaction that include precision measurement, quantum science, ultra-cold matter, and frequency metrology. He has co-authored 380 scientific papers and delivered over 600 talks. His group explores precisely controlled lasers to enable our communications with microscopically engineered quantum systems of atoms and molecules. By preparing matter in specific quantum states using probe light with the longest coherence time and precisely controlled waveforms, they strive to make fundamental scientific discoveries and develop new emerging technologies. Let's welcome our speaker, Jun Yi.
It's on? Yeah. Okay. Well, thank you very much. I want to thank Sasha and Vlad for inviting me to this workshop and seeing on Saturday so many enthusiastic discussions going on with students. So this is great. It's actually perfect that my talk was previously going to be before the previous speaker, but now it's after, which is perfect. You know, the previous speaker set the tone right. I flew in really late last night. That's why my talk was arranged to be the very last one in the morning. I hope I will finish on time so we can all go to lunch soon. So I'll tell you a little bit about clocks. And I want to give you the sense that the clock and the previous speaker talking about dark matter search, it's very much connected. And I will tell you, there was a great question about, can you use atomic qubits to do dark matter search? The answer is absolutely yes. So you will see some of that, although I mainly want to tell you about the exciting time when you can do tabletop experiments, building on quantum systems, and have a big impact on both condensed matter physics, particle physics, high energy physics. So in some sense, quantum science is really at a very exciting stage right now for discovery. Okay, so what is quantum metrology, right? Our previous speaker very nicely said, in order to enhance signal-to-noise ratio, you want to look for quantum systems that has a very long coherence time. And some of those these days can have a coherence time, like the clock I built, can have a coherence time that allow you to have quality factors of these oscillators approaching 10 to the 17, meaning this, once you prepare this quantum coherence, it will persist for 10 to the 17 cycles before it decays away. So it's amazingly long coherence. And you want to build with large quantum numbers that would allow you to build up statistics and large count rate. And in the end, now that we have this quantum information era, where we are starting to talk about entanglement, and you have heard from this workshop, people like Misha Lukin, people like Chris Monroe were telling you about quantum gates. And now you start to think about these quantum gates can actually be applied onto the quantum, on the computer, on the clocks. And the reason why I emphasize this point is whether you're building a quantum sensor or building a quantum computer, they're very much the same thing, right? You're building on the exact same technology. And I even think of myself as building a quantum computer, not necessarily for universal quantum computing purpose, but for specific purpose of searching for, say, dark matter, or building the very best clock to connect quantum physics and gravity. And so the field is exciting. And it really comes from this very rapid evolution, or I would say revolution of our field. If you think about it, over the past 20, 30 years, how many Nobel Prizes have been given out to the field of atomic physics? Quite a few, 5 or 6. All of them happened since late 1990s. And almost everything that we use to build a clock today builds on these sort of fundamental research, and yet we are integrating them together into today's technology. Quantum control that allowed us to approach extremely high quality factor of optical transitions. Novel laser technology now allow us to access optical coherence approaching a minute. Frequency comb technology allow us to synthesize electromagnetic fields. Quantum gas, such as Bose-Einstein condensation and so on, allowing us to probe many-body physics for entanglements. So therefore, the clock that we build based on these sort of incredible strong advance in both fundamental science and technology has rapidly advanced. In my career, for 20 years or so since we were building these clocks, this number has advanced to 5 orders of magnitude.
And it's now reaching field parts 10 to the 19th, accuracy at 1 times 10 to the 18. But I have to say, this revolution is not stopping. And that's because over the past couple of years, this number has now already changed by a factor of 50 on the measurement precision, reaching a field parts 10 to the 21. And just remember, 10 to minus 21 is when LIGO first heard a gravitational wave in 2016. So these are the numbers that's actually kind of going to be quite important as we continue to push on this to start to see things that nobody has seen before. And I want to emphasize this particular point that these days when you're building atomic clock, it's really not just for the timekeeping piece. It's really a quantum system that allows you to understand a many-body Hamiltonian, systems like that, where you have to understand it, because otherwise you'll have a systematic effects at the 10 to minus 19 level or below. At the same time, once you understand something, you can control it. So now you can start to think about controlling these kind of many-body Hamiltonians to enhance the measurement precision, to build entanglement into the system. So I'll tell you a little bit of both in today's talk. As you can see, the building clock is nothing but building a microscope to look into sort of layers of quantum science of emergent phenomena. And by the way, if you have questions, please stop me in the middle of this. It's much better to see the interaction as I just witnessed from the first speaker. But I don't want to just tell you the story about the clock. In fact, I want to start with telling you a little bit about following our previous speaker. I decided, I think it's actually quite interesting to think about this very broad scope of what quantum science's impact on fundamental science. The building accelerators was a golden age in the 1970s, 60s, and so on. Right now, the quantum science is at the golden age, because we want to see some of the fundamental symmetry breaking process, such as CP violation or time reversal symmetry. If you look at an electron, it's got a magnetic moment. If electron has electrical dipole moment, which the standard model says it should exist at the level of 10 to minus 40 electron centimeter. So it's a very, very tiny level. The standard model actually has a built-in violation of a time reversal symmetry. Why it's a violation of a time reversal symmetry? If you look at the magnetic dipole, if you reverse the time evolution, the magnetic dipole will reverse its direction because it's associated with a spin. But electrical dipole, however, is a parity in space. When you reverse the time, the electrical dipole is still pointing in the same direction. Now you can see if the electrical dipole exists, it will actually violate time reversal symmetry. And this part we knew exists, right? We already knew this. The problem is there are many, many mysteries in the universe we do not understand. That matter, antimatter symmetry, the existence of dark matter, the fact that the sun has searched really, really hard, they never found any WIMPs particle, as we heard. So something is wrong, something is missing, we haven't seen it. And if this time reversal symmetry is probably from the standard models likely too weak to explain this mystery. And that's why there's a very strong motivation to search for the existence of electrical dipole moment much bigger than the bottom of the standard model. So it's very strongly motivated theoretically. And what can we do? Well, it's not about smashing two bigger particles and generating a new particle like a CERN traditionally does. It in fact comes from tabletop experiments, could be coming from a lab in Purdue. And these are the experiments that's happening right now. Let's see. The basic principle is you have a molecule and you have this electron that's confined within that molecule. Within the molecular frame, you have this exceedingly large electric field. And this exceedingly large electric field can be very easily manipulated with external electric field in the laboratory when you can make the molecule oriented up or down, when you can also control independently the electron spin. So what this gives rise to is a co-magnetometer and an electrical dipole measurement device in a same molecular system that you can actually look for this combination of my dipole is a proportional to the oriented with respect to the electrical field or anti-parallel to the electrical field with a different magnetic field, magnetic dipole orientation, such that you can cancel out many of the systematics associated with the search for the electron dipole moment. And this has been an approach that our field has been using. In fact, you can see this incredibly rapid, and this is actually not common to see fundamental science moving in like that. This is the 2002 when Berkeley, Eugene Cummings, the pioneer of EDM, back in 2002 set a limit with atomic beam, thorium, at just above 10 to the minus 27 electron centimeter. And soon after that, Imperial College and then Acme is a collaboration between Harvard, at the time Harvard and Yale, now it's a Harvard, Northwestern, and Chicago collaboration. And you can see that the Acme moved quite a bit by 2 orders of magnitude over the less than a decade based on the Imperial College results. And the Gela result, and it's actually just came out, we put this on the archive, and it's going to come out in Science, is now further pushing this towards the 10 to minus 30 electron centimeter. Nobody has found it. There was a question about earlier, what if you didn't find something? And the answer was, it's still really exciting because you're setting the limits. But for dark matter and electron EDM, there's some difference. Dark matter is this incredible range. Nobody knows. The mass of the dark matter can range from 10 to minus 20 eV all the way to the mass of the black hole. So there's a 50 orders of magnitude. So you say, I'm setting a limit at 1 gig eV or 1 eV. It's a small swatch of the landscape. But still, it's worth doing because Axion is also very motivated in theoretical sense. EDM, on the other hand, sooner or later, it has to be there. We know that for a fact, right? The EDM actually exists at 10 to the minus 40. It's just that that's in standard model. It's just that we also know there's new physics going on between this 10 orders of magnitude, from 10 to the 40 to 10 minus 30. So it's going to be exciting if we can continue to build on quantum science, on cold molecules. One day, one of us, including you, will find that EDM, and that would be big. That would be a big thing because it would explain many of the mysteries of the matter, antimatter, and asymmetries, and may perhaps is even a candidate for dark matter. How do we do this? In some sense, since this is a workshop of quantum science, and I want to reflect on that, on that theme. It's nothing but, in some sense, looking at the molecules, but with a modern twist of quantum control. If I prepare these molecules, and we all know molecules are notoriously complex, but nowadays, we can actually do optical pumping, for example, to prepare the molecules into a particular quantum state where we're going to use for EDM search. This is the 4 states I was telling you about, this combination of electron spin and electrical dipole moment orientation. And so this control has been giving us this amazing technology of preparing single quantum state in molecules with regard to its orientation, its spin, and so on. At the same time, we also can let molecules coherently evolve in its quantum state. It's like a spin resonance. Oh, sorry. I'm sorry, that's like a spam call. And in this particular case, for example, when we can say, I want to look at the coherent superposition between spin down and spin up, and I can actually dissociate, the photo dissociation. It's actually old technology of chemical physics, but in a new twist with quantum science, we can, for example, when I dissociate the molecules, depending on whether spin down or spin up, it flies out left and right, so I can simultaneously measure how many molecules are in spin down, how many molecules are spin up, and I can remove the quantum noise fluctuations to get to the so-called quantum spin noise limited measurements. And all of that allow you to build this type of interference, or you can say Ramsey spectroscopy of the spin resonances. And these are not a theoretical calculation. These are experimental data. This incredible long coherence time over 2 seconds, we can see this electron evolving. And if there was electrical dipole moment, what we are seeing is this evolution time changes slightly. It reminds you of building a clock. It's very much like a clock. And so being able to do this kind of a very long coherence time, quantum noise limited sensitivity measurements is what we are talking about as a quantum sensing. So this is really the main thing I want to say for this workshop. So let me go back to, since our previous speaker also touched on what is quantum noise. She mentioned about photon statistics. And in this case, since we're talking about qubit, I'm going to tell you a little bit of, you probably have heard about these things from entanglement perspective from Chris Monroe's and Michel Lukens and so on. But let me tell you a little bit of slightly different angle from a quantum sensing perspective. And you may find that interesting, that angle. Okay, so suppose this is a spin-half Hamiltonian, a spin-half system, which you can describe as a little block sphere, and it's pointing down or pointing up at the two quantum states, spin up and spin down. What you're doing in clock or EDM type of experiments is putting the quantum system in coherent superposition between ground state and excited state. And we know the ground state excited state has an energy difference, which is E. And all we are doing is to measure this phase factor in front of E. Because you put it in coherent superposition, excited state has a little energy larger than G. So the phase in front of excited state will evolve as E times T. That's what you're trying to do, right? You're putting this in coherent superposition and let it evolve and use a coherent laser to read this out. This evolution has a little bit of a quantum noise. That's because fundamentally, when you put something in coherent superposition, and before you make a measurement, you do not know whether this coherent superposition was in the ground state, excited state. This is the most, I would say, if you say, I understand everything about quantum mechanics, there's only one mystery. Well, that was the only mystery, like the measurement science, the fact that we do not know. And the system can be decoherent and so on, by coupling to the path. But fundamentally, this measurement process is whether we are. I wouldn't say we do not understand it. I just want to say there is still a lot of philosophical discussions about what that measurement process means. But experimentally, we know how to make those measurements. Oops. I was warned that if you push this too long, the screen will go dark. So now this goes to the so-called standard quantum model. The way to circumvent this noise, there are several different things to do to push on the measurement limit. One is, let's just make the spin as processing as many times as possible. That's the coherence I talked about. Making this pendulum go as fast as you can so that you can have lots of evolutions you can count. 1, 2, 3, 4, 5. And the very last evolution, you have this uncertainty. But if you had lots of these evolutions, you reduce that uncertainty. The other technique is to use many, many of the atoms. And this is the whole point of scaling up quantum system. Instead of using one atom, let's use a million. And if you can do that, if you can prepare them all identical, then you can reduce that noise as a 1 over square root of that measurement process. Well, there's one final trick. And this is the most exciting aspect of the trick in the modern era of quantum science that we are trying to take advantage of, this so-called entanglement. What entanglement is doing, it's actually very simple to explain in the sense that if I had two particles, and if they're strongly entangled, that means the noise, used to be when the particles were independent, when you were doing like this type of experiment, every time you switch, trying to measure the quantum state, there's uncertainty associated with this quantum pendulum, which is totally independent from the next pendulum and next pendulum. So therefore, there's n copies of noise in your system. But if you can have an entanglement, the story changes because it's almost as if you flip one spin, the noise is only one copy and the rest of the noise is non-existent because they're entangled. And that's the same entanglement you use to build a quantum computer, right? Because once you have it entangled, you have all these parallel processes going on to process information at the same time. But from quantum sensing perspective, this is exactly the advantage we are trying to take is by having having all the quantum systems to have identical quantum noise due to entanglement, such that when you make a measurement, you only have one copy of a noise, even though you have n copies of a signal. And that's the whole point of the so-called 1 over n Heisenberg uncertainty scaling. Okay, and another visually, too, you can think of as the spin projection noise used to be a big blob classical noise of the uncertainty principle. Now, because of n-particle entanglement, you can actually reduce the noise distributions on this equatorial plane as it evolves. So you can see it's a sharper needle to allow you to tell the time or spin precession in a better way. This is probably the most important slide, just because that connects the quantum sensing, quantum computing, and all the quantum networking. They're all in the same sort of a set of a technology. But it's also a slide which you can directly read off from quantum textbook. So it's not like nothing really fundamentally new, except that we can do this now in the laboratory. That is fundamentally new. So just to give you one slide about laser coherence, because in order to read out these quantum state, we need to have a very good classical technology. A laser is one of those. I'm calling laser classical technology, which is a little bit of a, I don't want to say that the laser itself builds on quantum physics, but it does not depend on, traditional laser does not depend on entanglement and so on. So if you want to say, I want to see a laser that can have a very long coherence time, well, you have to actually think about some engineering. I know Purdue is particularly strong in engineering, finding out new materials to build the optical interferometer. In this particular case, silicon crystal is used so they can enjoy the zero thermal expansion at particular temperatures with very high Young's modulus and high mechanical quality factors. You can build these new interferometers to stabilize your laser. And if you want to test how good the laser is, you can build two such systems. It's a collaboration between Jella, our lab, and the PTB, which is the German standards lab. And you can just hear, almost like putting two music folks together, hear the beat note. And we can hear the beat note between two lasers. How good is a beat note? Well, the beat note can be as narrow as just a few millihertz out of hundreds of terahertz. And that's the quality factor I was telling you about, 10 to the 16, 10 to the 17. And this technology can be translated into, suppose you're not as familiar with the coherence time, or maybe you're familiar with the coherence length. A laser like this will allow you to build microsecond interferometer between Earth and the Moon, for example. And you can have the photon go back and forth between Earth and the Moon 100 times. You will still see which fringe of a microsecond interferometer is sitting on. And with the frequency comb technology I mentioned very briefly, one stable laser allows you to transfer that coherence to anywhere in the visible spectrum, or actually into the infrared, into the extreme ultraviolet. So this technology allows you to essentially coherently synthesize an electromagnetic field anywhere in the visible spectrum. And so this is quite enabling, allowing you to connect optical waveform to the microwave form. But also, you build one stable laser. In principle, every lab, all the labs can have different colors of lasers and so on. They're all stabilized. So I want to tell you, this is on the light side. I'm going to focus my talk on the atom side. So as I mentioned, you can think about spin. This qubit is nothing but a two-level system, ground state and excited state. And one of the key things, the advances in our field has been control of the motional degrees of freedom. You have heard about this in trapped ions and in tweezer arrays. And here's in the rendition of the optical lattices, where you have just simple interference of laser beams forming these pancakes, like standing wave pancakes in the one-dimensional interferogram of the laser. And the atoms are cooled down to very, very low temperatures using laser cooling technology that you have heard also in this workshop. So these atoms are in the motional ground state, as indicated as harmonic traps, and their motional degrees of freedom are quantized, just as the internal degrees of freedom. So you have these internal spin degrees of freedom, motional degrees of freedom, which is usually to describe the Doppler shifts and so on. And when you talk about quantum state engineering, you really have to control everything, the entire degrees of freedoms of whatever quantum particle, quantum systems you're studying. And here shows example. If you can trap the atoms in a specially designed, engineered optical traps, you can actually decouple the spin degrees of freedom and the motional degrees of freedom, because the motional degrees of freedom have exactly identical trapping potentials. So as you evolve in the spin degrees of freedom, you don't really care whether the atoms are in different harmonic oscillator levels. Yes, that makes sense, right? That allows you to completely remove so-called Doppler effect. And this is a spectroscopy you can take out of the systems like this. This is so-called a carrier transition here. The carrier transition is, you're driving the spin degrees of freedom without changing the motional degrees of freedom at all. And you can see those very classical Rabi line shape, almost like a classical textbook. You can just calculate on Mathematica, and it exactly matches with the data, experimental data. Or you can think about well, where did the Doppler effect actually go? It went into this blue sideband in the sense that you can put a quanta into the system, motional quanta, and this sideband distance from the carrier exactly equals to the trap oscillation frequency. So the Doppler effect is still there. It's just quantized away in the reflection of the sidebands. So when you drive the clock transition, you are no longer bothered if the sidebands are far away from the carrier. You're no longer bothered by these sidebands, but the motional effects. And you notice that there's a little sideband on the red side called the red sideband. In principle, the red sideband should be completely gone because the motional ground state, there's nothing lower than the motional ground state. You cannot remove another quanta as you drive it. But there's something left, indicating this atom is not completely in the motional ground state. There's some fraction. And in fact, the asymmetry between this red sideband and blue sideband tells you the temperature of the quantum system. You can actually measure it and then cool this down. Later on, I will show you a slide where this is completely removed. So systems like this allow you to perform experiments where it's Doppler-free, where there's no photon recoil energy, and so on, and you can have lots of atoms contributing. But being able to say, well, I have created a trap, the trapping potential for the ground state and excited state to be exactly identical to allow you this decoupling between spin and emotional degrees of freedom is not given. You have to actually work for it. You have to go to the lab and actually search for that wavelength that allow you to work this out. And this is still at the forefront of research to identify the identicalness between these trapping potentials. For example, in the recent work, just even a little earlier this year, we were able to characterize this remaining uncertainty, the difference between the two trapping potential at the level of a few parts 10 to the 19 level. So now if I focus onto a single pancake in the middle, and now I have put, say, a dozen of those atoms in there, and I start to do the clock spectroscopy. As I explained earlier, you already know that there's a Block sphere, and this Block sphere is what lasers driving this spin evolution, putting them into the coherent superposition, and you see this classical noise, which is essentially representing that each spin when you flip, you don't know whether it's excited state or ground state. So this is the quantum uncertainty principle right there. If you let the system evolve, it turns out we build the system based on fermionic characters of these atoms, so that we know that when you have two fermions, you write down the wave function of two fermions, the total degrees of freedom has to be anti-symmetrized, because that's Fermi statistics, that's Pauli exclusion principle. That means that if the internal degrees of freedom, if the internal degrees of freedom is totally symmetrized, GE plus EG, that's a symmetrized spin, the motional degrees of freedom has to be anti-symmetrized. N1, N2 describes the transverse motional quanta of these particles that's moving around the transverse direction. The motion in the longitudinal direction, in the axial direction of this thin pancake, the motional degree of freedom is totally frozen. So this negative sign represents the Fermi statistics, and for some condensed matter physicists sitting in the audience, you will know this is so-called a P wave. That's the lowest order odd partial wave that we have to allow you to have a Fermi statistics to survive. So in this case, turns out these sort of a contact interaction, these atoms can rub, they can run into each other, have these contact van der Waals interactions. Those van der Waals interactions are not very sensitive to the motional quanta of N1, N2. So you can actually turn out, you can actually write a total spin. If you have N particles in there, each one has is 1/2 spin, the collective spin is nothing but N/2. And this interaction is actually collective that allow you to write down a Hamiltonian, which looks like the total spin projected along the z direction, and it has this interaction parameter chi in front of it. This SZ squared term allow you to do the so-called single axis twisting of the original, the quantum noise, which looks like that classically, but you can actually twist it to a degree where, due to these interactions, the noise that's above the equator gets pushed to the right. When NZ is below the equator, gets pushed to the left because it's SZ squared term. And that allows you to really create this non-classical looking noise distribution. If later on, you can, initially the noise looks like a sphere, but you stretched it. And if you were able to later on in your spectroscopy use the short axis to be the uncertainty, then you can see you can take advantage of that spin squeezing for your measurement enhancement. So this is the Hamiltonian we will actually use later. At the time, though, this is 10 years ago, 2013, we actually thought about, well, this process is going to create some uncertainties in the systematic shifts, the spin-spin interaction. We want to study clocks, but it turns out to be a spin Hamiltonian, and we want to understand the consequence of all the spin Hamiltonians on the clock accuracy. So we went ahead and tried to avoid this problem. How do you avoid this problem? At the time, we came up with the idea that, well, let's just, instead of building one-dimensional trap, let's do three-dimensional system where you're basically interfering three orthogonal directions of a laser beam, creating essentially a three-dimensional crystal. And if the atoms are cooled down to very low temperatures, you know the Pauli exclusion principle for fermions will guarantee one atom per site. And so you can have a system that has about 1 million atoms loaded into the 3D lattice. 100 by 100 by 100, that's not a too big a scale. I have to say this is actually still something we haven't achieved, but that's something you can think about engineering. You know, this is nothing preventing you if you have a bigger power lasers to get to that level. If you have coherence time, as I mentioned earlier, 120 seconds for the strontium, the spin coherence, you can actually build a clock at a second, reaching already 10 to minus 20. And we were very excited. This was a number we were deriving in 2016. We felt that was the year also LIGO just detected gravitational wave. And we found very inspirational looking at the LIGO success that one day we should be able to build a clock at this level of precision. If you average for 100 seconds, this precision goes to 10 to minus 21. And you can then use the clock directly to measure gravitational wave shift. You don't actually have to build interferometers anymore. You can just build 2 clocks and compare the time difference when the gravitational wave comes. The current record, we haven't got to that level, but the current record is now at its field parts 10 to the 18. And to just give you a little bit of a flavor, this kind of a quantum state engineering, remember we were worried about the interactions, but now the atoms are confined one by one in their own little house. And so this is a kind of nice. You can have a three-dimensional confinement, and you can see this is the so-called emotional sideband I mentioned earlier. The red sideband is not totally disappeared. So in all three directions, you have a quantization that's at the absolute bottom of the so-called ground band of this artificial crystal that we have created. So the atoms are cooled down to very low motional temperature, the ground low motional temperature. And then you can, in this case, we actually turned out we actually have a fermionic isotope with spin of 9.5. You can think of these different colors represents different nuclear spins. And what's really interesting about the system is the electronic angular momentum, J equals to 0. And if you think about hyperfine interaction, it's nothing but I dot J. It's about nuclear spin interacting with electron spin. But if the total electronic angular momentum is 0, you can have different nuclear spins like here, 10 different colors, but they're all going to interact or behave the same way. So, and this nuclear spin is kind of interesting as a label. You know, you can say, well, this ball, this atom looks blue, this atom looks green, this atom looks cyan, and that's because they have different nuclear spin states, which means they can make these atoms to be distinguishable. So you no longer have a Pauli exclusion principle if those are distinguishable particles. So that means if you have different colored atoms, they can actually occupy the same site as long as energy is allowed. And so what happens? What's the consequence of that? Well, you do spectroscopy, you'll find out if you have 2 atoms, their energy is separated from the main carrier when you have only 1 atom per site, and you have 2 of them. The reason because you have 2 of them is there's 2 ways of anti-symmetrize the wave function between 2 atoms. One is the electronic spin degrees of freedom to be symmetrized, the nuclear degrees of freedom to be anti-symmetrized, and vice versa, and you see 2 peaks. And it's interesting, right? You see only 2 peaks despite the fact that you can have 10 different colors. And it's telling you exactly this physics that called it. It's actually the SUN term that was coined in nuclear physics. In the nuclear particle physics, there's SUN symmetry. And we are enjoying that SUN symmetry that even though you have N different nuclear spin states, but all of them interact exactly symmetrically. In fact, we can put 3 atoms per side, 4 atoms per side, 5 atoms per side, and you'll always see 2 peaks. And that's because no matter how you orient or reconfigure how many nuclear spins, recombine them in the system, you always represent it as a symmetrization or anti-symmetrization states. That's why you always have 2 pairs of states. So it's interesting, right? In quantum systems like this, you're building clocks where you ended up studying magnetism in a condensed matter session, in a condensed matter kind of a sense. And you're starting to borrow ideas from nuclear physics and particle physics into quantum systems like that. We can also take images. I think somebody may have told you about taking very, very good high-resolution image. And when I said we can put 1 atom per side, some of you should be looking at me with suspicion. How can you prove that? But we can take a microscopic image and show that in the middle of the 3-dimensional crystal, indeed, this looks like a Mexican pyramid. The top is flat. And the reason why it's flat, well, you can only have 1 atom per side if the nuclear spin is totally polarized. And that's guaranteed by Pauli exclusion principle. So it's nice to see this directly. And then you can apply a field gradients to just test the technology of the imaging. You can apply, for example, a magnetic field gradient. And each atom will behave slightly differently because the magnetic field shifts the Asimian energy. And you can actually freeze this kind of a coherence between laser and atom into the distribution of the atom. Just take a picture of those and tell you exactly the field gradient is. You can also use this to kind of do clock comparison, like this half of the Mexican pyramid versus the right half of the Mexican pyramid. If you have a magnetic field gradient, I can actually measure, there's very high precision of what that field gradient is. It's because I can compare the clock here and the clock there. And this is a comparison that we cannot do at the level, this is showing the uncertainty of or the imprecision of the clock or instability of the clock as a function of the measurement time. You can go down to 10 to the minus 20, 10 to the minus 19 level. And this is actually a perfect time to tell you about clock comparison, because if you want to turn clock into a quantum sensor to measure dark matter, field distributions, and so on, you have to do clock comparison. So one way to do clock comparison is using a common laser to drive 2 atomic systems and putting them both into coherent superposition, and you directly compare atom versus atom without the lasers being involved. Laser only used to prepare the quantum coherence, and then you no longer use the laser as a laser atom coherence to probe the difference between the 2 atomic systems. This allows you to remove the noise of the laser, despite that we already have some of the best lasers, but it's not possible yet to realize the fully quantum mechanical coherence of 122nd kind of a coherence time with our current laser. The other more common clock comparison, of course, is actually more traditional, where you use separate local oscillators and you just measure the frequency ratios. I'm going to tell you a little bit of both. Maybe the first one is the second approach. I'm sorry again. Yeah. Okay, so the second approach, which is compare 2 different atomic species using different lasers, and to just show you this is a technology ready to go outside of the lab. My lab is actually in Jella, which is on CU campus. The campus looks as beautiful as the campus of Purdue. The Purdue is incredibly beautiful when I was walking over. But it's a pretty nice on Boulder campus as well. And we can send our clock signal, which is in the basement, through a fiber onto the top of the 10th floor in this building. And we can shoot a telescope, use a laser beam to shoot across 3 kilometers into another campus, which belongs to NIST. And they have atomic clocks there. So now we can actually use noise-canceled Airlink to compare clocks at the 10 to the minus 18 level. We also have the technology, the more traditional, which is just lay a piece of fiber underground, connecting those labs so you can compare between these different pathways. This free space link is really important. Imagine that I want to compare my clock against clock on Purdue campus. The way to do it is you send to the satellite, and the satellite comes down to Purdue. And in order to do that, you need to clear at least 10 kilometers of air. So if you can do this over a few kilometers, well, if you can push this technology a little further, you will be able to do 10 kilometer. Once you go through 10 kilometer, there's no more air. You're clear in the space with satellites. So that's pretty nice. When you can compare different atomic species, now here is a connection to the previous speaker about dark matter. That's because the different atomic species has different dependencies on fundamental constants like a fine structure constant. Suppose the dark matter exists we heard about dark matter could exist in field or in particles. In some sense, you can think of electron EDM search is trying to look for the particle mass. There's some unknown particle that CERN hasn't found yet, but the electron EDM is trying to place a limit on it. On the other hand, the field-like dark matter, which is essentially saying the mass of the dark matter is so light that you have abundance of the dark matter per mode, such that they can't be particles, they must be field, like Bose-Einstein condensation in the universe. And those fields are going to oscillate. If they have some coupling to the ordinary matter or ordinary field, it will cause the fundamental constant to change. Remember, fundamental constants governs the part of the physics we understand. It's coming from standard model. Dark matter is a part of physics we do not understand. And what we are trying to do, so-called search for dark matter, is nothing but trying to put an upper bound, at least at the moment, of this coupling between the unknown physics to the known physics. The coupling strength is what everybody is putting on the limit. Okay, and all everybody is doing right now is so-called exclusion limit, is to try to say in this particular mass range, you can see this is a very, very light mass, 10 to the minus 20, 10 to the minus 16 eV. But in this ultralight dark matter region, you can actually use atomic clocks because they have a different dependence on the fundamental constants. And if the clock is agreeing all the time, meaning fundamental constants is not changing. But suppose one day you will find out one atomic clock will evolve slightly different than the atomic clock, the other one. Then you will start to say, what's going on? First thing you should check is your systematics in your experiment. But if you keep checking and if you do coincidence measurements and you have a clock network and you start to see this existence of such signal that's verified and confirmed, then you start to say, well, I have discovered the dark matter. And that needs to be done very, very carefully, of course. Those are fundamental discoveries. But these are, at the moment, all the experiments are sort of setting the limit of if there exists dark matter in this energy range, what will be the maximum coupling strength you could have between the dark matter and ordinary matter or ordinary field. And this is so-called exclusion limit. And you can see the atomic clocks like that is setting the best exclusion limit for a particular range of dark matters. So let's talk about the first approach where I mentioned you can compare two clocks with a common laser. So here we started back in 2019, we used one laser to compare atomic clock in one-dimensional space, I mentioned earlier, or what's in three-dimensional space, three-dimensional crystal. With one laser, we can actually then, once you drive the atomic coherence, we can make a comparison between these two different systems and then let them evolve. And at the time, it's getting to the level of 10 to the minus 17. But this actually gave us the inspiration of building a completely new system. And I'm going to rush through this a little quick. How many more minutes do I have? A little over time already, okay. Give me like 2 minutes, 3 minutes. It's okay. I will try to be very fast, okay. So the idea was in the past, we built atomic clocks based on lattice, which is really deep. These atoms are confined in individual pancakes. They do not talk to each other. Each individual pancake can be thought of as independent. And based on the work that we did a few years ago, we start to think, well, maybe what we should do is actually make this pancake to be weaker and weaker and weaker to a point where they actually start to be so weak that this looks like the atomic wave functions start to be spreading out between these pancakes. It's a really interesting regime. If you remember in quantum mechanics, when you learned about periodical potentials, and somebody say, let's apply electrical field with electrons. Usually that's what your condensed matter system you do. When you apply electrical field, there's a potential energy difference called tilted lattice. And in the tilted lattice, there's already formalism to describe it. It's called a Wannier-Stark lattice. In a Wannier-Stark lattice, the wave function is no longer confined in a particular site, rather it's spread out. The wave function is actually spread out. So with this technology, remember that we have this magic wavelength where the ground state and excited state of the spin degrees of freedom enjoy the exactly same potential. Suddenly you have the capability of driving the transitions on the same site, which means that the clock transition is happening within the same site, or you're driving between the opposing sites, or even actually driving a coherent wave function between site 0 here and 20 sites off. It's a very weird quantum mechanical coherent superposition. The atom's in ground state here, and it being in excited state some 20 microns away, and it's evolving. Okay, and those are the systems we can now achieve. So you can have coherent superposition of both spin and emotional degrees of freedom simultaneously, and use this to actually sense the general relativity effects. What Einstein told us, if you have a clock here and a clock there, because of Earth has a space-time curvature, the time should evolve differently. And now we can put atoms in coherent superposition here and there simultaneously and try to see how the quantum mechanical wave function actually survive under the space-time curvature. This is actually something we are about to do. Because my time is limited, I'm rushing through this, but I just tell you, I won't tell you the details. The coherence is great. To telling you, 50 seconds later, we can still see the coherence between these two sites. And you can start to see gravitational redshift at the level of a few hundred micron difference when the two clocks are separated by a few hundred microns. And so the question I'd actually want to ask ourselves is about what if we continue along this path where the time is really, really soft, as Salvador Dali wrote this picture, painted this picture when he learned about relativity from Einstein 100 years ago. The idea being, well, there's no fixed time, right? The time is very soft. If I tell you, you move your clock by a few hundred microns, the time is different. Well, what if the measurement precision is so good such that on the scale of a quantum mechanical wave function, a couple microns where I can create a coherent superposition, time is different. But what if I create entanglement along this distance? How does entanglement evolve in the vertical direction versus in the horizontal direction? So these will be emerging phenomena. It's a linear physics, it's a linear gravity, it's not quantum gravity. I want to make that clarification. But it is now starting to probe how quantum mechanics, many body systems have new dynamics emerge due to the fact there's a gravity. So I'm going to stop here. I ran out of time. Sorry about that. I was going to tell you about spin entanglement, but I ran out of time. But it's actually a very exciting time. We can actually put a spin entanglement in the system and make comparisons. But I want to get to the very end, to kind of repeat this point that both the previous speaker and myself are making. Quantum science is giving us these new tools. And the clock I make, I never think of this as just a clock. I feel like I'm building a telescope because that will allow me to look at the gravitational waves in the dark matter search. I also feel like I'm actually building a microscope where you can look down on Earth and find out, well, what is the groundwater is migrating? What about Yellowstone, understanding different masses underflowing underneath the Yellowstone. Do we need to worry about one day it's going to erupt? But clock should be able to tell you the mass change because the gravity is going to give you the rise of the time difference. So some of the work you can see is actually quite interesting. This paper, for example, was a paper written between Misha Lukin and my group with the idea, very futuristic looking at a quantum network of these clocks sitting in the space. And this turns into this incredible interferometer that allows you to see these different phenomena in the universe. That's really the aspect of a telescope. I apologize for being delayed, but that's the end of my talk. Thank you very much.
All right, questions?
Thank you so much for very impressive accuracy and application.
Thank you.
Yeah, so my question about the electric dipole moment.
Yes.
If I go from an electron to anti-electron positron, do I still expect the same results?
Yeah, so there are that's very interesting. There are search going on, people to do so-called a CPT. What they want to do, for example, create an anti-hydrogen, where you have an anti-hydrogen, anti-electron and an anti-proton. And then you form this anti-hydrogen, and you study the spectroscopy and try to see whether there's a difference with hydrogen versus anti-hydrogen. Are they have the same exact Lyman transitions? And you can compare those in principle to very high order of precision. The question is, however, this is about CPT. If I completely change charge, parity, and time reversal, do I see something violated? And that's connected to the so-called local Lorentz invariance. You can actually probe whether remember Einstein mentioned that if you're in the elevator, the window closed, you couldn't tell whether you're inside the elevator or you're on Earth. That's the equivalence principle. But the equivalence principle is telling you, regardless of where you are, the physics should always be the same. And that's actually connected to CPT. I personally believe the CPT violation is extremely weak. So people are going on doing experiments like this. I don't think, theoretically, it's very well motivated. But CP violation, which is basically CP or T violation, is very strongly motivated. So your question about if I go to matter to antimatter and I try to see whether the physics is the same or not, that's really the CPT violation. Does that make sense?
Yeah, because we learned something about the positron, which is...
Absolutely, and the people do look at that. There's ongoing work going on at the CERN. People actually have this two different collaborations. They're forming anti-hydrogen, and they're trying to do the spectroscopy between hydrogen and anti-hydrogen.
Thanks, Chen, for the amazing talk.
Yeah.
Very quick question is for the gravitational wave detection, what is the time window you have to see the change between the two clocks? And that should be long enough for you to achieve that very high accuracy, because you need to measure long enough.
Yeah, this is actually a very, in some sense, the question that we struggled a lot, but now we have a very clear picture of if the technology can actually go to space, we think this is exactly what's happening is the following. In the LIGO, if you imagine the LIGO experiment, you ask yourself, what is the bandwidth of LIGO? Well, the LIGO has this 40-kilometer interferometer. The speed of light is known, so you can calculate what's the time it takes for the photon to go from one end to the other. That's the transit time. That is the bandwidth of the LIGO detector. It's the delay, photon delay time. And that bandwidth, as you know, LIGO is particularly sensitive at 10 hertz, because below 10 hertz, you have this vibration noise. The clock that you're asking, I was telling you this incredibly long quantum coherence time. And your question is very natural, saying, well, that means, if you say your coherence time is 120 seconds, does that mean that your bandwidth is really very low at a millihertz level? And that means that if the gravitational wave is happening, you will most likely miss it, because the Big Bang or something which is the two black holes collapsing, and LIGO were able to see it over a second or a couple tenths of a second's time scale, you have to wait 120 seconds. That means you will miss it. Yes or no? So what's really interesting is that information is no longer in this interferometer, but rather you are looking at the quantum coherence of an atom, which takes 120 seconds, as kind of a coherence time. You're storing that information in that quantum oscillator. And so in principle, you can say, I'm just going to do a Ramsey experiment, wait for 120 seconds. That bandwidth is a millihertz. So unless something is happening at a millihertz scale, you wouldn't be sensitive to it. But turns out, in between the two Ramsey pulses, you can actually, this is again, thanks to quantum technology, you can put lots of pulses in the middle. Okay, this is called a dynamic decoupling pulses. And what that means is, yes, your bandwidth is 1 millihertz, but your detection window can be at 1 millihertz, 10 millihertz, 100 millihertz, 1 hertz, 10 hertz. It all depends on, here's the two ends of my Ramsey pulse, which determines the bandwidth. But in the middle, I can put lots of pulses in there that allow you to tune the sensitivity. So So allow me to make this crude analogy. It's like you have built this, going back to the Weber, you build this resonator. The resonator has the finite bandwidth, but this resonator is tunable. It's like a tuning fork. We can actually tune the detection bandwidth to different locations of the detection window, even though the bandwidth is limited, but I can do very, very sensitive measurements at 10 millihertz, at 100 millihertz, at 1 hertz, and so on. So what kind of scenario would that apply? Well, suppose you have two neutron stars circulating. They are emitting gravitational waves all the time. In fact, the gravitational wave is chirped. Initially it's slow, and then it gets faster and faster, faster, boom, they collapse. LIGO detected only at the very last 1 second when they collapsed. When the two black holes finally merged, they saw this little thing. But in principle, detectors like this, if it's narrow band, but tunable, you should actually be able to listen to these black holes over long periods of time. It's like a music folk, you're tuning it in. And so this is actually quite exciting. And somebody even asked me, like, well, what's the limit of the clock kind of measurements? In the end, it will be limited by, there'll be too many of those black holes actually happening all the time, and there will be stochastic gravitational wave. That will be the end of building clocks. The universe is a lively concert hall, and your clock will be always listening to the gravitational waves.
All right, let's take our speaker one more time. All right, before you leave, we have 2 schedule updates. Luckily, lunch was already extended, so we have until 1:45 for lunch. Then afterwards, the panel discussion has been adjusted a little bit. So we're still respecting the original timetable, so we're ending, that panel discussion will end at 2:15, but the panel discussion will be slightly less formal. It'll be a chance for you to do your homework and to ask questions of a few experts that we'll have on hand. So we'll see you back here at 1:45.
People remember heartwarming ads, so bundle and save with Liberty Mutual. Oh, Graham, I love you. Only pay for what you need.
Liberty, 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 liberty.
Hi all. A bit of two small programming changes. So, considering the time consideration, we won't do a formal panel. And since you guys, a lot of you hadn't had the time to install the Quera system Blockade this morning, we're encouraging everyone to kind of go through the material, and we have our experts on hand. If you want to revisit the material from yesterday from Classic, feel free to playing around with them. We've got another 25 minutes until our next talk. So our experts are on hand. If you have questions, technical questions or career questions, formal questions you want to ask them, they are around and available for help. And also our second programming change is that the next talk from Professor Kaushik Roy, he has become unavailable today, but another professor, Anand Raghunathan, has stepped in. He'll be talking, his talk is titled Narrowing the Energy Efficiency Gap Between Artificial and Neural Intelligence. So just a heads up that our afternoon session will be a lot more machine learning heavy. So for those interested in those systems, that's our theme for the afternoon, sponsored by our Elmore Centers here at Purdue. Quick announcements. If you are an out-of-town visitor and you have already communicated prior with Tracy and our conference planner, Robert Ooms, about reimbursements, they need your W-9 at the signed W-9 out in the front. We are waiting on 5 of them that were already eligible, and then we're just confirmed that you will get reimbursement, but we not need those signed W-9. Turn in at the desk today. Tracy, Sandy will not be here tomorrow. Thank you.
Hey, no problem. That's always a good thing. So it's a different topic. We gotta protect this. And as you go through some yes. Hey, no problem. Looking forward to it.
Okay, everyone, please take your seat. Morris, maybe you should check outside. Good, good. I think it's this time after lunch where kind of people has dissipated a little bit into past lunch siesta or something. It's been really great with such a wonderful program for the first days and for the first half of today. This afternoon, it's my pleasure to welcome you to this half day that will highlight the research that's going on at the Elmer Frentis Research Center on Crossroads of Quantum and AI that is hosted by Elmer Family School of Electrical and Computer Engineering. So we are an umbrella of activities where we really want to merge two concurrently happening revolutions in quantum and AI. So I hope you would enjoy the variety of talks that we will feature this afternoon, ranging from classical machine learning to advanced computing scheme, brain-inspired computing, and other topics as well. So I'm extending my thanks to Thomas Roth, who put together the program for this part of the school, and I am turning it over to our moderator and the main person today, Morris Young.
Right. Thank you, Sasha. So our first speaker for this afternoon is Professor Anand Raghunathan, Professor Raghunathan directs the Integrated System Laboratory in the Almo Family School of Electrical and Computer Engineering at Purdue. His group's research spans various topics in VLSI and computer engineering, including system-on-chip design, domain-specific architecture, computing with nanoscale post-CMOS devices, and heterogeneous parallel computing. He's the Associate Director of the SRC DARPA Center for Brain-Inspired Computing and co-director of the Center for a Secure Microelectronic Ecosystem. Before joining Purdue, Anand was a senior researcher at NEC Laboratories in America and held a visiting position at the Department of Electrical Engineering, Princeton University. Here's Professor Raghunathan.
Thank you. Okay, looks like the audio is working, so that's great. And we are on with the slides as well. Get my pointer. Right. It's a pleasure to be here today. Welcome back after lunch, I guess. And thanks to the organizers. I was telling Sasha, I know how challenging it is to put together a program like this. And so, thanks to her and all her team of organizers for doing such a wonderful job. I looked at the program and, I'm glad I have this opportunity not just to present, but I'm hoping to take in some of the interesting talks today as well. So my talk is titled Narrowing the Energy Efficiency Gap Between Artificial and Natural Intelligence. So I'm standing in for Professor Roy, who's listed in the program. So while I can't give his talk, the talk that I will give will have some overlap and intersection with some of the topics he was going to talk about. So I'll try and not disappoint you if you're looking forward to hearing about some of his work. But just to give a little bit of additional context to my background and where a lot of this work is coming from, I've been fortunate to be part of two large-scale initiatives in this space of AI. Actually, these are vertical centers that go all the way from theory and algorithms down to hardware. My own background being more on the hardware side of things. First, as was mentioned, is the Center for Brain-Inspired Computing. This is a center funded by SRC and DARPA that has been led by Purdue for the last 5 years. We are ramping down, we'll be wrapping up this September. And we were fortunate to also have the opportunity to co-lead, and I'm the co-director for a newly launched center, also funded by SRC and DARPA as part of their Jump 2 center program called COCOSYS, Center for the Co-Design of Cognitive Systems. We are just getting started in this journey. So hopefully by the end of that time, it would have been a decade working in this space. And I certainly have learned a lot from this and hope to learn more as we continue this journey. So I'll be sharing some of the work. I do want to acknowledge, of course, my students, my collaborators from these centers, and the sponsors. So I'll start by talking about the virtuous cycle in AI. And you may have heard about this or may be familiar with it, so I'll try and go a little fast in the beginning. But I just want to make sure that we're all on the same page so we can all relate to what I'll be talking about in the second part of the talk, right? And so this virtuous cycle, or if you prefer a virtuous triangle, is really responsible for the amazing advances we have seen in AI over the past decade or more, right? And the components, the legs of this triangle are algorithms, hardware, and data, right? So advances in any one of these are driven by the other two. For example, we know that AI is not a new field, right? It's several decades old. Neural networks are also not new. Many of the concepts that led to the inflection, the revolution in deep learning in 2012 were known at least 1 or 2 decades before that. But why did they take off? Because of availability of data and availability of hardware or compute capacity coming together. And of course, once that enabled lots of applications and lots of interest, it also drove further advances in AI and ML algorithms. Similarly, if you look at the increase in algorithmic complexity, in the use of larger neural networks, for example, and larger data sets, that has certainly led to the demand for hardware and driven a lot of innovation in the design of new hardware platforms. And finally, combination of better algorithms and better hardware is what enables you to derive value from data. Raw data is not of much value, right? It's only the insights, actionable insights that you get from data that are of value. Much as it is good to celebrate this virtuous cycle, it is also important to recognize that improvements in all three aspects are critical to keep this AI party going. Okay. So let's look at each of those three aspects, right? on the data side, the amount of data available certainly continues to explode, right? We have, of course, a lot of this has been driven by the internet, right? So we look at these large language models today, where there's a lot of excitement around ChatGPT, GPT-4, and so on. They're enabled by the availability of internet-scale data. But the next explosion in data is really coming from instrumenting the physical world, right? Everything around us is being instrumented, and there is, new kinds of data being generated, but also the next wave in that tsunami of increased data is coming. The key challenge, again, is to make sense from all of that data, actionable insights. If you look at algorithms, the complexity of algorithms is also exploding, right? And this is because the progress in deep learning and AI and machine learning at large is really facilitated by more complex models and, of course, more data, but more complex models, specifically in the context of neural networks, means larger, deeper neural networks with more parameters. So in the context of computer vision and specifically image classification, right, this is the problem of telling what's the object in an image, right? This graph here plots the advances over the past decade or so, right? So AlexNet was kind of this major revolution in computer vision where a neural network method first overtook the classical methods, and since then it's basically been neural networks all the way. So the starting point on this graph is AlexNet, and if you look at the 11 years or so that have elapsed since then, we have improved the accuracy of image recognition as reflected by the ImageNet dataset. This is kind of one of the commonly used benchmarks to compare image classification algorithms. We see that we have for about a 20% improvement in accuracy, which is a big deal, but it comes at a cost of about 1000x in the size of the models and the number of operations you need to classify a single image. So 3 orders of magnitude increase in the compute demand for 20% in accuracy, right? And in fact, it is hypothesized that there is some sort of a power law, and the dots, here kind of follow that pattern with a very high exponent. So any further advances are also likely going to require substantial increases in computational complexity. This is even more drastic when you look at natural language processing and the large language models in particular, right? It's not been publicly disclosed how big GPT-4 is. It's rumored to be about a trillion parameters. But in this case, in just 4 years, there has been a factor of 5,000 increase in the sizes of these models, okay? So clearly that part is scaling. Perhaps if I were to identify the weakest leg of that triangle or weakest vertex, it's the hardware, okay? Because we know that improvements in semiconductor technology have been slowing, right? This plot on the top right is a very well-known graph that plots microprocessor performance over like several decades of Moore's law. And in particular, we see that around the mid-2000s when the so-called Dennard scaling stopped, right? This is when we were not able to scale the clock frequency anymore without the power density going through the roof. We see that what ended up happening is that improvements in clock frequency more or less flattened out, right? So we don't see processors with tens of gigahertz today. That's why. As a result, the single thread performance, which is the performance of hardware in executing a sequential series of computations, a sequential program, didn't quite flatline but drastically slowed down. Of course, we still continue to see increase in transistor density. So from a strict sense, yes, Moore's law does continue, but it's not very easy to translate that into improved performance, right? These days, performance comes from increased number of processor cores or increased parallelism. That benefits some applications, not necessarily others. In any case, so this is one way of depicting the slowdown in semiconductor technology-driven improvements. And this graph at the bottom right talks about the logic transistor density, and this is specifically from Intel. We know that they've, of course, had challenges in really keeping up with the cutting-edge state of the art. So you see that in the form of increased times between consecutive node shrinks, technology shrinks, and in this case, the other major semiconductor manufacturers, TSMC and Samsung, who have been able to push further along, right? This is all the way down to 5 nanometers. This plot here on the bottom right shows the incremental improvement you're getting in performance and power consumption for each technology generation relative to the previous one, okay? And so you see that this is a downward trend, which means that you get very little in terms of performance or power improvement with each following technology generation, or certainly those are diminishing improvements. And so something has to give, right? On the one hand, data complexity is increasing, algorithmic complexity is increasing, so the demand for compute is increasing. But at least hardware improvements driven by technology are slowing. So all of these things manifest in the form of what I refer to as the AI versus NI, artificial intelligence versus natural intelligence efficiency gap. Okay, so the successes in AI, have been like when we see the headlines, right? They're driven often by these man versus machine contests, right? And these are nothing new. We may be familiar with the recent ones, but they go back to the 90s when we had, actually even before that, with Othello, the game of Othello, but the chess program Deep Blue from IBM versus Garry Kasparov, the then reigning world champion, and then the Jeopardy champions versus IBM's Watson, and of course, more recently, Google's AlphaGo versus Lee Sedol, and there's many other human benchmarks where AI has surpassed human performance, like playing computer games and other more and more increasingly sophisticated and challenging tasks, right? And this is great, right? And this really reflects it's I think a small reflection of the huge advances we made in AI. But if you ask the question at what cost, and in particular, if we look at what is the energy cost of the natural intelligence, that is the human versus the AI. Of course, these are very different systems, right? But the human, if you look at the AI side of it first, IBM Deep Blue ran on a 32-node IBM server cluster, which is estimated to have consumed about 15,000 watts. The Watson program that competed in Jeopardy ran on a cluster of about 90 IBM servers and estimated to consume about 200 kilowatts, right? AlphaGo, initially when the version that competed against Sedol was actually trained on a network of 1,920 CPUs and 280 GPUs. Later on, of course, these days they have their own specialized hardware called TPUs or tensor processing units to drive it. But initially at the time, this is estimated also to have been not publicly known, but several hundreds of thousands of watts, right? So you have this, if you look at the fine print, the energy cost, power cost and energy cost of computation is growing substantially, radically, right? And that's how this gap between the compute demand and the hardware-driven improvements is actually manifesting. And so if you look at the NI side of things, of course, the brain is a very different kind of computing machine. It does not use electricity, it uses glucose, but it's estimated to consume about 20 watts. So we see about a 4 orders of magnitude difference here. And the point here is not to say that, to compare it just for the comparison's sake, but to point out that there is potentially huge applications and further advances that can be enabled if we make AI more energy efficient, right? What if we can narrow this gap, if not entirely bridge it? And so, on a lighter note, I'll say this is actually just a zoom out of that picture with IBM Watson represented here in the middle versus the Jeopardy champions, and you can see that Watson is winning. But if we change the game slightly, what if we change the game slightly and place a very reasonable constraint that all the contestants must entirely be in the room? Okay, Watson had to connect to this data center, which requires huge amounts of cooling. It's really, really noisy, right? That game would not have been possible anymore. But that's what we'd like to do, right? You'd like to fit that in your smartphone or maybe in a wearable device, right? So we don't need to look at these very high-end systems. Even if you look at very simple, or humans for that matter, if you look at very simple organisms, in nature, we see examples where biological systems possess a level of functionality and intelligence in particular that if you look at it relative to the computational cost is really unmatched in artificial systems today, right? So let's look at a much, much simpler example. This is the very humble, or maybe not so humble if you try to swat one, fruit fly, right? This is actually a video of showing the fruit fly reacting to a active attack, somebody trying to swat it and jumping off. And we know that there's existential proof that it's possible to create these flying machines that can navigate very cluttered environments, fly really fast, avoiding obstacles and so on. And we are still far away from that level of capabilities in artificial systems like UAVs. So this is one of our collaborators from the Seabrick Center, the UPenn, the GRASP lab at UPenn. And this is one of the smallest UAVs. They call it the Flying Monkey. It's just order of 100 grams in weight. And the compute on board here consumes about 1 to 2 watts versus microwatts for the fly's brain. Right? Again, that's the estimate for how much power the fly's brain consumes. So you see 6 orders of magnitude. Yet, I don't think we have any system here that can be as adept as a fly in terms of avoiding clutter, avoiding active attacks, and so on. Right? So that really is the challenge we are trying to solve. And how do we solve this challenge? I don't have time to talk about all the aspects of the efforts in our centers, but I'll try to focus on the hardware side of things, okay? And so this is a roadmap that shows where we are today, the current state of the art, where we use multi-core processors, GPUs, and specialized accelerators, digital accelerators like Google's TPU. In fact, most of your smartphones, probably if you purchased in the last few years, have an NPU, a neural processing unit, which is really a specialized processor that performs AI and ML or neural networks more efficiently. Okay? So we are already here. So this is where we are starting off, but how do we still bridge this 3 or 4 orders of magnitude gap in compute efficiency with natural intelligence? And I'll talk about some of these techniques, including approximate and stochastic hardware, in-memory computing, and neuro-inspired algorithm and hardware co-design in a moment. But maybe a little bit of background to make sure we all understand what some of these mean. First, let's start off with how we do deep learning today, right? And again, this is going to be a very, very high-level 10,000-foot overview, but just to make sure that you can relate to some of the things I talk about. So this is a cartoon that shows a neural network, right? You have layers of neurons. Each layer in this neural network, in this case, it is a fully connected neural network, which means every neuron talks to every other neuron in the next layer. If you look at one of the layers, right, you can look at the computation performed in this layer by looking at the values of the neurons at the input of the layer, the input neurons, or the activations, which are the values that those neurons compute or produce. And that's represented by this brown vector here, right? And in this case, that's of dimension k, it's a vector of length k. If it's a fully connected layer with k input neurons and n output neurons, the weights associated with these connections can be represented by a k by n matrix. And finally, the output activations values in the output neurons is also represented by a vector of length n. And so what you're doing here when you evaluate this network as a forward pass to evaluate it on a given input is at every layer you are performing a vector matrix multiplication. You take the input vector, multiply it with the matrix representing the weights, and you get the vector representing the values of the output neurons, and you keep doing, of course, what I'm not talking about is you typically have a nonlinearity, right, like a ReLU or a sigmoid or some sort of nonlinear function that you apply there, and then you keep repeating this, rinse and repeat until you get to the output, okay? So this is, in a very, very simplified sense, how it works. Of course, typically you may not always process one input at a time. Sometimes for computational efficiency, you batch together a set of inputs. So it's not vector matrix multiplication, but it becomes matrix multiplication. This is useful because you end up getting more reuse of the data you fetch from memory, and that's more and improves your computational efficiency, right? So it's either vector matrix or matrix multiplication at the crux. That's the key. And convolution, which is a method that is very commonly used in computer vision in particular, because it gives you spatial invariance, can also be reduced, I won't go into the details, through a process called lowering into essentially matrix multiplication, okay? So, you take, kind of the convolutional kernel and slide it around the different parts of your image or the volume here that you see, and each of those instances of convolution can be kind of strung out into like a row and a column respectively of these matrices, and again it becomes matrix multiplication. Okay. Of course, there's many further nuances and advances I'm not talking about. You can do this process just more efficiently by doing it in the frequency domain with FFT-based convolution. There's Vinograd convolution. You can approximate some of these, like these kernels, the weight matrices, using lower ranked matrices and get computational efficiency and so on. So there's a lot of that, further advances there, but this is the basic approach, and this is useful to know for what I'm going to be talking about. Okay, so if you did a profiling of how much time is spent on a GPU or a CPU of, when you're evaluating a neural network, right? 90 to 95% of the time is spent on those fully connected and convolution layers, essentially on matrix multiplications. Okay, and this is really what has led to GPUs and even digital accelerators being so good at machine learning or deep learning in particular, right? And the fact that everything is kind of boils down to this one simple to linear algebra, not even all of linear algebra, just matrix multiplication and convolution, because you can put all of your energy into optimizing this and doing this one thing really, really, really well. And that's what GPUs do well. It was actually a nice coincidence that GPUs were such a great fit for machine learning, right? And of course, with some of the digital accelerators, they're deliberately designed to have these matrix multiply units. Okay, so and then you have a very sophisticated software ecosystem that's evolved around that makes it really easy for even a middle school or a high school student to download a Python package on your laptop, and in a few days you're up and running developing neural network applications. So all of that is amazing, but that's where we are today. How do we get to the 2 or 3 orders of magnitude or 4 orders of magnitude improved computational efficiency that we were talking about? So the first step in this journey we'll talk about is approximate computing. Okay, approximate computing very, very broadly just refers to performing the computations involved in anything. In this case, neural networks and machine learning in an approximate manner, right? Not precisely. And this is really a marriage made in heaven. A lot of the work, foundational work here in applying approximate computing to neural networks in particular was done right here at Purdue. It's a huge field right now. And so this, the reason I claim that this is a match made in heaven is that machine learning itself, intrinsically, the task you're doing, which is learning from a few examples of data, you're trying to fit an unknown function. That itself is an act of approximation. The whole thing you're trying to do, the whole task. Okay? And so, since you are the whole, and in fact, this is the very well-known classical result from machine learning called the universal approximation theorem, which basically says that if you neural network with one hidden layer, as long as that is arbitrarily wide, can actually arbitrarily approximate any function, right? And so a lot of the from a conceptual perspective, a lot of these advances rely on this. And so the question is, it's natural to explore whether the computations involved in evaluating the neural network, right? Those matrix multiplications and even those other computations can themselves be performed approximately. Do you need to perform them very precisely? Traditionally, 2012 and before, right? Most of the computations in neural networks, they were performed on CPUs or GPUs, but they were all using mostly single precision floating point computation, okay? Because that's what was present in the hardware, right? So just reuse what is present in the hardware, do that. However, that is overkill. For machine learning, it has turned out, and neural networks in particular, that you can do with far, far lesser precision. And so one specific form, perhaps the most widely used form of approximation, is called quantization. And again, you may be familiar with this. It's just the use of fewer number of bits to represent the weights or those activations that you're processing. It reduces the storage cost. I need to store less data. It reduces the computational cost because the arithmetic operations on smaller bit widths of data are of lower complexity. So I'm going to be able to fit more in a given area or a given power budget and improve my performance as well. So this is a whole plethora of number representations that have been explored, both fixed point and floating point of lower bit width. And these graphs down here actually show how you are able to improve your relative energy and area when going from a 32-bit floating point, like a multiplication or addition, down to 8 bits in this case, right? And you see that you can get literally a couple of orders of magnitude improvement, 1+ order of magnitude improvement here by just quantizing. And you see this quite universally today. Modern hardware uses 16-bit floating point for training typically, and 8-bit integer representations for inference. By and large, there are some special cases where the needs may vary, but the vast majority of neural networks use this reduced precision. There is active research going on, and this is a roadmap from IBM. Actually, we had some very early work in 2014 right here at Purdue, introducing a concept of trained quantization, where you quantize the values in the neural network and retrain to recover the accuracy. That kind of has enabled a lot of this. But if you see this roadmap from IBM in particular, it shows that they are pushing even below 8 bits. They're looking at as low as 2 bits for inference. And they have shown 8-bit floating point training, and more recently, a hybrid of 8 and 4 bits. As you try to push closer and closer to the limits, you got to get more sophisticated in how you do the quantization. You may need to mix and match different precisions for different computations in the neural network and so on, but it is possible to extract a little more juice than where we are today. In the short term, I definitely expect this will be one source of improved efficiency. The other kind of approximation that has been explored is called pruning. This is kind of orthogonal or complementary to quantization in a sense. And what this is saying is that if you start off with a neural network, again looking at this cartoon where you have every neuron connected to every other neuron in each layer, the question is, do we need all of these connections, right? Certainly what has been shown is that during training, you may need lots of neurons and parameters, but after you have trained the network, it is possible to get rid of most of them. Okay, there's a lot of redundancy in some sense in there. And one way you can get rid of them is to prune the so-called synaptic connections, or the connections between neurons. And you can see here that you have a sparse connectivity. And in some cases also get rid of some neurons as well, right? And again, you want to do this by retraining, and you keep using training to ensure that you're preserving accuracy as you get rid of the neurons. And so this distribution here is showing that one way of doing pruning is by looking at the distribution of weight values and looking at all the weights that have small magnitude and just getting rid of them. Okay, that's what this is done. So this is another very popular approach. One challenge here is that the computations now, if you look at those layer computations, are no longer that regular matrix multiplication. It becomes irregular. It's a sparse matrix multiplication, which is much more challenging to realize with high efficiency because it's not regular anymore. Yet another way of performing approximation or approximate computing for neural networks is to approximate the hardware itself. And this is yet another, I would say, orthogonal dimension, and these can be combined to get even higher improvements in efficiency. And again, this was actually introduced here at Purdue by my group and Professor Roy's group here. And so I'll illustrate this notion of approximate hardware using a very, very simple example, right? If you've taken a VLSI course, one of the basic circuits you'll build is full adders, right? And so if you look at a textbook, this is a very classical circuit used to implement a full adder. It's a CMOS circuit with 24 transistors. And the question we asked is, if we don't need to be precisely adding, if 10 plus 10 need not always be 20, if it can be 19 or 21, if I'm allowed to do that, then you can actually simplify the circuit quite a bit. Okay? And in this case in particular, what we did was we kind of arbitrarily said we got rid of a bunch of these transistors. We got rid of 8 transistors. Of course, you don't want to introduce short circuits or have floating outputs. So there are some rules that govern how you can do this. It's not as easy as it may appear at first, but assuming that you take care of all of those things, this is an approximate adder. It's going to be slightly different functionally from the classical adder. And you can, by removing different combinations of transistors, you can come up with many variants of such adders. And functionally, this is a truth table, which on the left shows the classical adder function, right, with inputs A, B, and C, the carry in. And these are the inputs to the adder, and these are 3 different approximations. And the red cells show you where the outputs differ or they are erroneous, right? But these are deliberately introduced errors with an aim to simplify the circuit, right? So here we have simplified the circuit by 33%. It's 33% lower power, smaller, it also is faster, right? It's good on all those dimensions. And using these approximate hardware units as building blocks when you're creating machine learning hardware can lead to further improvements in compute efficiency, okay, beyond quantization and pruning. And this has actually become a very active field of research these days with lots of efforts all the way from the circuit level to the architecture level and algorithmic level. So I won't have time to go into it. Okay, so we've taken one step, which is, I would say, kind of the first near-term step to improving computing efficiency for AI over the current state of the art. And let's see how we can push it even further. If you look at modern computing systems, and including AI accelerators, all of them are subject to the so-called memory access or von Neumann bottleneck. This arises because of the fact that memory access, especially off-chip memory access, is 1 to 3 orders of magnitude higher than computing operations that you perform, especially when the computing operations are simple like multiply and accumulate. So this graph here from Mark Horowitz at Stanford shows the cost, in this case the energy cost, normalized energy cost of compute operations, add and multiply at various bit widths, various precisions, versus memory access. In the case of memory access, you have a few different scenarios where the memory access is happening on chip from a 32 kilobyte SRAM, which is right next to your processing unit, to all the way where you have to go to DRAM to fetch the data. But in all the cases, you see that the memory energy is much higher than the compute energy, and it can be as high as 3 orders of magnitude or more higher than compute energy, especially when you go off chip to DRAM, right? And what this means is that this really limits the performance of, I would say, all computing systems, including AI hardware. This graph here shows that if you have a power limit of about 60 watts, and why do you have a power limit? Because DRAM, it is volatile, right? And the reason DRAM loses data is because of leakage. Leakage grows exponentially with temperature. So you need to control the temperatures. You need to have a certain power budget with DRAM. So if you assume that 60 watts is about your power budget, this shows essentially a trade-off between the per bit access energy of the DRAM and the memory system bandwidth. And HBM2, which is kind of the state of the art in off-chip interfaces to off-chip memory systems, gives you about 2 terabytes per second here in terms of the bandwidth, but we need much more than that. Okay? Accelerators help by exploiting the computational patterns, and in particular the data access and the data reuse patterns that are present in these neural networks. Okay, they help by ensuring that you don't hit this worst case of DRAM access very often, that as often as possible, by exploiting locality, you keep the data that you need close to the computing units. If you do that, it helps a little bit, but it still does not entirely solve the problem, because once, especially after you quantize and you use these low precision computations, the cost of the compute is still much, much lower than the cost of memory access. The memory access bottleneck remains. This is a very famous plot called the roof line plot, which actually shows whether the different computations and the different dots here, different colors, actually represent different types of neural networks. So there is a diversity even among those the neural workloads. For each of them, it shows on the x-axis you have the operational intensity, which means once I bring a piece of data to a processing unit, how many operations am I performing on it? The flops or ops per byte. And on the y-axis, you have the throughput, which is the gigaflops per second. And so this part, the first part, which is shown by the straight line here, is the part of this regime is memory bound, right? Which means that your system is limited by the DRAM bandwidth, and if it's above this part, you're operating at peak compute performance, and so you're compute bound. And what we see here is that many of these, the recommendation models or the sparse length sum, which is also used in many neural network workloads, is actually very, very memory bound. Okay. So a natural question to ask is, can we not bring memory and compute closer to each other? And yes, you can do that. That is the natural solution, and in-memory computing is kind of the eventual culmination of that solution. But a short-term approach is near-memory computing, for example, using 2.5 or 3D type of integration to bring the compute and memory closer to each other. Sometimes it may mean, rather than having them on the same substrate where you need to go horizontally for a longer distance, can you bring them closer to each other so you have a higher bandwidth of connectivity plus shorter distances? And that's what we're already doing with some of these 2.5D and 3D solutions. But in the research context, we are looking at the next step of that, which is in-memory computing. Can I take the computations and directly embed them within the memory arrays themselves? Okay. Traditionally, we think of memory as just, I'm going to store some data in the memory, I'm going to read it back later, and in the meantime, I want the data to be there, right? So memory does not actually perform any computation, but here, the idea is that when I access the memory array, rather than just reading it out, can I directly perform a computation within the memory array and read out the result of that computation, as opposed to the inputs themselves? So this is a very active area of research. So our center has been focusing a lot on this, and I would say in the broader community, there's been a lot of interest in this space. There's many. This is a taxonomy. You could classify the approaches to in-memory computing based on the underlying device technology. CMOS-based, silicon CMOS-based versus beyond CMOS devices such as non-volatile memories and NVMs in particular. You'll be hearing from Professor Gupta about ferroelectric FETs. They have some unique properties that make them especially suitable for in-memory computing. Digital versus analog, it turns out that when you want to perform efficient in-memory computing, you need to perform analog computations essentially on the bit lines in these memories. And finally, whether you're performing the in-memory computing in the context of a general purpose memory hierarchy versus as a dedicated accelerator. So I'll give you just a little bit of flavor of this. So this picture for one kind of in-memory computing. So this picture on top here should be familiar. I introduced this. This is a vector multiplied by a matrix. So input neurons times the weights gives you the output, right? That's one layer of a neural network. This very naturally maps to this crossbar structure. In this case, the crossbar structure has these elements which are essentially programmable resistors, right? Any memoristive technology could be used to realize this, including spintronic, phase change memory, or ReRAM, to name a few. And so the idea here is one way of realizing this is that you take the inputs and encode them as voltages that are applied at the rows of the crossbar. You take the weights and program them into the conductances of these resistive elements. And you look at the currents that come out of the columns. And if you look at the currents that come out of the columns as a byproduct of basic Ohm's law and Kirchhoff's current law, right, you will see that these currents coming out at the columns of the crossbar are nothing but the dot product of the inputs and each column of the weights programmed into each column of the crossbar. And so essentially what you're doing effectively is this output vector represents the dot product of the input vector with the weight matrix. So you are simply by applying voltages and measuring the currents that come out of the crossbar, performing vector matrix multiplication in a very native way in the analog domain. Okay? This is not the only way of performing in-memory computing, but this is a very popular approach, especially when you're using NVM devices, and lots of commercial interest in this space, right? Academic interest, of course, a lot of research here at Purdue and elsewhere in our center, but also startups and large companies and national labs looking at this. So once you have that basic building block, right, which is a crossbar array which performs vector matrix multiplication, you need to enclose it in some peripherals, right? Because you can't just connect these crossbars together. It's not going to work very well. You'll have noise propagation or amplification, and it won't work very well. And so what you need to do is essentially have these digital peripherals around the crossbar that take digital inputs, convert them to analog voltages in this example, apply them to the crossbar shown in the middle here, and then digitize the outputs. And so that then you can communicate the values to another crossbar tile digitally. Of course, in addition to the vector matrix multiplication, you may need digital logic to perform the other computations, right? Like the ReLU or batch normalization and so on and so forth. One challenge when you do this, though, is you'll see that this pie chart here shows the breakup of the power consumption of this crossbar tile among the various subcomponents, and you'll see that ADCs, like conversion from analog to digital and digital to analog, basically kills you. Okay, this is a major challenge in this area, and a lot of research is really trying to address that bottleneck. Okay, but still, it is possible to do this, and once you have this as a building block, you can then kind of hierarchically compose this building block to form very large, high-performance neural network accelerators or AI hardware. So this is an example where these resistive crossbar tiles have been arranged in the form of a so-called systolic array, where data flows from inputs from left to right, and the outputs come out vertically. And then you have this whole crossbar-based processing tile, which you can then compose, in this case, using a ring structure shown here to form an accelerator that then can be used alongside like a CPU, just like you would use a GPU or a TPU today. So in this whole process, I mentioned it's an active area of research. Some of the critical design choices are how you encode the inputs and the weights. I gave one example of an encoding scheme where the voltages on the rows represent the inputs, and the actual resistance values programmed in represent the weights. That's not the only possibility. You could represent the inputs as a stream of pulses, for example, or in a pulse width modulated format, for instance. And each of those choices has implications on the energy efficiency, the time taken to compute, and so on and so forth, and the complexity of the peripheral circuits varies as well. Then once you have the circuit design choices nailed down, you also need to make the architectural choices. How do you hierarchically, this is one example of how to hierarchically organize these crossbar-based systems, but that's not the only way. There may be different ways of doing it. And you need to, how do you interconnect, the choices made to interconnect the different elements at each level of the hierarchy, right? So these are challenges, but I do want to mention that this is not, just a concept. These are examples of actual chips taped out in our center, some from Purdue, some from our partners, and many in collaboration with industries such as Samsung and TSMC. Initially, in our first years, we have single macros that implemented one of those crossbar processing tiles with the peripherals, and in more recent years, we have shown complete systems which are self-contained neural network accelerators using crossbars. For example, here's one from Georgia Tech that actually shows an ARM embedded processor in here, two SRAM banks for temporarily storing the activation data. These are just kind of scratchpad buffers, and the four corners here are actually 4 banks of crossbar tiles, and in all we have 288 RRAM-based crossbar tiles. This is taped out on TSMC's 40 nanometer RRAM technology, and this particular chip actually is the highest effective RRAM density reported to date, with over 3x improvements on the previous state of the art and over 50 tera operations per watt as the compute efficiency. So that's the next step, in-memory computing, right? Let's see how we're doing on time. Do I need to wrap up? I probably need to wrap up, right? 2 minutes? Okay, I will, thank you. Okay, the last part, and I'm glad you gave me a little bit of time because we need to get to the part that Kaushik was going to talk about. So this is neuro-inspired, let me go back, neuro-inspired algorithm and hardware co-design. Okay, I won't be able to do justice to this in a short period of time, but I'll try to give you some sense of the kinds of approaches we are taking. So here the idea is, well, we know that there's this gap, huge 4 order of magnitude gap between artificial intelligence and natural intelligence. What are the principles, the key principles we can try to abstract out from biological intelligence, right, biological systems, and incorporate to actually improve AI systems. Here is one example of such an effort from our collaborator, Jim DiCarlo's group at MIT. He's a computational neuroscientist. So what you see at the bottom here is a monkey which has implanted electrodes in its visual cortex performing object recognition tasks. So the monkey is seeing various images. As it is recognizing those images, its neural activity is being recorded at the bottom here. Right? The same images can be presented to an artificial neural network that also performs image recognition of those same images. And the internal values of those neurons, right, of the artificial neural network can also be recorded. And in Jim's group, what they did was by statistically trying to correlate the internal representations as well as the final results from both the artificial neural network and the biological system, they compute a metric called a brain score. Right? This brain score essentially tells you how similar, from an information perspective, this artificial neural network is to the biological system. And by using this brain score, this is actually it's open source. You can check it out at brainscore.org. It's a great resource for bringing together the neuroscience and ML communities. But one of the key outcomes is that they found is that they could create networks which were much, much smaller and much more compact, and therefore required far fewer parameters, much less computation, that would give you performance accuracy comparable to the state-of-the-art deep neural networks, but with like 1/10 or 1/50th the parameters and the compute complexity. Okay? So that's one example of how brain-inspired computing can help. I'll just give you one more and then we can conclude. So this is the other direction that we are pursuing. And when we talk of neuromorphic or brain-inspired computing, many people immediately think of spike-based computing. And that's not the only type. There's I give the other example just to say that there's different ways you can approach brain-inspired computing. So in spiking neural networks, you still have that artificial neural network structure, but each neuron is not a multiply accumulate. It's processing a strain of binary spikes. So the inputs are all binary, and that leads to a reduction in the complexity of this neuron. But then computation is performed over several time steps. So it's kind of like a space-time trade-off. And there's been a lot of chips, and these are just some of them, reported in the literature in like past decade or so, but there's been very limited adoption, despite impressive power efficiency in these chips. And this is my last slide, I'll conclude with this. Some of the challenges with spike-based computing are that the latency of computation is very, very high. So these are very, very slow, because I need to process over many, many time steps. It can be like order of 1,000 time steps to process a single image, okay? If you want high accuracy especially. And it's not very energy efficient, although the power numbers are very impressive. Remember, energy is power multiplied by time. So when you look at it from an energy point of view, it's not very competitive with GPUs or digital accelerators. There's a huge gap in accuracy between ANNs and SNNs, especially for applications like image classification or computer vision applications that ANNs are already good at. Okay? And so that was a big question, right, to use these chips. First, show me that you can be accurate, right? Then we'll consider this. But so, and we, in addition to answering some of these questions, we also went beyond this and answered questions like, are there applications that are better suited to SNNs, right? The whole community was trying to use SNNs for applications that ANNs were already good at, which was not the right way of using them. But this intrinsic temporal nature means that SNNs can capture temporal behavior, where the input is not a static image, but it is a time series or there is some temporal dependencies. Those can be captured much better with SNNs. So we have a whole bunch of research that I won't be going to the details of, unfortunately, but I'm going to be around and happy to talk to you offline, which starts off with converting ANNs, trained ANNs to SNNs, so that we could take advantage of all the training algorithms and show that SNNs can match the accuracy of ANNs, and then subsequently looking at problems that intrinsically leverage the temporal dynamics of SNNs, and then also looking at hybrid SNN and ANN systems. So why don't I stop here and conclude? So in summary, this is kind of the roadmap that we envision from short term to long term, right? With approximate computing, really continuing to drive immediate improvements in efficiency, followed by in-memory computing, and then, kind of longer term would be neuro-inspired hardware design. So the takeaways I'd like to leave you with: continued improvements in AI compute efficiency are going to be essential, right? You will not see the next decade of improvements in AI be like the past decade unless the hardware efficiency, compute efficiency continues, okay? It's absolutely essential, and we need to do this with, despite slowing improvements from technology, semiconductor technology. The past decade has really been enabled by accelerators, GPUs, and digital accelerators. In the near term, I think continued advances through approximate computing, as well as advanced packaging and heterogeneous integration to enable near-memory compute are going to help. But beyond that, we really need to look at in-memory computing and neuro-inspired algorithm hardware design. With that, I'd like to thank you. Apologize for going over a little bit, but happy to take any questions.
All right, we'll open the floor up to questions.
Thanks very much. This is very interesting. This is out of curiosity. Maybe you can, I'm not an expert in machine learning, but if you can give us some context of how these large language models now with like emergent properties, right? Like you do 10 to the 20 flops, nothing, 21, nothing, 22, 23, suddenly you got a lot, right, of improvement. Yeah. It's not like 1,000 times and for 20% improvement. It's like a factor of 10 there makes total difference. So can you...
Yeah, so there are these inflection points, right? We saw the inflection point in computer vision as well, right? Because there were consistent improvements in hardware technology, in the 80s, 90s, and 2000s. But in 2012, that's when the GPU performance got to a point where they could train these convolutional networks. Like AlexNet was the first, from Jeff Hinton's group. In a reasonable time, right? Within a human patience limit, right? As a grad student, you're willing to wait, maybe a day or a few days or a week. If you say you need to wait for a month, and if it doesn't work, you need to repeat the experiment. That's kind of beyond the patience limit, right? So there's that inflection point where it suddenly becomes feasible, right? And so I think we've seen those inflection points, to answer your question, not just in language models, but in other aspects of machine learning as well. And so I think what you're referring to is that aspect of, there are these sudden jumps in capabilities that are enabled when the compute performance reaches a certain threshold. You go past a threshold.
And you can also complexify things, right? Like first, one order of magnitude doesn't change it, right? You need to go that large, and then complexifying can't. It's not gonna. You need a lot of compute to get past the inflection point. Right?
Correct. And one of the models potentially that going forward, and that might. People are, speculating is that there will be the so-called foundation model. So not everybody will be able to, right? Not every research lab or academic group will be able to train a GPT-4. And there's some issues with that. I think personally it needs to be democratized. But one way forward is that a few entities will be able to train them, including maybe some open source entities, and there are such. And that they make those foundation models available. And the vast majority of users or even researchers would just customize those models, build off of that, right? So you don't need the huge compute infrastructure that a Google or Microsoft or OpenAI has access to. Yeah.
It's not that much a question, but rather provocative comment. So you made a very good point that brains use by far less energy to process information compared to any system. There is opinion, and it's actually some publication, although it's not really dominant opinion, but there are some people who believe that brains actually operate in a quantum way. They use things like entanglement, superposition. If that's true, that could explain actually this enormous energy efficiency.
Thank you for bringing that up. I actually, given more time, I would have tried to make more of a connection, with the quantum aspect, because I think that there is some fascinating connections there. We don't know much about the brain. First, we have to say that, right? There's been like 12 Nobel Prizes in neuroscience, but we still know very little about the brain. So I think that's the reason we make sure that we use the term brain-inspired rather than, neuromimetic or trying to copy it, right? Because you can't copy it unless you know what it is. So having said that, I think it probably, using quantum, and there is obviously this whole field of quantum machine learning, but the one comment I'll make is that I think it really requires rethinking the algorithms, right? It's not easy to take, especially if you look at inference, right? It's just a bunch of matrix multiplications. That's probably not the right computational model for a quantum computer, right? I mean, it doesn't take advantage of those natural advantages you have. However, quantum annealing, right? We already know, like, D-wave-like systems. I mean, that's one of the reasons, I guess, Google is interested in that is that for the optimization process of neural network training, right, it could be useful. I think, but the real advantages are going to come in when the algorithms really evolve to a point where they actually take advantage of the hardware properties, right, of quantum machines. And frankly, even with analog computing, right, the in-memory computing, it may seem to be a straight fit, but it is not, because you have noise. Any analog machine, that's the reason today we don't have large analog computers. There's lots of noise that comes from the hardware. The algorithms have to tolerate that noise, right? And so some of our work, actually has shown both the problem and some ways to possibly address it, but that's still an open challenge, right? So I think, yes, one will have to rethink the algorithms in the context of quantum computing and what it could do. But that's definitely a very promising direction. If we want to go beyond, I would put it in the roadmap I had, it's kind of beyond those 3 steps. Yeah.
All right, let's thank our speaker again, and we'll get prepped for our next talk. All right, for our next talk, before a brief break, is a presentation by Professor Joy Wang. Professor Joy Wang is an assistant professor of the Elmore Family School of Electrical and Computer Engineering and the Weldon School of Biomedical Engineering at Purdue University. She obtained her PhD from University of Pittsburgh in 2019, and her advisor was Professor Heng Wang. Prior to this, she received her bachelor's in bioinformatics from Zhejiang University in 2013. Her research focuses on machine learning and biomedical data science here.
You're on there. Yeah, you're on there. Oh, okay. Oh, now it works. Okay, hello everyone. Thank you, Maurice, for the introduction. So my name is Joy Wang. I'm an assistant professor at Purdue CE. Very happy to be here today to introduce our work. So previously we had the talk from Professor Raghunathan about improving AI efficiency from hardware and computer perspective. So for our work, we are on the algorithmic decision perspective. So we are working on machine learning algorithms, and we want to address another concern, which is spurious correlation. Oh, and before I go into our talk, I'd like to give a quick shout out to Sasha, Thomas, and also everyone on the organizing team for making this wonderful summer school come true. So this is a really great opportunity for students, researchers, everyone to be together to brainstorm, discuss, and learn from each other. Thank you so much. And then let's start our discussion. So nowadays we see artificial intelligence like machine learning like everywhere. So we have seen like machine learning models used to do 3D protein structure prediction, and also we can use machine learning models for quantum device design optimization. And also starting from last year, end of last year, we saw the development of ChatGPT by OpenAI, which has been like a hit nowadays. So for machine learning models, when we build the models, let's take a quick overview about the rough process of how do we build a model. So when we build machine learning models, roughly speaking, we will need data and model. So the rough idea is we will first collect a bunch of training samples, and then the data samples we use will reflect the problem we want to work on. And then we will fit the data into the model. And then we will build a model from different structures to fit the data we have. And then we want the model to approximate the data well, so that it can be flexible enough to approximate well to the training data for the problem we want to work on. And also at the same time, we want the model not to memorize the training data, but also to have some ability to do predictions for unseen scenarios, meaning that we want the model to generalize well enough to unseen data that was not used in the training process. So this is the idea of machine learning, and we use this process to build a lot of powerful tools that we use in nowadays AI. Okay? But the thing is, like for machine learning models, as we see, the model performance is largely dependent on the data we collect. But in practice, we don't actually have perfect data. So for the data, we have different types of problems, but if we have problematic data, then the model we build on the data might be also problematic. So one of the concerns we see, and it's very common concern, is spurious correlation. So for example, here is a study showing the analysis of two types of variables. One is the total revenue of casino in the US, a study over years. And then another is the number of biology doctoral degree awarded. And we can see that the numbers in those two variables are highly correlated across years. But it doesn't mean that if we award more biology degrees, then we will have a higher total revenue in casino, or the opposite. So they are highly correlated, but none of them is the causal effect of the other. And also in practice, when we collect data, say for image data, we also see things like this. So when we work on a study of bird type discovery, like identification, so it's more likely that we can capture images of land birds in the background of land, and also the word birds in the background of water. But it doesn't mean that if we put the same bird and change its background from water to land, then the bird type itself will change. It's not like that. So it's just that the background of the water versus land and the bird type itself is highly correlated, but it doesn't mean that the background will change the bird type. So this is another type of spurious correlation we see. And also we see such spurious correlation in healthcare. So for example, we are talking about melanoma prediction. So melanoma is a type of skin cancer, which is about the moles we see on our skin. And then we want to use the image to predict if the mole we see in the image is benign, is normal, or is cancer, is melanoma. And then there are studies showing that for the images we collected, for the skin cancer, for the malignant samples, they are more likely to come with skin markings, like in vivo markings. Those are made by doctors, and then the markings are just like, so you can use a pen to draw the markings, and it's just used for measurement purpose because we want to draw the markings and then to measure the size and the shape of the mole. But it doesn't mean this mole will be malignant or benign. But since the data we collected will have more melanomas come with the skin markings, and also much more samples to be malignant, to be normal without such markings. And we can see that there's also a high correlation between the existence of such in vivo markings versus the type of whether it's normal or it's cancer of the mole we are talking about. So with the existence of such spurious correlation in the data, if we train the model on such data with spurious correlation, machine learning models can actually take on such spurious correlations to make the prediction and inference. So meaning that if we apply a machine learning model on the image data, the bird image data we're talking about, Then if the model saw that the bird is in the water background, then it is more likely that the model will predict this bird to be a water bird, regardless of its type. And also, similarly, if we use such data with high spurious correlation between the skin marking versus the mode type to machine learning model, then if there's a skin marking in the image, then the model is more likely to predict that it's skin cancer. This is melanoma, no matter what type of mole we are talking about here. So the use of spurious correlation in machine learning prediction is really risky from two folds. The first one is it may affect the performance of machine learning a lot. Say if we train a model using such spurious correlation, and then if we apply that model to a data without such spurious correlation, then the model will fail. Okay? And the second thing is, like, even though in the spurious correlation, the model may seem to give us good accuracy, but the correct prediction is based on the wrong information. It's based on the spurious correlation. So meaning that the model can make right prediction, but based on the wrong information. Because for us human beings, we will never make the prediction of melanoma or not based on the skin markings. It's based on the shape and size and the intrinsic property of the model itself. So these are the things we want to address. And in today's discussion, I'd like to discuss this problem from two folds. The first one is how do we identify such spurious correlation in machine learning? And the second is if there are spurious correlation taken on by the machine learning model, how can we address that? So the first one is about detection of spurious correlation. There are a lot of studies about this. I will introduce one of the type using explanation methods. So nowadays, as we see, we use machine learning models to be more and more complicated, larger and larger size, more and more parameters. Most of the models we are using are black boxes. So black boxes are the models usually give us predictions but rarely explain. So here is an example to just showcase, to clarify what does explanation versus prediction mean. So here is an example of image classification. The task of a model is just to predict what the people are doing in the image. So for a powerful but black box deep learning model, it will give us the prediction showing the action. For example, those two people, they are brushing their teeth, and this person is cutting trees. But it doesn't actually explain why the prediction is made. But we can use explanation methods to see why the predictions are made in this way. So explanations, one of the formats will be in the heat map. So the heat map will highlight the areas of interest, showing that these are the areas where the model are focusing on. So meaning that the model are focusing on these regions when the model makes brushing teeth prediction. And the explanation can be obtained by various types of methods. And then we can actually use such explanations to detect the spurious correlation. So back to our melanoma prediction example. So we can see that for the same image, if we add some skin markings just on purpose, and then take a look at the explanation of the model, then we can see that the model tends to focus more on the skin markings rather than the mole itself, meaning that the model is actually taking on such spurious correlation and using the existence of skin markings to make the prediction. And then this is how we detect whether or not the model used the spurious correlation or information we don't actually want to make the prediction. And then once we see that we detect or hypothesis there might be spurious correlations, then we can take on actions to address that. So here I'd like to briefly introduce three types of methods like we propose to address this. So the first type is about balancing data. So back to our water bird, land bird example. So for here, the spurious correlation is happening because of the imbalance in the data size. So meaning that when in the collected image data, we have much more samples of the land bird in the land background and water bird in the water background. And we have much fewer samples in the opposite combination. Then if we use such imbalanced data to do the prediction to fit the model will actually focus more on the majority because we are using the average of prediction errors. So the model tends to focus more on the majority combination compared with the minority ones. So one way to address this is we can balance the data. So suppose we can add more images from the opposite combination, the minority combination, meaning that if we can have more samples of land bird in the water background or water bird in the land background, and then if we have a roughly balanced distribution of the samples, then that will be a good way to address spurious correlation. To add more samples, we actually have multiple ways. So one way, most straightforward, is upsampling. So upsampling just means for the minority combinations, we use the samples multiple times. We make multiple copies of them. For example, for here, we have 180-ish samples, and then for each of the samples, we use them 20 times. And then we will be roughly having like 3,000 samples for this combination, and then that will be a way to balance the data. So that's the first way. And then also we can add a little bit further variation to the data. So when we are doing upsampling for the minority group, rather than just making the exact copy of them, we can make more variations using data augmentation. So data augmentation, for example, for image data, includes geometric transformation. So we can rotate the image, make a crop, or change the distortion, or add some Gaussian noise, things like that. So meaning that for the original image, by applying different type of transformation, we can get, so for here we get 9 different variations. And then meaning that for the original image, we get actually 10 copies of them. And each copy, they are not the same as each other, but they are coming from the same image and with more variety. And then using this data augmentation perspective, we can add more samples to the image, to the data, and then provide some more balanced data for training. So that's about the data augmentation perspective. And the third way we can do is if we can collect more samples. So this is actually the way that will be the best for performance, because we are having more real data collected. So, and then if we can have more real data collected to balance the data, that's the best for machine learning performance. But this may not be the most efficient one, because in reality, collecting data may not be an easy work. So for this bird image, it might be easy, because now like last month, we just saw the great creation by Meta AI about segment anything. So you can actually take the image, apply that, and then segment the bird and apply it to any background you like. And then you can use that to create a more balanced data. And also for but for other cases, for example, if we are talking about batch effect or the like spurious correlation related to the data source. For example, we are talking about data coming from different cohorts or data source. And then it's likely that for different cohorts, the distribution of data may not be always the same. So we may likely to have positive samples from one cohort and more negative samples from the other cohort. And then the model will likely take on such spurious correlation between whether it's a negative or positive versus the data, like data source. But if we want to get more samples from those data source, it may be expensive, time-consuming, and sometimes not accessible. Then here comes to our fourth strategy, to use generative models. So for generative models, what we do is more like to use a computational tool to mimic the third type. So we want to get more samples, but instead of just collecting them, like due to the constraints, we want to use a generative AI model to create more samples that looks realistic, and then add those samples to the data set to balance them. And this is one of the approach we propose. So we use a generative model to do such counterfactual generations. So meaning that, for example, here is a bird image. Then we want to create its counterfactual examples, meaning that if this bird were a land bird instead of water bird, what does this bird look like? Or if this bird were in a land background rather than a water background, what would this bird look like? So we can use this generative model to create the counterfactual examples, and then we can use this to create like a perfect balanced data, because we can train a powerful generative model. We can create synthetic data as balanced as we need. And then we can use the balanced data to train the model. And then using the balanced data can help us to address the spurious correlation. So this is the first strategy we propose. And then we will talk about the second strategy, which is difficulty-based sampling. So still, we will use this example a lot. So for this Lambert Waterbird like image example, if we take a look at the setting, so previously we have data labels. So meaning that for each individual sample, like each individual bird image, we have the label showing that whether or not this is a land bird or water bird. For the bird type image, it's not too hard, but for some other cases, labeling of data is very expensive and time consuming. Then what if we are looking at the data that do not have labels? So for example, applied to here, it means that we collect a bunch of bird images, but we don't have annotation or labels about what type of bird they are. So we just know that some of them are from the land background and some of them are from the water background. But they're actually like high spurious correlation because we in the image, even though we don't know the bird type, but there are actually, for the true label, there are actually a lot of land birds in the land background. So how can we address that? So without labels, if we revisit the strategy we proposed before, they are not that applicable for all of the 4 strategies. This is because if we take a look at it, like say upsampling, data augmentation, crack samples, or generative models, all of them are based on the labels, because we need the labels to know that which are the samples we want to upsample or what type of samples we want to generate so that we can balance the data. But currently we don't have label information, then we just don't know where the imbalance come from. So how can we address this? This is the second question we wanted to discuss. In order to address the spurious correlation without label, what we do is we use a machine learning model called contrastive learning. And contrastive learning provides a powerful tool for self-supervised learning. And the idea of contrastive learning is to learn a representation that has very good classification power, but the learning process itself does not require label. So what contrastive learning do is to learn a representation such that we will have, for the same image, for the given image, we call that as anchor. We will distinguish between 2 types of images. One type is called positive samples, the other is negative samples. So positive samples are actually the data augmentation from the anchor image. So for here is a crop of the original image. And then you can apply any like affine transformation we discussed before. And then positive image means the image augmented by the original one. So they are coming from the same image, that's definitely the same class. And then for the negative samples, we just use everything else. So everything else are taken as negative images. And then we want to build a representation such that in the latent space learned, the positive samples will be more close to the anchor, and all the negative samples, they will be far away from the anchor. And this is a way of contrastive learning to learn such latent representation without labels. And then from the structure perspective, we can see that contrastive learning try to learn. So we can use MLPs, multi-layer perception, CNN, or transformer, or any structure that we need, and to learn representations, such that, for example, for the same image, among the 2 augmentations, they are treated as the same class. But samples from the other image, they are treated as different classes. So for samples from different images, we want them to repel from each other. We want them to be far away from each other. And then for samples from the same image, the positive images, we want them to be close together. So this is the idea of contrastive learning, and this is actually what we take on for addressing our second challenge, addressing spurious correlation without labels. And for here, but contrastive learning is powerful for providing classification power, but it will not be super powerful in addressing the spurious correlation. So this is what we want to do. So we want to address 2 types of bias. One is among the hard negatives versus easy negatives. The second is true versus false negatives. So a quick idea of what does this mean will be, for example, if we take an anchor image, suppose the anchor image is coming from the bird type in the water background. And then we will have different types of hard negatives, different types of negative samples. So for the land bird in the land background, they are easy negatives, meaning that they are easy to be classified as negatives because for this land bird from the land background, they are from the different bird type and also different background. So they are very easy to be distinguished from the anchor. But for the other type of negatives is land bird in the water background. So this is a true negative because this is a different bird type. But for the land bird, but in the water background, they are actually having the same background as the anchor, then the model is likely to treat them to be similar. So we want to distinguish more from the anchor versus the hard negatives compared with the easy negatives, because hard negatives are the more important ones we need to address for the spurious correlation. And then the second type of bias we want to address is true versus false negatives. So for the contrastive learning nature, we just take anything augmented by anchor as positives and everything else as negatives. And among the negatives, there are actually false negatives. So for example, for here, still the same anchor, the water bird in the water background, we will have false negatives which are water bird in the land background. So they are actually the bird of the same type. So the two images, they are actually from the same class, but the only difference is their background. But because of the nature of contrastive learning, the model will take this as a negative, but this is a false negative. But everything else in the above, they are actually true negatives. So we want the model to learn representation to focus on the true negatives, meaning that we want the model to do the distinguishment of bird more from the bird type, like from the bird type shown here, rather than from the background, like left versus right shown here. So those are the two types of bias we want to address, and the model we propose will be like this. So we learned two contrastive learning frameworks. The first one is for amplifying bias. So we first learn a bias amplifier, so that this model will be based on contrastive learning, and then they will want to amplify the bias, not only from hard versus easy negatives, but also from true versus false negatives. So we want the model to be as biased as possible and takes on as much as possible spurious correlation. And then based on this, we will get a model to be super biased. And then for this model, we can take a look at the model performance of the samples. And then for the samples that does not work well in the amplified bias model, then these are the samples we actually should focus on. Then we take a look at the samples shown by the amplified bias model, and then we add more weights when we are training the true contrastive learning model shown here. So meaning that we want to focus more on the samples that are not treated well in the like super bias model. And then we want to use the amplified bias model to provide the weights to guide us how to learn the true model we want to use here, which is to address the spurious correlation. So this is the second problem we address. So how can we address the spurious correlation with limited or even no access to label information? So the third type is about knowledge distillation. So it's another scenario and another model we propose for addressing spurious correlation. And for the discussion shown here, we will discuss a specific problem in machine learning, which is fairness. So fairness is commonly observed in real-world scenarios when we apply the models to high-stake areas like healthcare, job recruiting, like criminal justice, things like that. And models have been seen to have gender, race, age bias, and those are very concerning and important problems we want to address. And the reason model makes such biased prediction is because when the model is making prediction, they actually take on the spurious correlation between the predicted outcome versus the demographic information of people, like age, race, bias, like gender, geographic location, things like that. And this is what we want to address. And for this problem, we take on another challenge. So it's in reality, when we say we want to address fairness in machine learning, we usually require demographic information, like the age, race, gender information of the person we want to analyze. But in reality, due to law or regulatory or private concerns, it's often not applicable. It's really hard to get access to such demographic information. So meaning that we want to build a fair model, but we don't really have information to their demographic information. So in other words, we want to build a model to address such spurious correlation, but we don't actually have the information of their group information. And then also in reality, we want to build a model not only to address one type of bias. For example, we don't want a model just to address gender bias, but it will be super biased in like racial groups. We want a model to be overall fair, and then this is also another challenge we want to address. So existing works for addressing this are from either minimax problem or surrogate sensitive attributes, but they are usually very strict in terms of the constraints. So for our proposed method, we take on this problem by using a very new different perspective, which is knowledge distillation. So our idea is inspired by a preliminary results, a very simple experiment, but very insightful results. So let me explain to you what does this mean. So we are talking about a data set for adult data set. So adult data set is coming from the US Census data collected in 1994. And then the data we use is to, so for this adult data, the task is to predict if a person's annual income exceeds a certain threshold. So existing in the threshold, usually set as 50,000 will be a positive. Below the threshold will be set as a negative sample. And people found that in this prediction of the annual income, there are actually a very high race and gender bias. And we want to address this. And then we think what may make the spurious correlation, or what can we do to address the disparity. So one thing we think and we tested will be label smoothing. So if we take a look at the data set itself, so usually the case is the data is binary labeled. So meaning that it's just positive, which is labeled as 1, negative is just labeled as 0. But among the positive and negative samples, the label itself doesn't actually tell us the level of positivity or level of negativity in the data. So for example, we may have people whose annual income to exceed this threshold, but by different level. But all of them, they are just labeled as 1. So all of them are just labeled as positive. So we don't have a way to show how positive they are, like the level of positivity. And similarly for the negative samples. So we think if it's possible to provide such soft label information, so we use a continuous value rather than just discrete value, like 0 versus 1, to showcase the label of the person of interest. And then what we do is to use the data itself to provide the soft label. So we are doing the classification problem, but now the classification target, the label is no longer binary. So it's no longer 0 or 1 labels, it's continuous values. Continuous values like between 0 and 1. So higher than 0.5 values means positive, but the level of like beyond 0.5 shows how positive they are. And similarly for the negative samples. And then this is all we do. We apply this like soft label data to prediction and then apply a normal logistic regression to this test. And then we can see that the fairness of the problem got improved compared with a baseline. So we like evaluated that based on 2 statistical metrics. One is called disparity impact, the other is equalized odds. So both are popularly used metrics for fairness in machine learning. And for here, the lower the values, the better. And then we can see that if we use soft labels, actually the row 2, 3, and 4, they are different types of doing soft labels. And all of them can give us like improved results, especially the last 2 in terms of fairness. So showing that label smoothing actually address a disparity and also address the problem of spurious correlation. But the problem is that in reality, we don't actually have the soft label available. So usually the case is we may collect data from domain experts, and the data is already there. So it's either labeled as positive or negative. Then it's really hard for us to maybe go back to the domain expert and say, hey, can you provide me a little more information, and then can you give us a continuous value rather than a discrete value? Then what can we do? Like computational perspective, what we do is use knowledge distillation. So we use a model to learn the soft labels rather than referring to like troubling the domain experts again. So what we do is we first build a teacher model to like learn from the label, from the data with binary labels. And then the teacher model is just built as normal, and then the target is binary, like 0 versus 1. And then we want the teacher model to be complex and powerful enough to fit the data. And then the teacher model will actually give us soft labels, because for any model, we can do softmax prediction, and then the output will be a continuous value. And the continuous value shows the predicate probability of the label. And this is a label we can use. And then we can use the soft label to build a student model. And the student model is the one we are actually going to use. So the student model will just learn from the soft label provided by the teacher model. And then we can build a student model that is not trained on hard labels, but they are trained on soft labels. And then we show that this perspective actually gives us a way to address fairness. And we explore different types of soft label functions like softmax, linear, and then analyze the difference between them. And then we can see that the method works is actually because we assign the correct weights on the samples. So as we discussed before, when we are doing sampling, when we want to do data balancing to address spurious correlation, so we usually focus on the samples from minority group, and we also want to focus more on the hard samples. And this is actually what the model is doing. So the model actually correctly assigned higher weights to the samples that are harder to be predicted. And meaning that the samples are more likely to be mistaken by the model. We assign more weights to that so let the model know that you must need to focus on the sample and make correct prediction for that. So this is the reason that the model works, and we have some theoretical analysis to show the connection between the model versus like fairness metrics to show why it can effectively address this. So this is a rough idea of what we did, and this is a quick summary of our discussion here. So our discussion here is no way from like inclusive, but more likely I want that to serve as an introduction purpose so that we can introduce the spurious correlation, a very important and concerning problem when we apply machine learning modeling in practice. So hopefully in when we are applying or developing machine learning models for the problem we are interested in, we will be like thinking about the spurious correlation and then think about how can we identify and also address the spurious correlation so that we can make the model to make the right prediction based on the right information. Yep, so that's all, and I would like to thank my amazing students, like our sponsors, like Elmo Center, NSF, and also our wonderful collaborations, because none of them can be made true without their great support and collaboration. So that's all for today, and I'll be open to any questions or comments.
All right, I'll open the floor up to any questions.
In your slide on label smoothing, I may have missed it, but can you go over how the metrics for disparate impact and what was the other one, equality odds?
Mm-hmm.
Can you go over how those are measured?
So the definition of these two metrics. Yeah, so for disparity impact, it measures the disparity of the positive predicted rate between two sensitive groups. So the reason we focus on positive prediction is because we are talking about cases where positive prediction means favorable labels, like getting admitted or getting approved for a certain application type of things. And also for equalized odds, it talks about both true positive rate and true negative rate. So means that we want to calculate the disparity of the average of true positive rate and true negative rate between two groups. Yeah.
Any other questions?
Thank you for the talk. Could you please give some intuition on, in the last part, why the teacher models would give higher score or weights to the minority samples?
Yeah, so that's a good point. So just to clarify, for teacher model, we don't use that to address spurious correlation. So teacher model just so the purpose of teacher model is just to provide the soft labels. So teacher model can be biased, but they can learn from the binary label and provide the soft labels. And we want the student model to be debiased so that they can learn from the soft label and inspired by the preliminary results, soft labels can actually address the disparity.
All right, if there's no other questions, let's thank our speaker again. And we'll take a quick 15-minute break, and afterward we have 3 final short series of lectures before we... Yes, we get a 5 minutes break. Get a stretch of your legs, and then we'll get through our last 3 discussions here before dinner.
just want to find my laser pointer. There it is. There's a little lag, but I guess that's fine.
All right, here we're gonna get rolling here. So our first of the last 3 sets of talk for today is by Professor Christopher Brinton. So Professor Chris Brinton is an associate professor of ECE in the Elmore Family School of Electrical and Computer Engineering at Purdue University. His research is at the intersection of networking and machine learning. His group develops data-driven optimization methodologies for communications and social networks, with particular emphasis on distributed edge intelligence. They investigate including fog computing system, the Internet of Things, and social learning networks. Without further ado, Professor Brinton.
Thank you. Well, thank you so much for having me. And I also appreciate the promotion to associate professor in the introduction. I'll let the primary committee know we won't need to be doing any voting on that next year. So I'm going to talk to you today about some of my work in really rethinking some of the ways that we do communications with AI and machine learning. And so this communications that I'm talking about is primarily thinking wireless communications, but I think there are certainly many ways to extend this. It's what's being done in the quantum space, and it's one of the reasons why I'm very excited to be a part of the quantum center that we have in the Elmore Family School of Electrical and Computer Engineering, and very happy to be here today. So I'm going to talk about, I don't know how far I'm going to get, frankly, into both of these different topics because they're both reasonably long, but I'm more than happy to chat afterwards. They're two of my favorite topics. One is in robust coding design and actually developing code books for the ways that we communicate, point-to-point channels. And another one is on a heterogeneous federated learning. So it's more of a way of optimizing machine learning delivery over networks. And the first one is about using machine learning to optimize networks. Okay, so when we're talking about AI and ML and communications, right? Today we have billions of connected devices, billions of Internet of Things devices, and it's constantly growing. In fact, the amount of data is increasing exponentially, literally exponentially. Like if you fit it to a curve, it's an exponential growth. I'm not just exaggerating it. And that's obviously fueling advances in AI and machine learning. When you have more data, you have the ability to train much more complex models and do a lot of really cool, awesome things. ChatGPT, for example. So what is that leading to in the communications realm? One is advanced edge capabilities, or at least a desire to have advanced capabilities at the edge in our handheld devices. This is a principal objective of next generation access. We have 5G here now. It's going to be in 2028 to 2030, it's going to move to 6G. After that, it's going to move to 7G, then 8G probably, and 9G, and then, I don't know. But it'll keep going up. And so one of the aspects of these wireless communication technologies is the ability to deliver these really intelligent services, like wearable health analytics, right? Anybody who has a smart tracking device like I do, augmented reality, virtual reality, smart manufacturing, right? These are all AI and ML driven innovations. They're also very data intensive, very latency sensitive applications, right? They require processing a lot of data, because data is coming in so quickly. And at the same time, often in contrast with that, we need to make decisions very fast on the fly. Like if you think about self-driving cars, the amount of data they have to process to make decisions is really quite amazing, right? When you think about it. So how do we deal with all of that demand? And then on the other hand, it's more of communication protocols driven by AI and machine learning. So this is really more of how do we use networks to deliver and get AI and machine learning to people. This is more about, okay, well, what's the benefit to the networks themselves, right, for the AI and machine learning? How can we innovate and enhance the way communications work using an AI and ML? And there's two broad categories of innovations being looked at here. One is really re-examining some of the existing protocols that have existed for a long time. You know, for how do we send information over a channel? How do we estimate channel conditions? How do we estimate the amount of interference on the channel? All the way up to a much higher layer type function like congestion control. How do we control the amount of congestion that's being placed on the internet at a given time? So there's a lot of work going on in looking at how to use AI and ML to really think about these much more from a data-driven approach. And then AI and ML is leading to new network paradigms, massive multiple input, multiple output systems. That's one of the key 6G and beyond innovations that's going to be or should be largely driven by AI and ML, intelligent reflecting services, and certainly many types of quantum communication systems that will be a part of this sort of merging of quantum with wireless and AI and machine learning. So one of the things that we tend to look at in my research group is efficient ways of delivering machine learning over network systems. The sort of standard way of doing that today is a technology or technique called federated learning, federated machine learning. And in federated learning is actually rather simple. Okay? What it says is if I have a network of devices, they could be drones, they could be cars, they could be smartphones, whatever they happen to be, right? And if they're connected upstream to a server, this kind of a connectivity of pretty simple, what we call a star topology, because if you put them all in a circle around the middle node, it would look like a star. Those devices have the data that we want to train the machine learning on. The traditional way of doing it would be to have them all send their data up to the server and have the server crank out some really sophisticated deep learning model, or even before deep learning was available, some really powerful, more general machine learning model, and then send it back to the devices so that they can use it to do whatever they're doing. There's a couple problems with that. One is privacy. Okay? Anytime you send data over a wireless communication channel, it's possible that it's going to get intercepted by an adversarial threat. It's possible that somebody else that you don't want to see having the data is going to get access to that data. So we'd rather not send the data if we could. Second problem is communication efficiency, right? Data is so large, right? The amount of data that we have to be sending is so large that going back to that idea about having this be latency sensitive, really being able to make decisions in near real time, we'd rather not be sending data up. So the idea of federated learning is instead of doing that, let's have the devices train their own local models, okay, on their own data. They're going to execute these gradient descent iterations to train their local models. And then the server instead is going to receive their models, not their data, and aggregate them, literally take an average of them, and then send them back. And we'll continue this in iterative refinement. Okay? So that has a lot of advantages, particularly when you have devices that are capable of performing those gradient iterations, and when you have some type of statistical similarity amongst the data sets. Because if all the data sets are completely different, then if you're training them all individually without knowledge of the other one, like all the devices would be, in that case, they're all going to be overfit to their own local distributions, right? So that's also a bad thing, right? So the more dissimilar the data sets are, the more frequently we have to do the synchronization, Another problem is think about how large these models are that we're talking about, right? I mean, I'm not saying that you take ChatGPT and try to have that be trained on individual like your phone. Training ChatGPT, that'd be pretty crazy. But just think of a few layer neural network. How many parameters are in there, right? Quite a lot, quite a lot. I mean, you're getting into tens, hundreds of thousands of parameters. You know, so your phone doing that, you know, that takes a lot of energy, right? It takes time. And it takes a lot of energy to send it back, right? The models are becoming large too now. So these are some of the aspects that motivate my work in what we call fog learning. Getting towards fog learning is trying to do distributed machine learning over these distributed architectures. First of all, they don't always match this star topology, right? I mean, think about how many devices, IoT devices there are. If I have 1 billion IoT devices all connected to one server, and I look at the network that way, that's a whole lot of bandwidth going up to that server that's to be used, right? In reality, the network is much more hierarchical, right? It probably looks something more like this, right? You have edge devices connected to maybe unmanned aerial vehicles, remote service unit, base stations, right? Depending upon what sort of service area we're talking about wirelessly. They get connected up to edge servers. Edge servers are then connected through a backhaul to cloud servers, right? So you have a whole large, very large hierarchy. So the network is not, by any means, a star topology. It's a hierarchical structure. So that's one key challenge to federated learning. Another one is what I was mentioning, heterogeneity in resources and the statistics. And the third one, as we get talking about the actual communication protocols themselves, is proximities between different wireless devices. So if I have to be communicating information over wireless networks, the distance between the devices will matter. And as they start moving around more, that'll increase or decrease the efficiency of those transmissions. Okay? So my research is very much about, as I've mentioned, this interrelationship, right? A symbiotic relationship between fog learning, or fog and edge computing. Fog computing is like looking at edge computing, but over a hierarchical structure from the edge to the cloud. Call it the fog, it's in between. And AI and ML. Okay, so fog, edge computing provides a scalable training and inference substrate for AI and machine learning. Then AI and machine learning in turn provides learning-based protocol optimizations to fog and edge computing. Then we can refine the models, more AI and ML, provide better models, train them better, provide a better fog edge computing structure, right? So that's the idea. Okay, so this is just a bit about my research process that we look at in this domain. Tends to span theory and practice. So we go all the way from looking at fundamental relationships between how fog computing configurations, model training performance, wireless resource utilization are all intertwined for given structures, and really understanding how even new nodes as they come online, what is their expected benefit to the learning process that we're trying to execute. Once we have those relationships, right, using them somehow to do an adaptive orchestration of fog learning, adapting all the way down from the device and wireless level to, talking about how many data points should I sample and use locally to do my model update, to when and how should I actually transmit my updated model over the network and who should receive it, all the way up to the cloud level decision making. The cloud itself trying to orchestrate different time scales, when the learning process takes place, so on. Okay, so there's 4 main design principles behind fog learning that I'd like to point out. One is device to device, D to D. Okay, before 5G, most communication was focused on device to server, upstream, downstream communications. With 5G and beyond, we have a lot more device to device or machine to machine direct communications. So how can we use D to D for data sharing, and local synchronization of models. Rather than having to send all the way up to the server and have that do the orchestration, send it back down, can we do some kind of stuff locally, right? This can apply in commercial setting. It can apply amongst our phones here if we all turn our privacy restrictions off, I guess, right? I don't know. But I'm a lot of times thinking when I'm saying that about more defense-oriented settings, like Department of Defense, right? Setting out a set of drones to do a surveillance reconnaissance mission. They're communicating directly through device-to-device communications. They may not be able to go back to the base station. If it's compromised, whatever else, we may want the communication to be as local as possible. Another one is let's distribute both, so it's related to this, let's distribute both the ML updating process. That's something that was done by federated learning. Federated learning said, let's distribute the update process, but let's keep the aggregation process centralized. Federated learning is a distributed update process, but a centralized aggregation process. In fog learning, we have both being distributed, both the update process and the aggregation process being distributed. Another one is that we have a whole continuum of update frequencies. The edge is going to interact locally much faster than it's going to go up to the cloud and do the synchronization. This is going to occur at a much broader, much coarser time scale. Okay? You're talking even milliseconds, seconds levels here. This might be, hours or something, depending upon how frequently your training does have to occur. At the same time, the learning that's occurring here is limited in the sense that you don't have in any one of these local partitions, you don't have a global view of everything. So if you have a threat emerge here or some change emerge here, that may not get propagated through quickly. So the most robust learning is going to still happen at the cloud level, but the most fine granular learning will happen down here. And finally, integrating protocols for resource allocation and ML training. Can you remind me when this talk started? I just want to make sure I don't go way over time. When was the start of mine? 3:50? So I'm already 25 minutes in? All right, I'm already 20 minutes in? Okay, I'll try to end in like 15 minutes. Thanks. So in this slide, that's an overview of what we do, and of course that took half the time already. But I'd like to talk about one topic that we're particularly excited about in my group, which is more along the lines of the using AI and ML, or I hate using the word using because we're not using it out of the box, innovating AI and ML innovating AI and ML for the communications domain. Okay. This is called work called robust nonlinear feedback coding via power-constrained deep learning. And this with my collaborators, my student who just newly minted PhD, collaborator at University of Kansas, one of my close colleagues over here in ECE. This paper is just accepted to ICML. Okay, so we're down at the physical layer now, talking about channel coding. Okay, in channel coding is also known as forward error correction or error control coding. And the idea is that I want to control for any noise, any imperfections that may exist in the channel between a transmitter and a receiver, using some codes that will be robust against the noise. So I have an encoder that's going to actually, encode what I'm originally trying to transmit into some vector X of bits, that when it gets sent over the channel, the idea being this coded version would be more robust and more efficient than if I sent the original bits themselves. And then the idea is, ideally I'd like B to be equal to B hat. Of course, it's not going to be exactly equal, but how close can we get, right? So we add this kind of redundancy to be robust against channel noises. A lot of times at the transmitter, we add extra bits within the raw bit stream itself. That's a standard technique that's used. And then at the receiver, the errors would be detected or corrected as and the bit stream is actually recovered. Okay, so this problem has been studied a lot under specific models for channels, additive white Gaussian noise channels in particular. That sounds very complicated, but what it means is that the noise that's introduced over the channel is Gaussian. It's a normal distribution in nature. Okay. It's a standard noise model. For such an AWGN channel, Claude Shannon, one of the fathers of information theory, introduced this capacity measure. It's just the maximum capacity that the channel can possibly have is logarithmic in the power that we're sending over the noise. That many bits per use of the channel. It's the best that we can possibly do. And we now have near optimal or capacity achieving codes for these kinds of channels because over the past 70 years, there have been extraordinary advancements in this field. Okay. The turbo coding, for example, LDPC codes, these are all near optimal codes. Okay. So a question we can ask, though, what would you do if there was some feedback available? This is entirely forward-facing, but if I could have some feedback from my receiver to the transmitter about what the receiver actually measured, could we actually do better in this case than just looking at this as a forward coding problem? Could I use some kind of feedback information? So feedback coding has also been studied quite a bit. We have feedback-enabled channels. In this case, the transmitter has access to a delayed version of the received signal. So over that forward link, then whatever is actually received before it's decoded, with some delay, I can feed that information back to my encoder. Can I use that to update what I'm sending to try to be more robust? Maybe look at the difference between what I expected versus what I intended, or what I expected versus what actually happened, and use that to, possibly retransmit, possibly modify what I'm transmitting, so on. So, but I already used the term that we can achieve near optimal codes, or we can achieve capacity. So we can't ever get better than the capacity of the channel, right? So using feedback information cannot increase the capacity. That's not going to happen unless something really strange happens and physics changes, which I don't think it has. Hopefully it hasn't. The second fact, however, the communication reliability measured in terms of our bit error rate can be largely improved using such feedback because of the fact that there's noise in the channel. So that capacity is really in a longer-term expected value sense. But we can improve the reliability, like looking at their probability of each individual bit, say, having an error in it. So given finite block lengths, a block is just you think of it like a byte, actually. It's just a certain number of bits that are being transmitted. Given a finite length, feedback coding improves the error probability over traditional channel coding. So feedback coding has been studied from a linear perspective for, say, the past maybe 10 years or so. It was studied first with noiseless feedback, but then if you have noisy feedback, my collaborators back about 10 years ago studied this problem of what to do if what's actually coming back also is adding a noise, right, which is more practical. It's never going to be noiseless. You can have a delay, but you're also going to have noise. Whenever I have a separation between a transmitter and receiver, there's always some noise that's introduced, right? They study it from this linear perspective, okay? And there are several interpretations you can make. When we build linear code books, they tend to have very nice properties. Just like in electrical engineering in general, if a system is linear, it tends to have a lot more easily manipulated mathematical properties, much more beautiful results mathematically, right? But this linear assumption on coding does limit the performance. So the idea that we've been looking at is, can we use AI and ML to actually induce a nonlinearity in the way we do channel coding? How do we look at this nonlinearity to improve the performance? So rather than having linear encoder and decoder, can I make them nonlinear? That's what ML is really good at, taking problems and making them nonlinear when it's necessary. So when our theory fails us, which we've seen, these linear assumptions are not great, especially when we have very noisy type channel conditions. Okay, so we're not exactly the first ones to do this, I should say. This was looked at back in 2018, about 5 years ago. This ML-based nonlinear feedback coding. There was a paper in a conference, a great conference called NeurIPS, Deep Code, they called it. Deep learning-based coding, deep code. They proposed using RNNs, recurrent neural networks. RNNs are a very common structure that we have in machine learning. We also have convolutional neural networks, tend to work very well in vision problems. RNNs work very well with time series problems. We have some time dependencies. And they use RNNs to introduce this nonlinearity. So out of the transmitter, the idea is that I take my individual bits, these are zeros and ones, I convert them to a BPSK format. So what it actually, this is just a conversion from a 0, 1 to a 1 minus 1, multiplying it by 2 and subtracting 1. And then based upon what actually ends up being sent out, I can receive feedback. And the feedback I get is this Y1 hat, for example, from the first bit that I sent, Y2 hat being from the second bit that I sent, and so on. And so what I feed into the RNN in each stage is the next bit and the feedback of how the reception happened. And then the feedback additionally, and I keep going down the line, right, until I get to my kth bit. So we're feeding into the RNN in each step is not just the new information, it's also the error, essentially, between what was received versus what was intended. Okay. So this is what deep code did, and deep code improved the bit error rate performance over existing linear coding schemes in many noise scenarios. Okay. It obtained very nice results and is very popular work. But it's still very vulnerable to large channel noises, which tend to happen in reality. Okay, channel noise is large. We tend to deal with large forward noise and large feedback noise in many situations. That could be, just noise due to interference, friendly interference. It could even be malicious noise that's being entered into the channel. Right? So it's very important to build resilience against such noisy schemes. And so that's what we did in this work. We looked at how to build a deep learning-based feedback coding scheme that obtains much better properties against noise, against both forward and feedback noise. Okay. Two main challenges that we faced along the way. First one is, as I mentioned before, physical separation between where the encoder and the decoder are. Right? I don't know how far away they are, but anytime they're separated, it means that the latent space that's learned at the encoder side, if I send that over to the decoder side, I'm going to get some perturbed version of it. It's very hard to synchronize the two latent spaces, right? Because we have separation over noisy channels. So we have to figure out how do we do this kind of joint training, dealing with that, those mismatches in the latent space. And the second challenge, which is often overlooked, and this is really much more of a practical challenge, is we need to have efficient power control. Okay, because we can't just do an unconstrained increase of the power that's being inputted at the transmitter side. I have to make sure that the total power in my transmission of n bits is less than some upper bound, n times p. So this is hard to do because this now I'm saying I want to turn this into a deep learning problem, but I also want to have a constraint, power constraint. So that's why our end-all solution becomes what we call power constrained deep learning. Okay, so the way we ended up solving this problem was using, we introduced a power control layer at the encoder, and we were able to show mathematically that we can satisfy, using our power control scheme, that we can satisfy that constraint in an asymptotic sense for our scheme. And then we also maximize the denoising effect that we get from looking at longer block lengths. So the original deep code scheme was bit by bit processing. And now what we look at instead here is block by block processing, where we get a denoising effect that we get from information theory. We consider the entire bit stream as a processing unit, and we also add some what are called attention mechanisms. We add attention mechanisms at the decoder side, which help us boost performance on certain bits that are having more errors in them. Okay, so I'll skip over the system model here, go right to the architecture. This is just to show you it's pretty involved, but at the same time, it's as much simpler than many deep learning models are today. This is what exists at the encoder side. This is the encoder. So the bit stream is sent through a bunch of GRUs. Those are called gated recurrent units, GRUs. And then the feedback information of what gets received. So this is transmitted and it's fed back with noise added. That also gets fed into the next time. So this is basically we have two GRUs stacked, one on top of another, and we're feeding in the feedback information each time, all the way up to the nth feedback, or n-1 feedback for n transmissions that come in. This is on the encoder side. And then on the channel itself, right, that's where the noise happens. And then on the decoder side, we actually have bidirectional GRUs out here, and we use those bidirectional GRUs to get this attention mechanism. So we do both a forward pass as well as a reverse pass through all the information and aggregate all of those out. So by doing this additional linear combinations up here, on the outputs of the GRUs, we can get additional denoising advantages. Okay? Even if you want to just forget about these mathematical details, I can show you it works really, really well. Okay? When we have high feedback noise, so the feedback noise power here is particularly high. You can see our proposed method. This is in a short block length regime. We're only using 6 bits in each block. When we have feedback noise that is high, we're obtaining pretty nice, like an order of magnitude on a log scale, advantages over even the best, the deep code scheme. You can see deep code, that was the ML-based, the deep learning-based approach from 2018, ends up not really getting much of a gain either in lower feedback noise regimes, but ours is really able to take advantage as the feedback noise gets lower. So we're able to take advantage of noisy as well as non-noisy feedback until eventually, when the feedback noise is low enough, we get overtaken by traditional just linear schemes, as we would expect. They would tend to work the best under ideal conditions. And then as we consider medium or longer block lengths, we also see very nice advantages again, like 2 orders of magnitude even over this deep code scheme. The only schemes that end up beating us here are when we use turbo codes. They're called turbo codes with extremely long block lengths, and they only beat us when the feedback noise is very low, because turbo coding is just it doesn't use feedback information. But under an ideal channel, basically what we're saying here is that under a very ideal channel condition, you still want to go back to what decades of information theory taught us and use something like turbo coding. But once you start adding noise in, that's really where we can get these gains. So I'll go ahead and stop there, I think. I had some slides as well for the second part. This is more on upper layer type machine learning, but I'll leave you with that. So I was pretty excited about it. The paper just got published about 6 days ago or something. So Happy to talk about it today. Thank you.
All right. Any questions from the audience? All right. If not, thank you to Professor Chris Brinton. We're going to get our next speaker up here. Institute of Technology, and a master and PhD from electrical and computer engineering at Purdue. His research interests include low power variation, aware VLSI circuit design, neuromorphic computing, in-memory computing, nanoelectronic and spintronics, as well as device circuit closed design, and nanoscale device modeling and simulations.
Is it good? Yep. Okay. And okay, shall I use this or clicking this is not working?
Will that work?
No.
Is it not hooked into your?
Is it not?
I wonder why it's not working. Is that the same one he used?
I
Oh, here,
guess.
let's try this. Here, let me make sure this is clicked on here. Sometimes, not try it.
It's okay, I can use this if this works. Just a second.
Yeah, I made it a little bit too big for you, sorry.
Yeah, this works, but let me try this. No, this is not working. That's okay. I can use this. No problem. Okay, thanks. All right, so today I will be talking about our research on ferroelectric transistors and its technological capabilities to enable in-memory computing. So I'll try to give you a flavor for different kinds of computing in memory frameworks and how ferroelectric transistors can be utilized in some interesting ways for that. All right, so this is what we are going to talk about today. So I will first start with an introduction to computing in memory, so that we are all on the same page. Then I will go into a little bit of the basics of ferroelectric transistors and talk about some of the interesting aspects of FEFETs that are really appealing and are triggering a lot of research into these devices. And then I will talk about FEFET-based SIM architectures for two broad applications. One will be on artificial intelligence accelerators. How can we use FEFETs for those? And the second one will be for general purpose computing. Again, merging the computing and memory together, considering some of the requirements of general purpose computers. So let me start with a brief introduction to computing and memory. And to motivate it, I think all of us know that we are really living in this era of big data. So we are dealing with lots and lots of data. And to give you an idea about the kind of data that we are attempting to process, this graph from Seagate, it kind of shows the picture how the global data sphere is kind of growing, And what is predicted is that by about 2025, we will be dealing with about 175 zettabytes of global data sphere, right? And to give you an idea, 175 into 10 to the power 21 bytes, right? And to give you an idea about what that means, so if you store this data in, let's say, DVDs, the standard DVDs that you get, and you stack them, then you can circle the Earth 222 times with that, okay? So that's a pretty amazing amount of data, and not just that. If you look at the real-time data trends, right? How much data we are kind of consuming or generating when we are communicating with each other, those real-time data trends is also growing. And that is about it is going to go to like about 30% of the global data sphere, right? And if you see like around 5,000 daily data interactions per connected person. So it's a huge amount of data, right? And what that means is that in order to deal with that amount of data, for our electronic systems, there will be an enormous load, not just on the storage, but also data processing and data communication, right? So that means that we really have to rethink about our designs that we have been kind of pursuing. And of course, the standard architecture that our computers use, all of you must be familiar with this, is what is known as von Neumann architecture. And this is not really very well suited for the kind of data-intensive computing that we want to do, okay? And the reason is that in these architectures, the memory unit and the compute unit are two separate entities. So this has worked very well for the kind of applications that we have been dealing with. But now with data, a lot of data that we are kind of are going to process now, there will be a lot of performance limiting and power hungry data transfer between the logic unit and the memory unit, which is not a very good thing. So the solution to this, at least one of the potential solutions, is can we merge the memory and the logic functionalities together, right? And that gives rise to this paradigm called computing in memory. So the idea is that we'll have one entity which will not only store the data, but also process the data, right? So that is the idea, and if that can be done, then we can eliminate this processor memory transactions that I was talking about and really save a lot on power, especially for the data-intensive applications that now we are going to deal with. So I'll go over the basics of computing in memory. So there are different ways of merging the logic and the memory functionalities together. But one of the most common ways is what is known as multi-word line assertion, okay? So the idea is as follows, okay? So let's say you have this memory array, which is storing some data, right? So in a standard architecture, what you would do, how you would use it, use a memory is, let's say you assert this row, you activate this row, and let's say read or write into this, selectively into this row, right? But now with the in-memory computing, what you do is that now you think about asserting multiple of these rows and then doing some post-processing with the data, and that I'm going to talk about, okay? So the first way to look about this is, accelerating the matrix vector multiplications operation by doing these multi-word line assertions. And these matrix vector multiplications are one of the dominant computing kernels for AI applications. Okay, this is, if you can accelerate this, then potentially you can get a lot of energy efficiency improvement in your artificial intelligence accelerators, right? And the way it works is as follows. So let's say you have some sort of a matrix stored, and I'll call it a conductance matrix. Each of these elements is like a resistor or a conductor, nonlinear or linear. But it's some sort of a conductance, right, that you are kind of storing in this array. So you can think of that as a matrix. And the input vector that you want to multiply it with, you apply that as input voltages, right? So this is right here. This is the voltage vector. And it turns out that, the current that will be flowing through this element will just be a multiplication of this conductance times the voltage. And if you collect all the current on this green line, right, this is the output line, then the Kirchhoff's current law will naturally sum up this current. And you will get, if you kind of do all these, calculations, then you can show that this output will correspond to, all these outputs will correspond to the matrix vector multiplication of this conductance matrix with the voltage that is being applied here, okay? So this is one form of in-memory computing. And the other form is for general purpose computing. And if you just change the perspective a little bit, then you can also kind of compute some Boolean or arithmetic functions within the memory. And again, the idea is very simple. It's similar to that, but with a slightly different perspective. And the idea is now we want to achieve computations between two operands which are stored within the memory, right? Here what we are doing is, because of the demand, with the nature of the AI workloads, we are performing the operation between a conductance matrix which is stored in the memory with some external signals, right? These are like synaptic weights, and these are like, the neuron, the outputs of the previous neurons, right? So that is how the AI workloads are. But for general purpose computing, a lot of times what you want to do is you want to compute functions for in-memory operands, so A and B, and you want to, let's say, add them, right? So again, what you do is you assert these word lines corresponding to these operands that are stored in the memory. You sum up the currents on these green lines, and you will get different combinations. And what you can do is if you choose a proper reference, you can compute A or B or A and B, simple Boolean functions. And then what you can do is that you can use these simple Boolean functions to actually perform additions of these words within the memory itself, right? So these are some general purpose, computing architectures can kind of really make use of some of these techniques. All right, so this is the basics of the in-memory computing. And what are these memory elements? Well, these can be anything. These can be CMOS memories, which I think we are all familiar with, like SRAMs or DRAMs. But they can also be some non-volatile memories. And there are different kinds of non-volatile memories in that storage landscape that we are talking about, right? So in this talk, I'll mainly be focusing on the ferroelectric transistors. So I'll talk about that in a moment. But in our research, especially in this JUMP Center for Brain-Inspired Computing, we are looking at different technologies and what are the implications for in-memory computing in general, okay? But today I'm just going to focus on FEFETs. All right, so let me go over the basics of FEFETs and talk about some fundamental physics. Of course, I'll not go into the details, but just try to give you a high-level overview for that. So what are ferroelectric transistors? Well, what you do is you start with a standard transistor that we all have studied. And what you do is that instead of having a simple gate oxide, a dielectric, you integrate a ferroelectric material in this gate stack. And this ferroelectric material is a non-volatile material, which means that it can retain its charge even if you shut off the power supply, okay? So let's say if it retains a charge or a polarization which is pointing towards the channel, then you will get a low resistance state. While if it is in the opposite way, then it will be the high resistance state, right? So you can get a transistor which has an inbuilt non-volatility in it, okay? And that's very interesting because that can be utilized for computing in memory in some very interesting ways. And also, not just for computing in memory, but also for, storage in general. And what, this is showing, these are some experimental results from some other groups, so this kind of a functionality, non-volatile functionality has been demonstrated, where you can really control the threshold voltage of your transistors by playing with the polarization that is stored here, right? And that you can do by applying some programming voltages on the gate, okay? So this is a very interesting non-volatile technology, like I said, because it's kind of combining the non-volatile storage within a transistor, which is very amenable to compute. So it is kind of combining that compute memory functionality at the device level, which is very interesting. And what this enables us to do is that you can design a memory array with just one FEFET, right, as opposed to 6 transistors in SRAMs, in CMOS SRAMs. So this is a very compact solution that you can get, right, as I'm showing here. So I'll not go into the details, but certainly this has a lot of advantages that people are looking at, but also its own set of challenges, okay? So I'll leave the discussion of those challenges for another day, but happy to talk to you about those if you are interested. But certainly this is a very appealing technology from the storage point of view, okay? So what we are doing in our group is that we are trying to understand the fundamental physics of this device, of this technology. And for that, we are developing some detailed phase field models, what are known as detailed physics-based models. So of course, I'll not go over the equations, but just to mention that we are solving some of the fundamental equations that govern the operation of these ferroelectric devices, self-consistently with these, with the electrostatics. And in fact, the material that is used these days, which is of a lot of interest, is what is known as hafnium zirconium oxide, okay? And it is like, the standard high K dielectric that you use in your transistors, in your computers that are there, but you just, change that material a little bit, dope it with zirconium, and you get ferroelectricity, okay? So it's very CMOS compatible, but that material has a lot of interesting physics in it, okay? So for example, it has multiple grains, so we are trying to capture that effect also through some of the 3D grain growth equation and coupling it with these phase field models, okay? So we collaborate with some leading experimentalists in this area, and we make sure that our models are predicting the trends that we observe in the experiment. So you see some of the calibration here, right? And because these are very detailed physics-based models, we are able to kind of study some of the microscopic polarization profiles through these models. For example, here I'm showing, so let's say this is a device based on its ZO, and if you apply different cycles, so as it is kind of cycling through, it is kind of changing the polarization profile. These red and blue domains are changing, and this is something that is very fundamental to this material, and it gives rise to what is known as stochasticity in these devices. All right, and this can be very useful for switching, for computing. Okay. So with this, we are able to capture some of these detailed physics. So what I wanted to do is to give you some idea about what kind of fundamentals are there, fundamental physics is there that governs the operation of these devices. And for that, let me briefly talk about a very important phenomena in these devices, which is known as multi-domain effects. Okay, which gives rise to some of some of the appealing properties, appealing characteristics for storage as well as for computing in memory. Okay, so let me start with this very fundamentals. So when we are talking about the ferroelectrics, then we have energy which is called a free energy term. So it is kind of a sixth order polynomial, and it gives rise to this double well potential. Okay, this you'll see in a lot of memories. This is kind of an energy landscape for non-volatile kind of memory elements. And what this shows is that the system would like to be either in this minima or in this energy minima, and this is what gives rise to its non-volatility, the bistable state, right? So let's say if I have this ferroelectric, and in a device, in a real device, it will kind of be in series with some sort of a dielectric and some sort of a capacitance, okay? So if, let's say, it is what is known as a single domain behavior, which means the whole of the ferroelectric is kind of behaving as one entity, then it turns out that this is not a very, this is kind of a high energy state. And that high energy state is really coming from the fact that this dielectric causes some depolarization fields to appear in this ferroelectric. And that raises this energy, right? This leads to this additional term, which is not very conducive for this whole system. So in order to minimize the energy, what this ferroelectric likes to do is break into multiple domains. And when it breaks into multiple domains, then it is able to lower the depolarization energy, all right? But then this also comes at a cost. There is an energy associated with this, which is called the gradient energy, okay? So anytime the ferroelectric breaks into multiple domains, there's a cost associated with it. And this gradient energy, again, depending on which one is higher or lower, it'll like to kind of develop a configuration, a multi-domain configuration, which will minimize the energy. So that's the whole picture. So it'll come to a state which will find that balance between the depolarization energy and the gradient energy, and will kind of try to minimize the energy by balancing these two opposing effects. All right? So that's the picture, and this gives rise to some interesting physics. Right? So one of the things that I want to talk about, which will be important for computing in memory, is the concept of memory window. And one of the things that we have been trying to do in our research is trying to understand what are the key design knobs for this technology, which will help us to optimize the performance of computing and memory architectures. Okay, and one of the key design knobs is the ferroelectric thickness, the thickness of the ferroelectric material. And we have been studying the detailed physics of what is the implication of scaling the Fe thickness. And one of the important characteristics is that the memory window, and I'll talk about what memory window means. It's really the hysteresis that you see in these polarization versus applied voltage characteristics. And this hysteresis, the width of this hysteresis is important for memory, for storage, but I'll also talk about why it is important for computing and memory. Okay? But what happens to this memory window is that as we scale down the Fe thickness, then that kind of memory window decreases. And you can see that our model is able to kind of predict the trends very well, as shown by the comparison with the experiments, right? So by understanding some of the physics that is involved in governing this behavior, why this memory window decreases and in what way it decreases, we are able to quantify some of these effects. And this memory window is going to play a very, very important part in some of the computing and memory performance and robustness. Okay, so remember this trend. And one of the other important trends that I want to talk about, which again will play an important role, is the fact that as we scale down the ferroelectric thickness, the effective permittivity of this ferroelectric, okay, how well it responds to the charge, it kind of increases. So you see the experiment, this is seen both in the experiments and in our model. It increases as we scale down the Fe thickness. And by the way, this has been shown in multiple experiments. And this increases beyond its intrinsic values. So there are some interesting electrostatics that go on. Okay, so again, this is very important to capture when we are talking about some of the memory and the computing and memory applications. And I think I'll probably skip this slide, but we have kind of, based on our phase field models, we have kind of tried to explain why this happens. Okay, this is a very interesting effect. And with our phase field framework, we are able to kind of study this in detail, but I'll probably skip this in the interest of time. Just want to mention that this is really a multi-domain phenomena, okay? This is happening because the ferroelectric is breaking into multiple domains, and because of these multiple domains, when we apply some voltage, then you just don't get that conventional dielectric response, but you also get what we are calling some transformation of these in-plane fields to the out-of-plane fields, which kind of increases or enhances the effective permittivity, effective charge response of this material. So this is really a multi-domain phenomena, but again plays a very, very important role in the operation of these devices. Okay? So I'll skip the detailed explanation, but I'm happy to talk about it. But let me proceed with how we utilize this in our SIM performance, the computing and memory performance evaluation. And for that, we kind of develop a compact model based on these phase field models, which basically couples this ferroelectric phase field model to a transistor, and you can see that this shift in the threshold voltages that I was talking about, the model is able to do a reasonably good job. As you can see, it is matching quite well with the experiments. All right? So with this background, now I'm kind of ready to kind of discuss some of the computing and memory applications, and I'll start with the first one, which is the application of ferroelectric FETs for matrix vector multiplications, targeted for AI applications. Okay? So again, the idea, just to remind you, was that we have a conductance matrix, we apply some voltages, and it is able to compute the matrix, the product of this matrix and the vector on these green bit lines. But this is the ideal condition, okay? What happens when we actually put them in hardware? There are several hardware non-idealities that come into the picture. So what happens is, let's say we have this array. We, of course, have to connect them through the wires. There will be some wire resistance. These voltages have to be driven by some drivers. They will have their own resistance. I have to sense this output. That will have its own resistance. So all these hardware non-idealities, circuit non-idealities come into the picture. And of course, the device that I'm using, for example, a ferroelectric FET, or any kind of device, will have its own non-idealities. Okay? It will not be a completely linear or an ideal device. So what happens here is that when I look at the actual output in a hardware, then there is a lot of deviation from this ideal or expected output that I wanted. Okay? And this can lead to some computational errors, and therefore it is very, very important to understand this. So what we are doing in CBreak is that we are capturing this in detail. For example, for ferroelectric-based computing in memory, what we do is we put these detailed models that I talk about, couple them self-consistently in a circuit framework, and capture this non-ideal effect. And we have in Professor Kaushik Roy's group, he has a tool called GenieX, which kind of models the non-ideality in general and is able to kind of predict what is the impact of these hardware non-idealities on the system accuracy for AI applications. Okay, so this is the framework that we are using. And I'll give you one snapshot of what kind of analysis we can do with this, and hopefully this will also kind of put across the kind of concepts that I want to convey, like what is the effect of some of the technology parameters on the system level accuracy. Okay, so what I'm showing here, again, is what happens if we scale the ferroelectric thickness. So what happens to these device characteristics, the drain current versus gate voltage characteristics. So these are different characteristics. This is the reset state of the ferroelectric FET, which corresponds to weight equal to 0, the synaptic weight of 0. Then these are 3 set states, and I can shift the threshold voltage by programming appropriate polarization value, right? So what happens here, what you see, there are two interesting trends when you scale the Fe thickness. One interesting trend, which I think all of you know, is that the leakage associated with these devices is going to decrease, right, as you scale the Fe thickness, right? So this current is decreasing, all right? And this current decrease is dependent on not just the standard scaling behavior, but also because of that enhanced permittivity change, or the enhanced permittivity with Fe thickness scaling that I talked about. This leakage reduction is also kind of amplified. Okay, so this is very important to capture. And the other trend that I want to talk about is this memory window reduction. And I mentioned in the earlier slides that the memory window decreases as we scale the Fe thickness. So what is going to happen is, because of this reduction in memory window, this current that I have circled here in brown, that increases with the Fe thickness Fe thickness scaling. And these two currents I'm particularly drawing your attention to, because these are the non-ideal currents that kind of can lead to some computational errors. Why? So let's look at these two cases. So these currents correspond to the actual output, the expected output of the computing in memory to be 0. Okay, and ideally we want that to be 0, right? Of course, that we'll not get. So this blue current corresponds to when the input is 0 and weight is whatever, right? The output is supposed to be 0, but then what is happening is that the leakage is kind of coming into the picture, and it is kind of leading to these non-idealities. But of course, we want this current to be as close to 0 as possible, which means as low as possible. So with Fe thickness scaling, what is happening is that this current is reducing, which is good. So the FE thickness scaling is amenable to reducing this non-ideality. But the brown current, it also corresponds to output of 0, which corresponds to when input is 1 and the weight is 0. So again, we want that to be as low as possible, but that is kind of increasing as we scale the FE thickness. So there are two opposing effects that are coming into the picture. And now what happens because of that is that the FE thickness impact, scaling impact, is not as straightforward, okay? So what happens, there is a non-monotonic behavior, and it turns out, let's say the 7 nanometer FE thickness is able to attain the maximum accuracy considering these different non-idealities. So this is the system level accuracy for these 3 different FE thicknesses, considering nominal conditions, considering variations, considering faults, and it turns out that the 7 nanometers somehow is able to balance these 2 opposing effects and attain the maximum accuracy, okay? So this is one snapshot that I wanted to kind of give, just to highlight the interactions that go on all the way from the technologies to the system level, and why it is so important to understand some of these cross-layer interactions so that we can really understand how to optimize these technologies for computing and memory. Okay? So this brings me to the, so I'll skip this slide in the interest of time, but just want to mention that some of the other things that we are doing in our group is to understand the impact of other non-idealities like faults, and what are the solutions for that. Okay, so I won't go into the details, but just mention that we are looking at some of the hardware design solutions for mitigating the effect of faults on the system level accuracy. So this is one design that we had looked at, where we are looking at differential encoding to kind of bypass the effect of some of the faults. Not only that, we are also looking at how we can bring in training into the picture and engineer what is known as the loss landscape of a neural network, and utilize that to get reduced impact of faults on the system level accuracy. Okay, so I won't have the time to go over all these, but certainly I'll be happy to talk about this. So what I had in mind was also to talk about the other aspect of computing in memory with FEFETs, but let me quickly check on the time. So how much time do I have? 5 minutes? Okay. So maybe I'll utilize these 5 minutes to just give you a very, very brief idea. I won't have the time to go into the details, of course. But what is the idea again? So the other aspect of computing in memory is that you take these 2 in-memory operands that are stored in memory and try to do some computations with these. And the standard way of doing these, some of the works have really explored this effect, and what they do is that they assert these word lines, they sum up the currents on these bit lines, and when you sum up the currents, these will be a function of what is stored in these 2 memory cells, right? And so you will get 3 kinds of currents, right? These are the 3 currents that you get in black. And if you place a sense amplifier reference at an appropriate level, then you can compute OR and AND. And once you have OR and AND, or their complements, then you can utilize this compute module to actually do additions of these 2 words that are stored in the memory. So you're doing these additions, you're not sending it to a processor, but you're really doing these additions within the memory macro. So the problem, or one of the limitations of this approach is that, these 2 vectors that you see are mapped to the same current. So this approach will not be able to distinguish between 0, 1, and 1, 0 vector. And why is this important? Because of this limitation, this existing approach is not able to do the computations in memory for non-commutative functions. And there are some very important class of non-commutative functions like subtraction and comparison, right? So for those, we have to resort to the standard ways of doing the computation, which is to read first word, read the second word, and then compute. So what we looked at is, so let me skip some of these slides and just give you an idea. So what we looked at is a technique which we called asymmetric dual row activation, which is, or ADRA, and the idea was very simple but very effective, is to get around that many to one mapping between the input to the output by using 2 different voltages, right? That is the high level idea. Of course, there are more details to it. But if you use 2 different voltages, what you can do is you can have 4 distinct output states for these 4 vectors. And once you have that, then you can actually perform single cycle 2-bit read. That means in a single cycle, you can read 2 words, okay? And with that, you can do actually computations of any Boolean or any arithmetic functions. And of course, you don't want to do very complex functions because otherwise, your peripheral circuits will really, grow. So it has to be done judiciously. And what we have explored so far is how this technique can be utilized for doing some in-memory subtraction, comparison, in addition to the standard Boolean and additions that existing approaches have done. Okay, so I'll kind of skip all the details, but just mention that maybe I'll just take a few seconds on this slide, is that if we do this, then we can get a lot of speed up across 2x speed up, approximately 2x speed up. And why we're getting to this 2x speed up is that instead of using 2 cycles to read A, read B, and then doing the subtraction, we are actually able to do the subtraction in just 1 single cycle. Okay, so almost 2x speed up, and we also get some energy decrease in certain cases, which is also important. Okay, so I'll skip all these details, and maybe I'll just summarize this talk. And I'm sorry that I could not go into the details of the second part, but I'm happy to talk to you about. But to summarize, the ferroelectric transistors are very, very interesting technologies as they combine the rich physics of hafnium zirconium oxide with the transistor. And there are some interesting scaling behaviors that we have studied, and I talked about one of them in the context of machine learning applications, and showed that really the cross-layer interactions are very, very important to understand and capture in some of these frameworks. And the other part, which I really went very fast, was how we can enable this computing in memory for general purpose computations within the memory. And in that context, our technique ADRA is able to really extend the kind of functions that you can compute within the memory to a large range. Okay? So with that, let me thank you, and I'm happy to take any questions if there is time. Thank you.
All right, any questions from the audience? Yes.
Oh, so for your matrix vector multiplication using the kind of the current, so you said that there is some resistors on the circuits, and then you use like the deep learning model to kind of cancel that effect out. All right, is that right?
So, so your question is, how do we cancel this, or how do we get around this?
I mean, from my point of view, it's a fixed kind of errors because those resistors are fixed.
Yes.
And then, I mean, from the quantum point of view, we dealing with something like this too, and then we use something called confusion matrix, where we establish that, and then we we take the inverse of that matrix and apply into this, rather than have to train a deep learning model, which is essentially doing the same matrix.
Sure, sure, absolutely. And this is a very, very good question. So certainly, these techniques are utilized if the errors can be predicted, right? So some of these errors are predictable, and certainly you can use the training of the neural networks to kind of be aware of these predictive non-idealities and get around these, certainly. But some of these are not, right? For example, variations, for example, faults. Even the effect of wire resistance, it depends on the input vector and the distribution of the weights and how you bit slice, and there's a lot of variables there, right? So some of them are predictable, which you can certainly take care of, like you said, but the ones that aren't will have effect on the accuracy. And therefore, by what we do is, of course, that is one method, that train it, being aware of this non-idealities. But the other knob, which is a complementary one, is to kind of design the technology, design the device in such a manner so that it can, minimize the effect of these non-idealities. And that is what I attempted to give you an overview of, right? So if we want to kind of, if we have these non-idealities, how do we think of designing a technology so that it can minimize their effects? And that can be complementary to the kind of approaches that you're talking about. Absolutely. Okay.
Any more questions? If there are no more questions, let's thank our speaker again.
Thank you.